Welcome to our esteemed judges who have joined us today. Before we begin our session, an important announcement. The next session of oral presentation will begin at 1:30 p.m. in the Nobel Laureate Hall. With that, I would like to invite our first speaker to come forward and begin their presentation. I wish you all an informative session.
Please note the rules for presentation. The duration of presentation is 7 minutes and 3 minutes will be given for the Q&A session. After 6 minutes, a short bell will ring and the final bell will ring after 7 minutes. Now I invite our first speaker, Tijo Anthony, code number APB05.
Organic acid hydrolysis. Cellulose is the most abundant naturally occurring polymer, and it is formed by the beta-1,4 glycosidic linkages of D-glucose units. And cellulose microfibrils are the basic structural unit of all plants. The hierarchical architecture of natural cellulose consists of nanoscaled fibrils and crystallites. Various mechanical and chemical methods leads to the defibrillation of cellulose microfibrils into nanoscaled cellulose structures. These nanoscaled cellulose structures are mainly classified into cellulose nanofibrils and cellulose nanocrystals. These cellulose nanofibrils are made up of elongated bundles of elementary nanofibrils, and they consist of alternating crystalline and amorphous region. They have a width of 20 to 100 nanometer and a length of 500 to 2000 nanometer, whereas cellulose nanocrystals are some needle-like crystals with limited flexibility and higher crystallinity. They have a width of 5 to 50 nanometer and a length less than 500 nanometer. These cellulose-based nanoscaled structures can be used in a wide range of applications. They can be used as reinforced in polymer composites, and they can be used in the field of biomedical applications and all. This is the experimental section I adopted for the extraction of nanocellulose from the bark of Saptolobus parviflorus. This Saptolobus parviflorus is a woody creeper plant found extensively in Kerala. The bark of Saptolobus parviflorus is collected from Idukki district. Then it is chopped and dried under sunlight. Then it is grinded using a mixer grinder. After this, the hemicellulose is removed from these fibrils by alkali treatment. These ground fibrils are treated with 5% NaOH and boiled for around 45 minutes. This process helped to remove the hemicellulose from the samples. After the alkali treatment, it was bleached using peracetic acid. Bleaching helped to remove some other impurities like hemicellulose, lignin and pectin. Then these bleached fibrils are steam exploded in an autoclave at a pressure of 25 psi for around 45 minutes. The steam exploded fibers are then well washed with water and they are undergone high pressure homogeneous in an ultra-Turac homogenizer. And we get a nanocellular suspension. This nanocellular suspension is further characterized. This is the result and discussion structure, and this is the FTIR spectrum of fibrils under different processing stages. From this FTIR spectrum, it is clear that no more any additional functional groups or any additional groups are attached to the fibrils, and the main peak at around 3,400 centimeter inverse is due to the presence of hydrogen bonded OH groups, and it shows the hydrophilicity of fiber. All other peaks are listed in this graph. This is the scanning electron microscopic images of fibers under different processing stages. The figure A1 is the raw fiber, and we can see the smooth surfaces of the fiber. Here the fiber is immersed in a matrix of lignin and hemicellulose. The figure B1 represents the fiber after alkali treatment. Here also we can see that the fibers are attached by the cementing material lignin. Then after the bleaching treatment, we can see that the cellulose fiber diameter is very much decreased because it removed the lignin content. Then this figure D1 represents the same image of the obtained nanocellulose. These are the transition electron microscopic images of the cellulose, nanocellulose. We can see that this nanocellulose has a crystal needle-like structure, and these crystals have a chain-like connection, and they have an obtained CNC have an average length of 326.16 nanometer and an average width of 26.42 nanometer. These are the AFM images of nanocellulose obtained, and the average length and width is further supported by these images. This is the dynamic light scattering of nanocellular suspension in water, and we obtained the average particle size as 354.4 nanometer. Then these are thermogravimetric analysis curves, and we can see that this obtained nanocellulose has a higher decomposition temperature than the raw fiber, and it is around 363.4 degrees Celsius. And this is the XRD diffraction pattern, and it is clear that crystallinity is increased after each treatment, and crystallinity index is about 85.91%. And this is the zeta potential analysis, and the surface has an average zeta potential of minus 23.3 millivolt. And these are my conclusions. Highly thermally stable cellulose nanocrystals was successfully isolated from the Bacchus Saptophilus parviflorus using oxalic acid hydrolysis. The isolated Saptophilus parviflorus CNCs has an aspect ratio of 9.96 plus or minus 0.72. And the crystallinity index was around 85.9%. And these SPCNCs can be used as a reinforcement while making polymer composites. It's the end of my presentation. Thank you all.
To John. The initial processes you have used peracetic acid as the bleaching agent.
Yes.
Why you haven't used this hydrogen peroxide, which is more green in nature?
Yeah, Otherwise, we can use this sodium chlorate or sodium hypochlorite. I think this chlorine is somewhat harmful to the environment.
You haven't tried hydrogen peroxide? Hydrogen peroxide.
Yeah, H2O2 and acetic acid mixture.
Not paracetic acid.
Not
Then
paracetic acid.
instead
it's a
of prepared.
reactive mix.
And in the initial process also you have used oxalic acid.
Yeah.
What is the use of this oxalic acid?
Um,
For what purpose?
the surface is in order to get negatively charged and to you get a well dispersion.
Well, dispersal.
And I think for the next step it will be more helpful for me to make the composite.
Okay. Then in the IR spectra, all the samples look similar.
Yeah.
IR.
Yeah.
Then how you can infer that the product is different from the starting material?
I think the around 1510 centimeter inverse we can see the CC stretching of lignin, and it is somewhat diminished in intensity.
That is the only conclusion.
Tijo, what is the reason behind choosing this Parviflorus, and what is its common name?
Yeah. In Malayalam it's known as Adamb.
Adamba.
Yeah. It has a good, I think it has used by the local farmers to bind some, and I think it was more mechanical strength. While making for the composites, I think it will be more helpful for me.
Okay, so this is seen in all seasons, this particular.
Yeah, it is very common.
Okay, so so this is the first part of your PhD thesis. So what are the further plans?
Next step, the surface modification of the cellulose nanocrystal. Then I try to make a composite with the polylactic acid, and I think it can be used for the packaging applications.
Okay.
Thank you, sir. Let me invite our next speaker, Rajiv MR, code number AMI03.
Good morning to one and all. Myself, Rajiv Amar, doing PhD under the guidance of Professor Dr. T.S. Anjuthan, Emeritus Professor, Department of Chemistry, University of Kerala Kalivattam campus. With pleasure and honor, I would like to present a part of my research work entitled as Polyelectrolyte 3-layer nanoparticle of graphene oxide, polyethyleneamine, dextran sulfate as a multi-drug transdermal carrier for chemotherapy. These are the contents. First of all, we have to go through the introduction. We all know that cancer is one of the major threats to human life. And the abnormal and uncontrolled growth of cells is known as cancer. There are lots of methods to treat cancer, among which chemotherapy is the one of the leading method in which chemicals are used to treat cancer. There are lots of drugs are available to treat cancer, but the direct consumption of drug is not possible. As a result, the arising question is that why we need a drug delivery system. A drug delivery system can provide a targeted and a controlled delivery of drugs, and it can maintain the concentration of drug at the site of action and to increase bioavailability and avoid the death of normal cells, and it is easy to administer and safe and reliable. There are mainly three routes of administration. One is the oral, second one is the transdermal, and the third one is the intravenous. In this chapter, mainly focusing on the transdermal delivery of drugs. So we have to discuss the advantages of transdermal drug delivery system. Transdermal drug delivery systems not cause any pain and unwanted side effects, and it can be substituted for oral administration. Thereby we can avoid the first pass metabolism, and it can maintain the maintain the prolonged duration of action and reduce the frequency of action. A drug carrier can be synthesized in such a way that drug can be released from the carrier on the effect of some stimuli. These are the examples of stimuli. So we have to go through the main part. The objective of this work is to synthesize a polyelectrolyte 3-layer nanoparticle of graphene oxide, polyethylene imine, dextran sulfate for the transdermal delivery of doxorubicin and methotrexate. Then following are the characterization parts. These are the major materials used for the synthesis of nanomaterial. This is the scheme of the synthesis of final material. The material is characterized by stepwise modification is characterized by FTIR, XRD, and the size of the final material and the intermediates are analyzed by DLS analysis, and it was confirmed that the size of final material is in the nano range on 47.1 nanometer, and the surface morphology is confirmed by SEM analysis and AFM analysis. From AFM analysis, the surface roughness is also obtained, and the particle size is confirmed by TEM analysis, and the result obtained from TEM analysis is good agreement with the result obtained from DLS analysis, which is on 42 nanometer. And this stepwise modification is again confirmed by the zeta potential analysis, as this is synthesized by layer assembly. Zeta potential is an important factor. And the drug loading efficiency is also determined for the loading of doxorubicin on the surface of the folic acid conjugated graphene oxide. And the viscosity, pH, swelling index, and the moisture uptake of the final material is also determined, which gives positive result to act as the material for the transdermal carrier. And the cumulative drug release were conducted in basic pH and in acidic pH, and both the doxorubicin and methotrexate is released in the acidic pH. That means the tumor cell is in acidic in range. As a result, it's a good material for the delivery of doxorubicin and methotrexate. And for preclinical evaluation, I did hemocompatibility test. In this include hemolysis ratio, blood clotting index, and protein absorption assay. These three analysis gives a positive result for the material. And the cytotoxicity of the material is done by MTT assay in MCF7 breast cancer cells. The final material shows good toxicity towards cancer cells and non-toxicity towards a normal cell line L929, and it gives a good LC50 value. These are the morphological changes of MCF7 when the material is applied on it. The dark portion showing the dead cells, and we can see that the final material gives a good toxicity towards the MCF7 breast cancer cells. The cell toxicity is again confirmed by apoptosis assay. Here it is also confirmed that our material shows good toxic towards MCF7 breast cancer cells. The green cells showing the live cell, and red or yellow cells showing the dead cells. The figure D showing the image when the material is treated with the MCF7 breast cancer cells. There the existence of live cell is very low. That is good activity, good toxicity towards MCF7 breast cancer cells. As the material is to be used for transdermal application, we have to check the skin irritation test. The final material has a primary dermal irritation index is 0. That is, it is good for used as a transdermal carrier. And the in vivo pharmacokinetic studies of the material were done in visitor rats with the permission of animal ethical committee. And from this, we get the result that the transdermal application of the material has mean residence time twice than that of the oral administration. And the ex vivo skin permeation test is also conducted by the use of Franz diffusion cell, and the material itself shows good permeation because the graphene oxide and polyethylene itself act as a permeation enhancing agents. And the storage stability of the material is determined in normal room temperature and the freezer condition. In both conditions, material is good state, is highly stable in nature. The summary is that in this work, I successfully synthesized a 3-layer nanoparticle of graphene oxide, polyethylene imine, and dextran sulfate for the transdermal delivery of doxorubicin and methotrexate for cancer therapy. Acknowledgement. These are the reference. Thank you.
Rajiv, can you explain the nature of bonding on the graphene surface, graphene oxide surface?
In this study, graphite powder is used. Graphite powder is converted into graphene oxide by modified Hammer's method. Then folic acid is grafted on the graphene oxide by EDC NHS coupling. Then the surface of the folic acid conjugated graphene oxide, doxorubicin is loaded by pi stacking and the electrostatic force of attraction. On the surface of the doxorubicin loaded graphene oxide is negatively charged. As a result, the positively charged polyethylene imine is coated on the surface of this material. And finally, methotrexate loaded MTX loaded dextran sulfate is coated on the surface of polyethylene imine.
That means the initial binding is ionic in nature.
What's that?
Ionic in nature.
Ionic.
Then how the drug molecule can deliver at the active site? It is the change in pH or thermal effect?
Both the doxorubicin and methotrexate is released at the acidic pH. It is determined from release studies.
You studied
Yeah.
in vitro pH.
In vitro and the cell toxicity also confirmed the releasing of material in the acidic pH. We done in MCF7. Material alone and drug loaded material is done in MCF7 cancer cells. As it is released, if the dual drug loaded material shows good toxicity towards MCF7, that means that drug is released into that medium. That MCF7 breast cancer cell is in acidic nature, that is why both the drugs, doxorubicin and methotrexate is released into that medium.
Then regarding the cytotoxicity, you have how many cells you have studied? Cell lines. How many cell lines?
Only MCF7 breast cancer cell.
Okay.
And the normal cell is
My question is whether the normal cells
normal
are,
cells. L929 is also checked.
whether the drug is toxic towards normal cells.
Toxicity is there is no toxicity. The live cell is above 80%, 82%.
In the case of normal cells.
Normal cells.
Okay.
Thank you, sir. The next speaker is Varsha Lisa John, court number AMI 04.
with receptors such as nanomaterials. Due to its tunable biodegradability, ease of processing, presence of functional groups, and controllable conformation transitions. So here goes literature. From the literature, we get to know that there are various nanomaterials which have been fed to silkworms by the direct feeding method, like by modifying their feed, which is the mulberry leaves itself, and we got augmented. They have obtained augmented silk fibers. So in that context, I intended to synthesize carbon dots from Morus rubra variant of mulberry leaves, which is the feed of silkworms itself, and synthesize carbon dots from it and modify the feed of silkworms, and let's see how that turns out. So this is known to us that the moth undergoes various stages to form cocoon, and by then we get silk fibers. So here I would like to introduce the concept of instar, because these silkworms, they undergo molting process 4 times in its life cycle, which is divided into instars. So by the 4th instar, the silkworm have more of the feed, and that's how the life cycle goes. So here the gist of my work is like we modified the feed with MBCDs, and it was fed to silkworms, and we obtained cocoons, and we could extract augmented silk fibers. So the feeding of silkworms started, like modified feed were given to the silkworms from the 3rd instar onwards. So various structural characterizations have been performed for the MBCDs, and MBCD is what we call the carbon dots, which are derived from Morus rubra variant of mulberry leaves, and we got average size of 4 carbon dots of average size of 4 nanometers with 0.22 nanometer of lattice fringes. Again, IR all structural characterizations provide the data that it consists of carbon, oxygen, and nitrogen in abundance. And here you have the fluorescence lifetime has been estimated around 4.68 nanoseconds. The optical characterization says that there exists pi to pi star and n to pi star transitions from the absorption peaks, and the photoluminescence is dependent on excitation wavelength, pH, and ionic strength. So this is all about the MBCDs, and we observed that these MBCDs are capable of detecting dopamine with an detection limit of 4.39 nanometers, even without adding any surface passivating agents or chemicals. So the selective detection of dopamine is due to the non-covalent interactions that exist between MBCDs and dopamine through the amine group, diol, and the phenyl groups. So the detection limit was 4.39 nanometers, and we could extract silk fibers. So we modified the silkworm feed and with MBCDs, and it was fed to silkworms, and we categorized these silkworms into 4 groups. Like one is the control group, where we did not give MBCDs at all, and with T1, T2, varying amounts of carbon dots were fed to these silkworms. So here goes the cocoon formation. So it's formed, the silkworms are forming the cocoons. So as we all know, silk fibers, they are natural protein filament from silk glands of Bombyx mori, and it has a triangular cross section, and 2 fibrons are held by a gummy sericin. So you have to remove the sericin content in order to avoid the toxicity. So they have silk fibers, they are characterized by H chain and L chain, where H chain consists of 12 hydrophobic and 11 hydrophilic units, so which are connected by disulfide bonds. So the silk fibers, they exist in 2 conformations, like silk 1 and silk 2. Here, from the structural characterizations, we understood that there are the silk fibers obtained from the control group, they are quite rough, and we can see that there exists, the white patches confirms that there exists agglomerated nanomaterials within these structures. And in order to understand what happens within the fibers, we took a FASEM analysis in the cross section, and we found that in T3, which in which we have like incorporated more number of carbon dots, we could see like these carbon dots incorporated, and from control it was not so visible. So we could identify that MBCDs have been successfully incorporated into the fibers. The FTI and XRD spectra like gives us the data that it consists of most of like there's a conformational transition from the alpha helical structures to the beta sheets. So that it again the Raman spectra also confirms that there exist there exist beta sheet structures. In order to confirm whether the beta sheet structures contribute to the crystallinity of the material, we took the water contact angle and more of hydrophobic content. Like if the water contact angle is more than 90 degrees, then we get it is hydrophobic. So hydrophobicity has been increased. So this is so this confirms that there is a conformational transition from alpha helix to beta sheet structures. The mechanical testing also proved that like there is an enhancement of mechanical properties like tensile strength and toughness. This is also confirmation for the existence of beta sheets. Again, in the control, in the optical characterizations, we found that there is a cross-linking capability. So silk fibers are intrinsically fluorescent, and when we incorporated MBCDs, the fluorescence have diminished, but it is still fluorescent from the solid state fluorescence. So we knew that MBCDs could detect like dopamine. So we found we had to think what these MBCD incorporated silk fibers, how they behave with dopamine, and we could find out there is a ratiometric dependence of ratiometric fluorescence quenching response to dopamine addition. So by now, like the direct by conclusion, we say the direct feeding method was apt to synthesize functionalized silk fibers, and MBCDs were prone to detect dopamine, and incorporating MBCDs that enhance the beta conversion, conformational transition from alpha helix to beta sheets, and MBCD it could detect dopamine. Those silk fibers which are incorporated with MBCDs could determine dopamine. So with this I conclude my presentation.
So your final application is this detection of dopamine.
With silk fibers.
Silk fibers, okay. So is it a first of
Yes.
kind of its work reported?
Yes, ma'am.
Okay, so it's already patented?
It's not patented, we have given for publication. We have other applications with the same food packaging applications with the same material, so we are going for a patent for that.
You have described that the quality of the fiber can be improved.
Yes, we can.
Then what about the quantity of the?
There exists batch to batch and lab to lab inconsistencies when you compare the synthesis methods. But this is also one type of, we do electrospinning and we get one kind of fibers, or we can synthesize fibers. So here, this is also a type where we feed silkworms to synthesize that type. So there was no change in the quantity of silk fibers that we got from the control group or the silk fiber or the MBCD incorporated feed. So we did not, there wasn't any change from the groups of silkworms which fed on MBCDs or the normal feed. So I think, did I answer your question? What was that?
Okay, normally how many grams or milligrams of fiber can be obtained from a single cocoon?
That depends. We did not check the quantity wise, we did not check, but we could, so we obtained same.
I am talking about the life of this species.
Species as in
Lifespan
lifespan of
after
silk.
incorporating these carbon rods.
You mean the
Whether,
silkworms?
silkworms.
It is a sacrificial organism. It converts into a cocoon. We extract silk fibers from cocoon, so it is almost the same, sir. We feed it from the third instar onwards, so it's more. We find that it was more healthy, than the control group.
Not affecting the health of the.
Not affecting. We have done the gut analysis also. That is we get to the for the next presentation. So like presentation as in we are publishing it in a different journal. This work is already reviewed and
Okay.
Thank you, ma'am. Now I invite Akash Chandran, code number ANM01 for the presentation.
Good morning all. My name is Akash Chandran, Research Scholar of the Department of Nanoscience and Nanotechnology, University of Kerala. I welcome all of you to my presentation entitled Tamoxifen Encapsulated 2D Covalent Organic Framework Nano Device for Efficient Drug Delivery and Cancer Therapeutics, which is done under the guidance of Dr. Jenish P.A., Director of Center for Advanced Cancer Research. The outline of my presentation are introduction, objectives, methodology, results, and discussion applications. Moving to the introduction, breast cancer is one of the deadliest malignancies among women worldwide, and the conventional therapeutics, including chemotherapy, radiotherapy, surgeries, are not efficient still. So it is necessary to improve the treatment therapy by advancing the material for therapeutics. So nanomaterial based therapeutics are emerged to get the efficiency in treatment of breast cancer therapy. And among these nanomaterials, porous nanomaterials, which is a class of crystalline porous material ingeniously formed by covalent strong linkages, that is covalent organic frameworks. They possess advantages of structural diversity, low density and high thermal stability and permanent porosity, which endow them to potential applications in drug delivery and catalysis, separation, sensing, further energy applications. Hence, COF can be included as a material in our society. The objectives of my presentation are synthesis a novel covalent organic framework material via an amide linkage and characterize the material using various analytical tools. Then the modification and characterization of the synthesized COF material by tamoxifen, and then check the efficiency of the drug delivery device in MCO7 cells. Then methodology. This is the schematic representation of the methodology adopted, and this is solver-thermal synthesis I have adopted, and the acid and the amine is condensed to form the amide linkage covalent organic framework. The characterization techniques used to identify the structure are this, and the application studies are this. Then moving to result and discussion, the physical properties of the material is it's a pale yellow colored compound having molecular formula C27H20N4O6. And then moving to the X-ray diffraction studies, this is X-ray diffraction pattern of the synthesized drug delivery device, and the highly intense peak indicates that the material is highly crystalline. The peak below 10 degree indicates that it's porous. And the FTR spectrum of the drug delivery device and the tamoxifen modified drug delivery device is shown here, and all the characteristic peaks are present in the tamoxifen modified material without affecting the crystalline structure. This is the UV-DRS spectroscopy analysis, and it is found that material having absorption in the maximum UV region and have an absorption in the visible region of 450 nanometer. Then scanning electron microscopy images of the drug delivery device before loading drug, and has a porous crystalline framework structure. After loading the drug, almost all porous structure have filled with the drug molecules. Then this is the C13 NMR spectroscopy of the drug delivery device synthesized, and all the peaks corresponds to CH2, CH, CO amide and carbonate are present. This is solid state NMR spectroscopy. Then CHNS analysis is found to identify the elemental composition, and it is found that a 65.5% carbon and 11.66% nitrogen and 5.4% hydrogen present, and trace of sulfurs are present. And then among this characterization possible structure is optimized. Then TGA analysis is used to identify the thermal properties, and it has found that up to 700 degrees Celsius, 30% of the sample remains, and it shows that it is stable up to higher temperatures. This BET surface area analysis is used to identify the porosity and surface area of the material, and the pore diameter is found to be 3 nanometers. And moving to the application studies, the in vitro drug release of tamoxifen, and which is done in both 7.4 and 5.4 pH, which is acidic pH. And it is observed that more drug is released in the acidic pH than the biological pH. Then the cytotoxicity analysis was done in both L929 fibroblast normal cells and in MCF cell lines, and it is found that COF and tamoxifen alone, COF-tamoxifen composite has no cytotoxicity in L929 fibroblast cells. After checking the cytotoxicity in L929, we have done this cytotoxicity in NCF cell lines. Then it is found that almost 80% of the cells were dead after the incubation of 24 hours of COF-tamoxifen. Then the scratches, it is used to check the proliferation of the cancer cells, and the COF-tamoxifen after 48 hours it inhibited the proliferation of MCF cell lines. This AO-ETBR staining assay is found to identify the live dead cells, and this is the merged images of tamoxifen and the COF-tamoxifen. So it is found that COF-tamoxifen kills almost all the breast cancer cells. In conclusion, a novel crystalline covalent organic framework material has been synthesized by amide linkage and characterized using various techniques, and synthesized COF material modified with the tamoxifen and characterized, and check the cytotoxicity of the material in L929 fibroblast cells and MCF cell human breast cancer cells. Then check the in vitro drug release profile in both acidic and normal pH, and wound healing assay or scratch assay is done, and AO-ETBR staining assays were done to check the apoptosis in MCF cell human breast cancer cells. These are the acknowledgements. My supervising teacher Dr. Danish P.A. and my lab mates Sudhina, Abhirami and Mahesh Chandra, and technical support Cliff, Kerala University and MG University. Thank you.
Akash, you have taken the term analysis.
Yes, sir. It's
What is the pore size and pore size of your material?
the course is 3 nanometer.
And pore volume?
Pore volume is going pore volume is 0.02.
How you have measured the pore volume?
We have done BJT.
Which method?
Desorption isotherm.
In which method?
Actually, we done this. They have calculated and sent to me.
Outsourced.
Oh,
Okay. And in the thermoanalysis, can you explain the weight loss?
what's that? Sorry.
Can you explain the
It's
percentage weight loss?
Two-stage decomposition.
Yes.
And, the first is the removal of any water molecule present in it, or the purification. Water was used to purify the material after synthesizing. Then the price that will
From
be
200 to 300
200
degree. What is the
that may be due to the carbonate or CO, CO2, escaping of CO2 or CO.
then 400 to 500
That I have not checked the degradation.
or complete decomposition? Oh. No questions from audience.
Well, I want to ask you. So you synthesize covalent bond organic frameworks, right, with the amide linkage. But there are many formal works on the such COF containing amide structure. But what is the unique point in the structure of your material? So maybe covalent bond organic frameworks has studied the containing amide structure has already studied. What is the unique point in the structure of your material? Chemical structure. Chemical structure.
It's a 2D organic framework material, and having amine functionalities is used to loading the drugs in it.
So which I couldn't see well. So what is the material serving the amide? Amine. Well, which amine did you use?
Diaminodiphenyl methane.
Diaminodiphenyl. Oh. So this is the reactant.
These are the 2,6-pyridine dicarboxylic acid and diaminodiphenyl methane. First acid is converted to acid chloride and then to amine.
I see. So this may form the linear structure.
Linear, two-dimensional structure, porous structure. That these NH can also form another framework.
This amide can chemically react
Yes.
to with something.
So another
Imide structure can be formed. So what kind of the reaction will the amide make?
amide.
So this is amide, right, already?
This NH is used to load the drug molecules.
Oh. Okay, thank you.
Thank you.
Thank you, sir. Now I invite Elsa George, court number ANM 02 for the talk.
Welcome to all. Welcome to my presentation. My work entitled as polymeric carbon nitride based ABS nanocomposites for better mechanical and frictional performance. What are composites? Composites are multi-phase material with different chemical structure and physical properties. It contains mainly two phases,
matrix and filler. The properties of these composites can be custom tailored according to our requirements. The nanocomposites are high performance composites where one of the faces should have nanoscale dimension that get dispersed in the matrix space. These properties of these matrices can be enhanced by adding nanoscale fillers. In our work, we used polyacrylonitrile butadiene styrene, abbreviated as ABS, used as the matrix space. Then polymeric carbon nitride as our nanofiller. It is a polymeric material of carbon and nitrogen having a layered graphite-like structure, which was discovered in 1834. This polymeric carbon nitride is a better reinforcement material choice in polymer composites because of its low cost, robust and metal-free nature. The application of this particular material as a reinforcing material in polymer matrix is a growing area and it is in its initial phase. Only a few reports are available on polymeric carbon nitride in polymer matrix composite systems. But the bio-inspired surface modification on this material using polydopamine is a convenient and very simple way to modify the material. This modified material in composite structures can broadly impact many properties like tribology, thermal stability, thermal conductivity, etc. Our objectives: we choose two nanofillers, NBCN, that is nano sheets of polymeric carbon nitride, and polydopamine modified nano sheets of polymeric carbon nitride as our two nanofillers, which get dispersed in ABS matrix. After the fabrication of the composites, we studied its frictional and tensile properties. First, we prepared nano sheets of polymeric carbon nitride from melamine, the precursor, through pyrolysis. Initially, bulk polymeric carbon nitride was synthesized, which was thermally etched to give nano sheets. The formation of nano sheets were confirmed by various spectroscopic analysis like FTIR, XRD, SEM and elementary analysis. All these observations were well agreement with the literature results. Then we modified these NBCN using polydopamine and we got a grey powder which is PDA NBCN. Again the modification was confirmed by similar spectroscopic analysis such as FTIR, XRD, scanning electron microscopy, EDS and elementary analysis. All these observations point to the successful introduction of dopamine on NBCN. After the successful preparation of NBCN and PDA NBCN, we fabricated its ABS nanocomposites with varying weight percentage 0.5, 1, 3 and 5 using simple solution casting method which was followed by compression molding. After the fabrication of the two sets of nanocomposites, that is ABS NBCN and ABS PDA NBCN nanocomposite systems, we studied its friction behavior on a pin-on-disc arrangement using three different loads, 5 Newton, 10 Newton and 15 Newton. This is the frictional behavior nature of ABS NBCN nanocomposites under 5, 10 and 15. The black one shows the COF, coefficient of friction, for the ABS polymer, which is the highest value, and the red pattern shows the COF of ABS NBCN 0.5, that means lowest concentration of the filler, which also has the lowest COF. Further addition of the filler increases the COF value. However, in all the cases the COF is lower than that of the ABS polymer. This is the COF for the ABS NBCN 0.5 system under 5, 10 and 15 loads, and this is the average COF of all the systems under the different conditions. This is the frictional behavior of ABS PDA NBCN nanocomposite, that is a modified version. Here also similar pattern was obtained for the frictional behavior. The ABS has the highest COF value. The 0.5 concentration of PDA NBCN has the lowest COF value. Further addition of the PDA NBCN increases the COF value. However, here also the COF value is lower than that of the COF value for the nanocomposites are lower than that of the neat polymer. This is the COF for PDA NBCN, ABS 0.5 concentration, and this is the average COF of the system. When we compare the average for COF for the system NBCN and B is the system PDA NBCN, we can clearly see that the COF for PDA NBCN is lower. In the case of COF, the COF for the PDA NBCN is lower than that of NBCN, corresponding to this concentration and the load, which means that the modification enhances the lubricity of the ABS polymer. This is the tensile properties of ABS, NBC and nanocomposites. When we compare all the thermal tensile parameters, we can see that the lowest concentration provides the better thermal stability, tensile stability. And for ABS, PDA, NBCN, here also the 0.5 concentration provides better tensile stability. When we compare the overall properties, friction study and tensile property study for ABS, NBCN and ABS, PDA, NBCN system, the 0.5 gives the better results. Furthermore, the ABS, PDA, NBCN shows better results than ABS, NBCN. That means modification definitely improves the property of the polymer. Conclusion: the spectroscopic analysis confirmed the synthesis of NBCN and PDA modification. Very small amount of the filler is beneficial in order to reduce the COF and increases the lubricity of the polymer. In NBCN, the COF reduction is 35%, whereas in PDA NBCN it was improved to 51% reduction. Then tensile strength was increased to 10% in NBCN, which increased to 29% in PDA NBCN. And also the tensile strength and frictional property is 3 times and 1.4 times than NBCN in case of PDA NBCN. Thus, the developed ABS nanocomposites offers promising application in harsh conditions. I like to thank my family, my supervisor Dr. Anas and NTAC-2023 for the opportunity. Thank you.
How you compared the properties with the similar work report in the literature?
Which one? Tribology. Yeah.
Then whether your composite is better?
Yeah.
In how many percentage?
Calculate the percentage. It will depend on the parent polymer.
Why how you taken melamine?
Because we can use any CN containing material as our precursor, but at the end intermediate is always melamine. So if we take melamine as our precursor, it will be easy for the synthesis.
Then urea is a very common precursor.
Even though urea, if we take urea as our precursor, melamine will be the intermediate. So finally we will get the polymeric carbon nitride. So we can select melamine as our precursor.
Okay. And questions from audience?
So can you explain why the 5% added one is showing the better mechanical property than the 10%? So not monotonous improvement, but just at the 5% better than 10% or 20%.
This one,
Tensile strength or frictional property shows a better property than the 10.
NPCN shows 10% increase in tensile property, and PDA NPCN shows 29% improvement in tensile properties.
I see.
Two systems. 10% for NPCN and 29% for modified NPCN. So modification definitely enhances the tensile property of the system.
So, but by increasing the additive percentage of the additive, not monotonously improved.
The increases. Only the lowest concentration provides better.
So why? So
why? It may be due to the agglomeration of the nanoparticles.
aggregation.
It will restrict the interfacial bond between the matrix and the filler. That will restrict the property of the polymer.
Okay, so for some property, so 5% shows the best property. Then don't you test at lower percentage, like 3%, 2%?
No, actually we are optimizing the percentage. Here in this case, in case of polymeric carbon nitride, 0.5% gives the better result.
0.5%.
0.5%. And further addition of the
Okay, okay, 0.5, but so how about lower than 0.5?
Lower than we will check lower.
So you may see the valley, so at a much lower concentration region.
We can check between 0 to 0.5.
Yeah.
We can check. Thank you.
Thank you, ma'am. Next, we have the last presentation of morning fission. Now I invite Fatima Fafna, PH, code number ANM03.
Good morning, everyone. My name is Fatima Fasna PH. I'm a full-time research scholar of Maharajas College, Ernakulam, under the guidance of Dr. Srisha Shashi. And today, I'm going to present synthesis, characterization, and drug loading studies of nano-sized IRMF or MO5. First of all, metal organic framework, which is usually abbreviated to MOF or MOF, is a coordination polymer or a coordination network having an open framework structure containing large number of potential voids. And they can also be described as self-assembled metal clusters with organic ligands having unique properties like their structure, permanent porosity, tunable properties, which makes them suitable for various applications. And talking about the basic structure of an MOF usually have two parts, an organic part and an inorganic part. The organic part can be the organic linker, and the inorganic part can be a metal ion or the cluster of metal ions. And both of it will club together to form the basic framework structure of MO5. And talking about the MO5 or IRMOF1, it is a three-dimensional framework structure composed of tertiary acid as the organic part and ZN4O metal clusters as the inorganic part, and has an open skeletal structure and controllable pole structure, high pore surface area, high thermal stability, which makes them suitable for applications like gas storage and separation, electrochemistry, catalysis, medicine, etc. And the present study I have synthesized a nano-sized MO5 using a room temperature fast precipitation method, and it is used for the study of drug loading. And this is the scheme of synthesis of my nano-sized MO5. And the precursors are zinc nitrate and benzene dicarboxylic acid, and triethylamine, a strong base, is used for the room temperature fast precipitation of MO5. And the MO5 thus precipitated is submitted to a series of purification processes including washing, solvent exchange, filtration, vacuum drying, etc. to obtain the final powdery nano MO5 material. And solvent adsorption method was used for the drug loading purpose, and all the experiments were carried out in water. And the three factors including weight ratio of MO5 to MB, drug loading time, drug concentration, etc. were selected to determine the optimum condition for the maximum encapsulation of the drug. And drug loading capacity was determined using the equation weight of drug in nanoparticle divided by weight of nanoparticle into 100. And the concentration of methylene blue in the solution was determined using the calibration curve method using a UV visible spectroscopy. And moving on to the resultant discussion section. First one is a surface analysis using SEM and TEM, and the second one is a TEM image of nano MO5. And from the TEM image, it is very clear that the MO5 nanoparticles lies under 200 nanometer range, and the average particle size is calculated to be approximately 120 nanometer. And from the UV visible spectroscopic analysis, the drug loaded MO5 has a adsorption peak around 664 nanometers, same as the drug methylene blue, which confirms the successful loading of drug into the MO5 framework. And the left side we can see the on the right side we can see the IR spectra. In the FTIR spectra we can see the FTIR spectra of the drug methylene blue and the drug loaded MO5 has three similar peaks at 1391, 1358 and 1338 centimeter inverse. And similarly, MO5 and a drug encapsulated MO5 has a similar peak at 1500 centimeter inverse, which also confirms the successful combination encapsulation of the drug. This is a thermal analysis using thermogravimetry, and from the TGA curve of MO5, you can see that MO5 is thermally stable up to a temperature of around 450 degrees Celsius, while the drug incorporated MO5 is thermally stable up to a temperature of around 500 degrees Celsius. And this might be due to the encapsulation of methylene blue, which has a higher thermal stability of around 600 degrees Celsius. And this is a surface area analysis using BET. First figure is absorption desorption isotherm of MO5, and from the BET analysis, the surface area of MO5 is around 425.84 meters square per gram, and the pore volume is around 0.56 cc per gram. On the other hand, the surface area of drug incorporated MO5 is around 24.988 meters square per gram, and pore volume is 0.058 cc per gram. And this significant decrease in surface area and pore volume might be due to the encapsulation or addition of this drug into the cavities of MO5. And this is the DLS analysis. And the figure A is the size distribution of MO5 and NB loaded MO5. And from the DLS analysis, the average particle diameter of both substances are found to be around 750 nanometer. And this is way higher than the size of the particle that we have calculated from the TEM analysis. And this hike might be due to the particle diameter that we have calculated in DLS is known as hydrodynamic diameter, which is the diameter of a particle in a solution, where we taken into account different phenomena like solvation and all. So it will be usually higher than the diameter of a particle in the dry state. And we also have the zeta potential calculation, and the higher negative value of zeta potential of MO5 and drug encapsulated MO5 shows that they are highly stable. And next we have a drug loading capacity for different concentration of methylene blue. We can see that as we increase the concentration of methylene blue, the drug loading percentage is also increases, and we got a maximum value at 0.5 milligram per ml of methylene blue. And we have a drug loading capacity for different ratios of MO5 to MP, and the higher drug loading capacity was obtained for the ratio 1:2, 1 MO5 and 2 methylene blue. And finally, the drug loading capacity for different loading time is also studied, and the maximum drug loading capacity was obtained for around 24 hours. And if we again increase the loading time, there is no significant increase in drug loading is obtained. So that's all about my work. Thank you.
So is it your PhD work?
It's a small part of my work.
PhD work.
Yes.
So what are the further applications that you are planning to?
Actually, methylene blue is a less exploited drug. Actually, it has many applications. Like, it is a very good drug in a disease called methemoglobinemia, and also it is a very good photosensitizer that we can apply in most modern treatments like photodynamic therapy or photothermal therapy at all. So as the next step, I wish to study the photodynamic or photothermal applications of this composite.
And say first report of this MB.
No, methylene blue incorporated MO5 is the first report.
First report. Okay.
Is methylene blue a drug, or is it sensitized activation of the drug?
Methylene blue itself is a drug.
For what?
It is a active drug for a disease called methemoglobinemia, a condition where blood have more than enough hemoglobin. So in that condition, this methylene blue can reduce the ferric ion in the hemoglobin to ferrous ion, thereby decreasing the concentration of hemoglobin. And also it can also be used as, or it has been used as photosensitizers where when we apply a particular wavelength of light, it can produce a singlet oxygen and kill the cancer cells or bacterial cells and all.
I understand. That's oxygen.
Yes, yes.
Activating oxygen.
Yes, that's it. So it can be used in the both ways.
Whether you have reports, of course, you might just study it because
Yes.
whether you have seen
Okay.
a report,
Mm.
whether methylene blue is considered for acting as a drug.
Okay.
Methylene blue
Itself. Okay.
Not,
The
not the
composite, not the composite, but methylene blue itself. The problem is when we use methylene blue itself, in the body condition, it will easily get reduced to.
I understand. So, but do you have any literature where it is reported that this methylene blue is used for something as a drug?
Yes, in the hemoglobinema like that.
That's not
Yeah.
relevant.
Okay. Thank you. Thank you.
Thank you, ma'am. We have one more presentation in the fission. I invite Fakria Matthew, code number ANM05.
Good morning to all. My name is Zakaria PM, part-time research scholar in SB College Chennai under guidance of Sam John. I am presently working as assistant professor in Government College, Kottayam. My topic is synthesis and characterization of chitosan bornite composite. First step is the preparation synthesis of nanocomposite of chitosan bornite. Chitosan 2% weight by volume of chitosan is dispersed in 2% volume by volume of aqueous acetic acid at 50 degrees Celsius for 1 hour. Chitosan is insoluble in water. It is a purely basic in nature. So the function of this acetic acid is to convert this as a salt. So it will get only a salt. It is not purely soluble in any solvent. Only a salt. Then after the dispersion, then the required percentage of bornite is added. Then it is dispersed with the magnesium is dispersed for 2 hours. Then we will get a gel. So this method is gel salt technique. So again, the free acetic acid is washed out with the pure distilled water. We know that this chitosan is basic in nature and acetic acid is also acidic, but we get a salt. It is a salt of weak base and weak acid, so it is acidic in nature. The Ka of acetic acid is slightly higher than that of the glucosamine, that is chitosan. It is a polymer. So it can be represented like this. Chitosan is a salt, then required percent of bornite added, dispersed, then we get a composite. Then its characterization. It is mainly characterized with the FTIR. The first peak at 3353 is due to the OH setting of this chitosan. This red line denotes the chitosan bonded composite and the black denotes the chitosan. Then green represents bornite. The first peak at 356 is due to the OH setting of this OH bond, and then second one at 2925 due to CH stretching. Then comes to a peak at 1738, that is HOH stretching of water present the chitosan. Then at 1657 is due to the amide carbonate stretching frequency of this chitosan. It is acetylated chitosan. Then next one is at the 1374 is the NH bending peak. Next one is at the 1277 is the CH bending. Then next one is at the 1155 is due to the COO stretching of the gases of chitosan. Then next one, last one is at the 1057 is due to the CO skeletal stretching of gases of polysaccharides. Then Bornite shows a 2 peak at the 1360 is due to the BN stretching, in-plane BN stretching of Bornite, and next one, the 763 is due to out-of-plane bending of the Bornite. Then all these peaks are appeared in this composite. So again, one thing is clear that if the peak of this Bornite is shifted from one of these peak is shifted from 763 to 523. The out-of-plane bending is shifted. The reason for that, with the exact picture of this Bornite is, it is a hexagonal nature, planar hexagonal nature, and the boron is in having partial positive delta positive charge, and nitrogen is in partial delta negative charge. So nitrogen is more electronegative. So it is a refractive material, Bornite refractive material, and it is a non-conductor. So it takes us delta positive for the boron and delta negative for the nitrogen atom. That is also, it is non-conductor and it is fixed. It is a non-conductor. Then when it is dispersed in chitosan matrix, this layer is slide from one layer to other. The exact position of the boron is exactly above the nitrogen. The boron lies exactly between the two layers of nitrogen atoms. That is the reason why it has a high stretching frequency, out-of-plane stretching frequency at the 763. When it is dispersed in chitosan matrix, so the stretching frequency is shifted to 763 to 523. That is, the plane is slide over one layer to another layer. Then again it is characterized as XRD spectrum. So chitosan gives a characteristic peak at 2 theta is plotted, intensity is plotted against 2 theta. It gives a characteristic peak at 20.7, 2 theta at 20.7. When it is dispersed in chitosan, when it is dispersed in Bornite, it is mixed with the Bornite, then the peak is shifted to, the chitosan peak is shifted to 19.7, this one. This clearly indicates that by Bragg's equation n lambda is equal to 2d sin theta, it clearly indicates that the interplanar distance between the chitosan is increased due to the dispersion of this Bornite. And the Bornite gives characteristic at 20.6 and 42. There is no characteristic change in the spectrum. Chitosan's Bornite peaks, there is no change in the spectrum. Again, it is further characterized with the TG. The thermal studies, the thermogrammetry analysis, the TG shows that in the case of this chitosan, the weight loss up to 100 degree is due to removal of moisture. Then the next weight loss, that is from 100 to 210, is due to the complete dehydration and removal of low molecular weight species. And the final weight loss from 210 to 390 Kelvin, it is the complete degradation of this chitosan unit, the complete degradation of chitosan unit to its oxides. Then there is no change. It is the TGA thermogram of 4% composite containing 4% boronite. There is no change in the shape. That indicates that there is no chemical reaction. There is no chemical reaction between chitosan and boronite. There is no change in the pattern. So this indicates that the thermal stability of the composite increases by the addition of this boronite. Again, the thermal stability increases by increasing the percentage of boronite. So boronite is a protective material. That is the reason why the thermal stability increases. Then this application of this composite, it can be used as a corrosion inhibitor, and it is used for the corrosion inhibition studies of steel in acidic medium. And this paper is communicated to the Elsevier journal Corrosion Science, and they accepted, and waiting for that publication. That's all.
What is the maximum percentage of or amount of boron nitrate you have used?
That is 4%. On increasing the amount of boron percent, this admitting capacity, it is used as the corrosion inhibitor. Admission capacity decreases on metal surface. That is the reason why it uses, and it gives an efficiency of about 94% efficiency. Corrosion inhibitor is 94%, 4% boron nitrate gives.
Maximum 4% is enough. And in the IR spectra, you have mentioned that the layering of boron nitrate changes from the peak shifter, shifting the peak from 700 to something to 500. But in the XRD, you mentioned that there is no change in the
slight change in the slight minor change.
Okay. Whereas chitosan layer is shifted in XRD.
Chitosan shows sharpen and boron nitrate slight change in the spectrum. Exactly pattern.
But IR major shifting. Major shift is there.
Yeah.
Okay.
So there are so many reports of this chitosan composites. So how will you prove that this work is unique in nature?
The main function of this work is to create a synthesize a corrosion inhibitor. That one of the paper already reported this synthesis of this chitosan boron nitrate composite through a heterogeneous catalysis by the use of copper glycinate complex. But I tried that method, but I cannot prepare. I then adopt this method.
So the application is this corrosion inhibition.
Corrosion inhibition studies.
Is there any questions from audience? Okay, sir, thank you.
Thank you, sir. And that was an end to this session. Thank you, judges. I would like to remind you that the next session of oral presentations will begin at 1:30 p.m. in the Nobel Laureate Hall. Thank you.
See what happens. Let's first figure this one out. I know the problem. Where is the numbers?
All are requested to be seated at the venue. The next session will begin soon. Today, we all are witnessing yet another milestone event, and it's a great privilege for me to be a part of this. We are honored to have such an amazing panel of delegates here. I take this opportunity to welcome all the delegates and other guests wholeheartedly to the second day of 21st Professor K.V. Thomas Endowment Seminar and 4th International Symposium on New Trends in Applied Chemistry 2023, organized by the Department of Chemistry, Sacred Heart College, Tevara. Let's begin today's sessions with the 4th plenary lecture, which will be delivered by Professor Dr. Yitzhak Tor on the topic Fluorescent Nucleosides, Nucleotides and Oligonucleotide. The session will be chaired by Professor Dr. N. Manoj of Cochin University of Science and Technology. It's my pleasure to introduce him to the gathering. Dr. N. Manoj joined CUSAT as reader in 2006, and he is currently a professor at the Department of Applied Chemistry and the University Coordinator of research scheme of MHRD at CUSAT. His research interests include photophysics and photochemistry, steady state and time-resolved absorption and emission spectroscopy, electron transfer reactions, solar energy harvesting, and organic synthesis. He has published over 30 articles in international journals and a total of 47 conference publications. He served as a principal investigator of research projects funded by UGC, ICMR, and DST. He has been chosen as a resource person and member of board of selection of candidates for International Chemistry Olympiad from HBCSE, Government of India in the year 2019. I cordially welcome you, sir, to chair the session.
Good morning, all. Indeed, I am privileged to introduce Professor Yitzhak Tor, who is a highly cited organic chemist who works in the interface of chemistry and biology, who had his early education from Israel with a lot of scholarships, and he has received a lot of awards during his PhD period. He has received John F. Kennedy Prize for Distinguished Graduate Studies and Gerard F. Schmidt Prize for a Distinguished PhD thesis. And he has served as editor to various journals and currently is the editor-in-chief of Organic Chemistry Insights. And he is currently the George W. and Carol A. Latimer Professor of Chemistry at the University of California, San Diego. His current research areas include biomolecule ligand interactions like RNA, nucleic acid, and ligand interactions. He has focus on antiviral and antibacterial reagents and cell-selective targeting of molecules. He's a highly cited chemist with about 172 publications. And Professor Yitzhak Tor, he will be delivering a lecture on fluorescent nucleosides, nucleotides, and oligonucleotides. Over to you, sir.
Thank you very much. Well, we're going to try and figure it out because obviously that's not working very well here, but I'll try and maybe point with my hands. If you have a long stick anywhere, just bring it over. I'll use it as a pointer. So, because I cannot manage all of this thing here, what's going on here. Anyway, so I'd like to thank the organizers for inviting me and giving me the opportunity to experience coaching as well as tell you a little bit about our work. I thought I'd start very quickly with what we've been doing, and I really don't know what's going on here, but okay. We started 30-some years ago by looking at RNA ligand interactions. We then, out of that, emerged a few other projects that are more occupying us right now. One of the interesting aspects of working on aminoglycosides as RNA binders in the early days led us to guanidinoglycosides that are very intriguing cellular delivery agents, a project that is not really active in the lab now because there's a company exploiting that. Takeda has been stepping in recently with some interest, and I don't know what's going on. But my talk is going to be on how we're not going to be able to give a lecture because of some technical issues. This adapter and this computer has been all over the world in hundreds of presentations, but somehow it doesn't like this particular place. So no, that's not going to work. You have another adapter to try? Okay. I'll try whatever you want me to try. Because that's how they test you in terms of, yeah, but that's not compatible because now I cannot see anything. Yeah, there's nothing on the screen here now. It's like it's not a PC. It doesn't like. I can't look. There's nothing here. Okay. I've been in this business 30-some years. It's not my first lecture, and I've been seeing a lot of people trying to mess up with my computer, and I let them. Although they think that they do know what's going on, but they don't, because on the screen here you see nothing. So, but I'm a guest, so I'll step aside and let you guys mess up my computer. Sounds familiar, Ada?
Use slideshow.
I can use a mouse, I can use a dog, I can use a cat, but I mean, it doesn't. It's just that you cannot see when you plug in and. Okay, well, we'll see what happens here. We're starting from scratch again? Okay. So, do you want to plug in your thingy or not? Okay, doesn't matter. We're starting again. Rewind. Anyway, so I'm not going to repeat that, but out of this interest in small molecules that bind nucleic acids, particularly RNA, the need to develop better ways to understand those interactions led us to think about fluorescent nucleoside and nucleotides. And I'll tell you about that because fluorescence is an amazing tool when applied correctly, can really be highly illuminating, and that's obviously a pun intended. So I'm going to tell you a little bit about this project, and I'm going to start with an introduction for the students. If you're not familiar with fluorescence spectroscopy, I want everybody to be on the same page, just the basic terms. So here's a very primitive Jablonski diagram where we are all familiar with the fact that when we shine light with a certain energy, we excite the molecule from the ground state to the excited state. The molecule will then relax for a little while, and we obviously monitor that by taking an absorption spectrum. We record essentially intensity of a wavelength. The extinction coefficient for us, if you think about it, and this is what we call the lambda max of absorption, is essentially the probability for the molecule to absorb a photon of this particular energy. Now, when there are molecules that fulfill certain electronic features and excited state dynamic features, you may observe fluorescence, where this extra energy is going to be released as a photon, and then we record this red spectrum, which is an emission spectrum. And this particular energetic difference is called the Stokes shift. And it could vary, and it has a lot of information. Actually, it gives you a lot of information about the excited state. Now, when it comes to times, you need to recognize that electronic excitation is very rapid, 10 to the 15 to the minus 15 of a second. It will then spend about 10 to the minus 12 exploring. This is actually a landscape. It's not just those lines, where these molecules will sort of relax and arrive, hopefully, at an emissive state, as we call it. And this emissive state, for most organic fluorophores, lives about a nanosecond. Okay? So we recognize this excited state lifetime. A few nanoseconds, very common for organic fluorophores. We recognize the quantum yield how many photons you put in to how many photons you come out. You put in 100, you get it out 70, the quantum yield is 70%. A more rigorous definition is actually the division of the excited state lifetime by the native lifetime, or you can look kinetically at the division of the radiative process, a photon coming out, versus all the processes that the excited state can undergo. And for people with, I have a laser pointer, but it doesn't work with this. Well, it does. Okay, thank you. Thank you, Fatima. You saved the day. So for people who do imaging, brightness is very, very important. It's the multiplication of the extinction coefficient, how probable a photon be absorbed, multiplied by the quantum yield. That gives you a value that is sort of called brightness. And I don't need a very high volume. I don't need the screen. So I prefer that it's clear. Okay, jumping right into fluorescence of biomolecules, we learned all about central dogma yesterday, going from DNA to RNA to proteins, very different biopolymers, of course. Now, protein biochemists have had a terrific life, if you will, because they can rely on this wonderful fluorophore that is found in tryptophan, this indole molecule. It's a very typical organic fluorophore. Excitation at 280, emission at about 350, quantum yield about 10, 15%. Excited state lifetime, very, very common, few nanoseconds. Now, why am I telling you that, and why do we have all these approximation? Because tryptophan is a very, very responsive fluorophore. It tells us about its environment by changes in all these values. And people have exploited that for 60, 70 years. In fact, the early studies were done by Gregorio Weber in the late 50s, who, in my opinion, was a prophet, because in 1960, the year I was born, he stated, there are many ways in which the properties of the excited state can be utilized to study points of ignorance of the structure and function of proteins. And indeed, people have been exploiting that since then. And I'll give you a quick example very soon. But there's a huge difference between tryptophan and organic molecules that you might think look very similar. Look at this adenosine here, or adenine, the heterocycle here. It looks very much like this, right? 6 5-member ring fused, a few more nitrogens, who cares? Yet, nucleic acids, DNA, RNA, and their building blocks are completely dark. No emission whatsoever. You cannot use fluorescence spectroscopy, at least in normal labs, to learn about these very important biopolymers. And the reason for that is very, very intriguing. When you do spectroscopy on the building blocks of DNA and RNA, you find that they have absorption in very similar wavelengths like tryptophan, and their emission is in the UV, but you realize their quantum yield for emission is essentially 0. And that comes from the fact that their excited state lifetime is in the sub-picosecond domain. What does it mean? It's about 5,000 times shorter than tryptophan. It means that these molecules have a unique ability to lose this excitation energy and go back to the ground state very fast, very effectively. And this, of course, is really important when it comes to evolution. And we wrote a paper about it about 10 years ago, because when a molecule is in the excited state, even for nanoseconds, it can undergo chemistry, because excited states, when you unpair the electrons, they're much more reactive. Yet, these wonderful building blocks of DNA and RNA have a unique ability to lose this excitation energy, go back to their stable ground state. So we believe that this was an important selection pressure on the evolution of, or the chemical evolution of these building blocks. But now, if we want to do biophysics of nucleic acids, and we want to do what protein biochemists have done, for example, hundreds of papers a year are being published exploiting the fluorescence of tryptophan. And in fact, biophysicists engineer tryptophans into different sites, and since it's a responsive fluorophore, its emission features change upon the environment, you can actually learn about protein activity, folding, unfolding very easily using tryptophan. So this is a random example. I just Googled show me a protein with 1 tryptophan, and I found this particular RNase that has been mutated to include 1 tryptophan in different places, and people have done it extensively for many years. So can we take Weber's prophecy and change the word proteins and put here DNA and RNA? Can we make a singly labeled RNA or DNA with a responsive fluorophore that will behave like the native bases, shown here schematically? Let's say, can we mutate this G to a molecule that looks like G, but will, and function like G, but will have fluorescence that G doesn't have, and will allow me to do what protein biochemists have been doing for decades on nucleic acids. So that's the idea. So about 20 years ago, we started a program where we defined 3 major criteria. Isomorphicity, we wanted to make molecules that will look like the native bases. We want them to be probes, so obviously they had to have favorable photophysics. And we want them to be responsive, so they'll tell us about what the nucleic acids are doing. Now, there's an important philosophical point here. So here are the structures of the native bases again. And as an organic chemist, I can control isomorphicity. I can draw structure, I can make a molecule, I can make it look like the native bases. But I cannot design photophysics. The molecules do what nature tells them to do. And they'll be dependent on solvation and viscosity and a lot of different features. I cannot control the most important things for my work. I can make structures, but what the features would be, I'll have to experimentally evaluate. So I'm going to tell you a couple of stories. We started with very simple molecules. For synthetic reasons, let's see if you see something here. We replaced the hydrogen or methyl group on the U or T with a 5-membered ring. It was the first primitive motif that we made many years ago. We'll finish with motifs that are much more sophisticated chemically and more difficult to make, such as thiophenopyrimidines. I'm not going to talk about molecules that we've explored along the way, like quinazolines, although they were very interesting molecules, because if you start thinking about your physical organic chemistry, resonance forms, pushing electrons, you realize you can tune the electronics of these molecules and actually tune their photophysics. And here's a wonderful tunability. We were able to make fluorophores that ranged from like 350 to 550. I'm not going to talk about it at all. I'm going to just jump into the first motif. But before that, I will not have time to talk about everybody else's work. So I concentrated all the reviews that were published over the past 20 years in one slide, and I'd be happy to share this slide with anyone if you're interested in the topic. I would just encourage people to actually look at Thomas Gustafsson's review from the accounts just from a year ago or 2 years ago, where he actually demonstrated that in certain cases, you can study nucleic acids by using their intrinsic fluorescence. Everything that I told you that you cannot do, he can do, because he's a very, well, he can do in certain cases. In very long oligonucleotides, where you have a lot of chromophores, sometimes you have enough residual fluorescence that you can actually learn something about the molecule. But it's not an easy thing, and it's not done on a benchtop fluorimeter like in most cases. Anyway, here are the 5 modified pyrimidines, all of them from the furan, thiophene, oxazole, thiazole. I always like to show these crystal structures. They're really nice, because I love crystal structures, but there's a point here. If you compare all of these structures to tea, you realize that the sugar pucker, the sugar conformation, is identical. No perturbation by this substitution of a hydrogen or methyl to a 5-membered aromatic ring. Also, the syn-anti orientation remains the same. So this is a crystallographic demonstration of something that nucleic acid chemists have known for many, many years, that modifications at the 5 position of the pyrimidines doesn't impact. It's really benign. It doesn't do anything to the structure. Photophysically, of course, that's what's important to us. And what you see, we had quite a surprise. The molecules absorb, for the most part, about 300 nanometers. And that's important because nucleic acids absorb at 260, 270. If you can push it above 300, you can have selective excitation. The emission is actually in the visible. That was very rewarding. The Stokes shift is relatively large, but there's a problem with the quantum yield. You can see these fluorophores, for somebody who's doing imaging, they're not even fluorophores. They don't want to talk about 1, 2, 3% quantum yield. They want 70, 80, 90. We'll talk about it in a second. I'm not hiding anything here. What we do in order to understand the responsiveness, how these molecules might react to their environment, we do a very systematic analysis of solvent polarity, where you measure the absorption and the emission in many, many solvent mixtures. In fact, we've brought articles about why it's important to use solvent mixtures and not pure solvents, but that's a different story. You can see the absorption energy doesn't change much, but a lot is happening in the emission. In the apolar domain, continuous one, in the more polar dioxin to water, it looks like a mess, but it's not. The Stokes shift remains linear with polarity, but the intensity varies, and that's why it looks like a mess. I'll talk a little bit about it in a second. Because when you correlate the Stokes shift, the energetic difference here, with microscopic polarity parameters, a beautiful linear line. And this is actually quite intriguing. Now, what about this mess here with the intensities changes? We suspected that these molecules are molecular rotors. It's a very common term nowadays. You have two aromatic rings that have a rotation, single bond between them. If you excite this chromophore, it can lose its excitation energy thermally by those vibrations. They tend to be twisted excited state that decay back to the ground state, which is typically conjugated and coplanar. How do you prove the existence or support the existence of a molecular rotor? You take the emission spectrum in low viscosity solvent, then you take it in high viscosity solvent. So remember, this was a pretty poor fluorophore with a quantum yield of 3% in methanol. But look what happens when you start adding glycerol. We all know that glycerol is very viscous. You start going from methanol 3%, you end up in glycerol with about 40% quantum yield. So this is not a bad fluorophore. It's a wonderful fluorophore. But under non-crowded conditions, it loses its excitation energy very effectively by this particular mechanism. Can you exploit that? Yes, we can. So I'll show you two examples of what we've done with that, both in terms of solvent or environmental sensitivity to polarity and then to viscosity. So if you have a probe where you can correlate Stokes shift with polarity, and you might ask the following question. What is the polarity of the major groove of a DNA or RNA or DNA-RNA hybrid? You have a probe, right? I can place it inside an oligonucleotide, excite the fluorophore, measure the emission, put it on my calibration curve, and say to you, the polarity is here, okay? That's what we did. Single-strand short oligo. I know the number doesn't mean anything, 48 kcal per mole, we'll talk about it in a second. Make a perfect duplex, the polarity drops. Reasonable, right? Because you're forming a structured duplex, you expel some water, it's a little bit more buried within a hydrophobic pocket, and you can see that it marches further because when you make a DNA-RNA duplex, has a deeper major groove, less solvent exposed, the polarity drops even further. So what are those numbers? Definitely not water on the Reichert scale. It's about 2-pentanol, a very hydrophobic alcohol. So we claim that the polarity of the groove is not very high. Now, here's the most important lesson for the students here. I talked to them about scholarship yesterday. We're not the first to do that. In fact, Ken Ganesh was then in ICER Pune, had done it many, many years before us. But he's done it differently. He said, okay, let's take this particular fluorophore. He made aminouridine, put a Danzel probe on that. Danzel is also responsive fluorophore, and he got a totally different number. His value was very, very polar, was very close to the polarity of water. We got a value, and this is, by the way, I converted the ET30 values to essentially dielectrics, which is a whole different story. We have a much less polar environment, like pentanol. He's approaching water. Who's right, Ken Ganesh or us? Well, we're both correct, because the major lesson here, it's probe dependent. Why is it probe dependent? So theoreticians have looked at the changes in polarity as you march from the wall of the groove towards the bulk properties. And it's very, very steep. So when you're very close to the walls of the groove, it's very apolar. When you start moving away, it becomes much more polar. So here's like a topographic map over the z-axis, looking down the DNA duplex from above, and you can see, and this is just graphic, that by the walls of the base pairing, the Watson Crick pairs, it's very apolar. The dielectrics here are very low, about 20. Start moving out to water, it's very high. Our probe is on this hydrophobic domain. Ken Ganesh's probe is sitting almost in the water. So all values are okay. The most important lesson is realize that the outcome is going to depend on your probe, and don't think that you have the best probe in the world, because people have done it before you. Can we exploit the sensitivity to viscosity? So one early observation was that when we put this molecule in a perfect duplex, where the furan is pointing out, it tends to be quenched. However, when you remove this adenosine or adenine, forming an A-basic site, which is a very important biological DNA damage, it turns out that this molecule flip back in, and it becomes sandwiched between two base pairs. And as a result, it becomes much more stiff, and the emission increases because it's now forced to remain coplanar. So these are the tools, and these are the games that you can play when you have probes that are responsive. And the reason I've spent time on these molecules that nowadays I consider them to be very primitive is that I'd like you, again, mostly the student, to recognize that by studying your molecules really thoroughly, you can get much more out of them. Not just taking, the NMR, the IR, and yeah, I got the molecule, but you can actually develop insight into molecular behavior and then exploit it in different contexts. Okay, so this molecule, luckily, is very unique. It's responsive to both polarity and viscosity. Polarity responsiveness depends on the electronic differences between the two heterocycles because there's a charge transfer in the excited state. The sensitivity to crowdedness, to viscosity, has to do with this molecular rotor element. And it turns out that this molecule has both sensitivities. It tells us about changes in polarity by changes in the Stokes shift, and about the viscosity of the environment by changes in the quantum yield. And it's a generic phenomenon. You look at all these molecules that now have this molecular rotor element, and look at the viscosity sensitivity. In blue, it's very high. Yet, their sensitivity to polarity on this particular scale, it's the slope of the Stokes shift versus polarity, varies a lot. This is very sensitive. This is not at all, on very little. And that's because the electronics here dictates this sensitivity to polarity. But they're all sensitive to viscosity because they all share this structural feature. Here's a demonstration, actually the work of Srivatsan, who's now a professor in Pune many years ago, showed that this chromophore now, that is very similar to that, but instead of the thiophene being appended, it's fused. This has no moving parts. Yet, and as a result, it's very sensitive to polarity, but zero sensitivity to viscosity. It has no moving parts. Okay? So this was the beginning. 2000, a Gevante paper with Srivatsan then really put us on a totally new endeavor where we said, okay, can we take and imagine the purines into a new entity, like with the thiophene I just showed you, keep the pyrimidines, and play with the 5-membered ring only. And presumably, if you can form a C nucleoside, create a purine mimic, and if you can make an N nucleoside, such as here, create a pyrimidine mimic with a modification on its back, if you will. The Wan Xin in 2011 made the entire alphabet based philosophically on this thiophenopyrimidine, where he made the pyrimidine analogs and the purine analogs, highly emissive molecules, is a crystal structure of adenosine overlapped with the crystal structure of thiophenoadenosine. I'm showing you here that there's some dislocation here, but you can see the sugar pucker remains the same. The conformation of the D-ribose is the same. If you force the aromatic rings to overlay, you realize that, well, you learned that thiophene is bigger than imidazole. We knew that anyway, but there's a slight change in the sugar here or in the orientation because you replace a carbon-nitrogen bond with a carbon-carbon bond. So there's a slight dislocation, but biophysically, if you make a short oligo with G and a short in the center, a short oligo, you replace the G with thiopheno G, and now look at all the different permutations of C as a match or all the mismatches, you realize that if you compare the stability of these duplexes, G shown with blue, thiopheno G in orange, thiopheno G follows it perfectly. It behaves exactly like G. The perfect match, GC is the highest stability, a wobble pair is in the middle, and the purine mismatches are, of course, unstable. They're highly emissive, in the visible, above 400. Quantum yields now very robust, 20 to 50, not 2% like before. Can see there's a lot of information here. I'm not going to go over all that. The G, for example, has a pump here that's a tautomer. We know a lot about it, published papers on that. But overall, these are now typical, really useful fluorophores. So what can we do with them? We started asking, well, can we trick biology to accepting them? If you're studying oligonucleotides, you need to make them either synthetically on a solid phase synthesis machine usually, or enzymatically. Since we're interested in RNA, we said, okay, in the lab, those of you who make RNA, take typically T7 RNA polymerase, take its promoter and DNA template, and you let the enzyme run off and provide it with all the triphosphate, and it makes RNA for you. The important, useful promoters require the insertion of G in the beginning. So we said, let's challenge this enzyme. Let's eliminate GTP altogether. All those sequences start with GTP. Let's eliminate GTP and put only our fluorescent GTP analog, where we replace G with the thiopheno G. Turns out T7 RNA doesn't care, runs off, makes beautifully highly emissive RNAs. So it initiates it, it elongates it, it runs off. Now, those of you who are doing fluorescence spectroscopy would recognize that having a labeled RNA with a lot of fluorophores is probably not good. Because if I want to study biophysical processes and I have a lot of fluorophores, some of them will respond, but overall the dynamic range will be highly compressed. So I need a singly labeled RNA. How can I make a singly labeled RNA if when I feed it GTP, it puts it everywhere? So Yao Li developed a technique taking the same T7 promoter template, native NTPs, throwing in the nucleoside, not a triphosphate, the thiopheno GTP, forcing T7 RNA polymerase to start the synthesis with thiopheno G. It's a really interesting way to trick an enzyme to start the RNA synthesis with an artificial base. Turns out that you can then kinase it and anneal it and use a ligase to create a singly labeled RNA with the position here depending on the sequence that you designed from the beginning. You can then anneal it with a complement and create a folded structure. We studied the hammerhead ribosome this way. This is just an example published in 2017. So note here that this particular T7 RNA polymerase, enzyme number 1 accepts the modified nucleobase. Kinase doesn't care that it's a modified base, it's phosphorylated. A ligase doesn't care. So 3 enzymes work for our benefit to make a singly labeled RNA construct. Venkat Gopalan from Ohio actually found out that this particular T7 RNA polymerase mutant likes our base even better. So this mutant incorporates our modified base even better than the commercially available T7 RNA polymerase, and he reported an improved method. Okay, let's see in celebrating Professor Yonat's work. You heard all about the ribosome yesterday. For us, one of the most ambitious projects about 10 years ago, exploiting these nucleosides, was to ask, can you actually monitor translation, protein synthesis, in real time using these nucleobases? It hasn't been done before because making a short messenger RNA with modifications has never been accepted by the ribosome. So now we have fluorophores that behave very much like the native ones. So we said, well, maybe it'll work. So with Barry Kupperman from UPenn, Dongwan made about 30 messenger RNAs. I'm showing just a few things, and I'm just going to summarize it, where you moved a modification systematically either in the start codon or in the second codon in 3 different positions. And what we've learned from looking at all these molecules, and here's just a reminder of a slide that you essentially saw yesterday in Ada's lecture, just so we all recognize a key step in protein biosynthesis where the ribosome assembles around the messenger RNA, the FMET tRNA is in place. We call this sort of the initiation complex, and the only reason I'm showing it is because we found out that those modified RNAs form the initiation complex. They facilitate pre-complex formation where the tRNA comes in the right with the right selectivity. They're translocation active, which means that they make peptides. But importantly, from a photophysical perspective, each one of those discrete states has a unique fluorescent signature. So here's an example, the A6 here modified, the free RNA in black, initiation complex in red, tRNA comes in, quenching, drops, moving on to the post-complex, emission increases. Why am I showing that? Because now you can do stop flow kinetics and measure those processes in their rates. So what was really interesting about it is that, and we're not the first to do fluorescence spectroscopy on ribosomes, by no means, but most of the community, even those people who do single molecule fluorescence, they tend to label the tRNA or the proteins with fret pairs and look at changes in distance. And the fastest process that has been detected was the accommodation process, where you saw it beautifully. Maybe you haven't paid attention to this step in Professor Yonat's beautiful videos, where the tRNA comes in, it needs to undergo accommodation in order to bring the incoming amino acid next to the free amine of the growing chain in order to form a peptide bond. This accommodation is a process that has been studied because if you think about changes in distances, there's accommodation. This is ideal for FRET, for fluorescence or Foster resonance energy transfer. We, in those studies, uncover a faster process. And just by logical analysis, we had to conclude, but we were very careful, and this again for the students to realize how carefully you have to construct your statements. We said, talking about our measurements, such measurements directly identify a specific step during pre-complex formation provisionally. We were not going to commit to that, but we provisionally assigned it to the donor, to the codon-anticodon loop base pair formation. What does it mean? We actually measured the rate of codon-anticodon Watson-Crick pairing or any other pairing that takes place there, which was not seen before because nobody had a functional emissive messenger RNA. Anyway, so I'm going to switch gears a little bit because one thing that I have not highlighted, but those of you who might be doing oligonucleotide studies know that incorporating a single modification into an oligo, sometimes it's just washed away. You have so many bases around, so many base pairs are formed that if you have one modifications, the perturbation is minimal. So we wanted to challenge those molecules and we say, okay, how do they operate at the nucleoside level? Let's take an enzyme such as adenosine deaminase, a very important enzyme that takes metabolically adenosine to inosine. It's essentially deamination here. Imagine OH coming here instead of NH, tautomerizing to the carbonyl. And we asked, okay, if we made the thiopheno A and the thiopheno I inosine, will adenosine deaminase catalyze this process? And if it does, can we monitor it by fluorescence? Because each one of these molecules is likely to be fluorescent, but differently. So we found out that it works. We start by making a mock mixture of the two emissive probes, realizing that there are big differences in absorption and emission, so we can actually create calibration curves either by absorption or by emission, and now we can monitor the deamination in real time. Now, if you can monitor the deamination by either absorption or emission, if you can monitor it in real time, you can also start looking for inhibitors. So here are two examples of two known inhibitors of adenosine deaminase. You can see as you titrate the inhibitor, you slow down the enzyme, all monitored by fluorescence. And in this particular case, for the sake of this particular paper, we used a known ADA inhibitor that is used in the clinic for leukemia. But there's a problem here that I have not yet shared with you, but I promise to be completely honest. So you say, okay, that works, and it does. But how good is this thiophenoadenosine compared to adenosine? And you realize, you do the Michaelis-Menten kinetics, you realize that A to I is relatively, has a relatively low Km. Ours is much higher. So there's a problem. The rates are not too bad, but there's a problem with the Km. So where is it coming from? Here's the enzyme mechanism. I hope you can see in the back. It's a classical deaminase where you have water activated by zinc, lowering the pH, it becomes hydroxide, attacks this particular rehybridization, then expulsion of ammonia, you get the inosine. We know that chemically we have no problem. Computational work with Dinton-Tillo shows that de-aromatization of this heterocycle versus the native one is not a problem. So the chemistry not a problem. The problem comes when you look at what happens in the active site. There's a carboxylic acid hydrogen bonded to this particular nitrogen. And as a result, if you think about what we have a problem because we have a hydrogen poking out at this particular hydrogen instead of a lone pair for hydrogen bonding. So we had to fix that. So that led to the new alphabet that is based on isothiazole. We started here, non-emissive. We made those thiophenopyrimidines very effective, but not working all the time. So we decided to make molecules that are much more difficult to make. Isothiazoles somehow don't have a lot of good chemistry out there. But that was the origin of the thought how to make a new improved alphabet. And Alex Rovira, an amazing grad student, was able to make all of them. Synthesis was much more difficult than the thiopheno. We could do just Friedel Crafts essentially and glycosylate. This had to be built from the ground up. He started with a ribolactone, 5-carbon lactone, iodomethylation, increasing it to 6, and essentially turning it into a thiol and using the Thorpe-Sigler cyclization to actually build this isothiazole from the ground up. Heroic effort. I told him it's not going to work. He proved me wrong. That's how it should be with a student-mentor relationship. So he also initially refused and then started getting crystal structures of everything. Here's the crystal structure of all the nucleosides that he's made. I'm particularly proud of the purines. We'll talk mostly about the purines because they're the most important. We had a really happy day in the lab when we looked at the old published crystal structure of guanosine. This is taken from a paper in 1970, shown pretty much copied from that paper and then sort of turned into a modern depiction using computer tools. This is again the March lab at Caltech. What you see in the structure of guanosine is a hydrogen bonding from the Hoogsteen face of one nucleoside to the Watson-Crick face of a neighboring nucleoside. It's a nice structure, nice packing. Alex got the crystal structure of the isothiazology, same type of interaction. So we knew that we successfully put this nitrogen back into play. These molecules are emissive, not as emissive as the thiopheno. The nitrogen usually interacts with solvent and leads to a lot of decay pathways that can kill off fluorescence, but the G particularly is useful, again, with pretty decent quantum yield, about 25%, emission close to 460. So now we have essentially two alphabets that are functional. The big question in the lab was, okay, so Alex has gone through 2 years of synthesis to make this alphabet, because we realized that when X was CH, we had a problem. Question is, was it worth it? After so much work, putting back the nitrogen, is it going to work like we want it to work? So here's the big day in the lab where you do the deamination, monitor it either by fluorescence or absorption. Here's the thiopheno system, the early one with the thiopheno. These things here you cannot see much faster. 2 lines actually overlapping. It's both the native one, adenosine, next to the isothiazole adenosine. Works exactly like the native one. Really big happy day in the lab. So where did we start? We start with those purines that are essentially dark with 0 quantum yield. We made, and the reason I'm emphasizing the purines will become clear in a second. Now we have 2 G analogs that are very functional, emitting in the visible. The A's are a bit more difficult sometimes, but still working very, very well. So to give you some perspective, and since we had a mess in the beginning, I don't even know where we're time-wise, but I guess you'll have to bear with me. For 50 years or plus, the community has been using 2-aminopurine as the purine of choice. It's been studied for decades. It was introduced by the great Lubert Stryer in 1969 and has been exploited in thousands of papers. For one reason, it was the only one that was available, the only one that was emissive. As a nucleoside, think about let's just pause for a second. Adenosine has this amino group here. 0 quantum yield for emission. You move the amino group from here to here, quantum yield for emission is almost 70%. Just realize how a tiny little molecular change changes the photophysics altogether. So the community had used this for decades because it's very responsive, but it's problematically responsive for the following reason. When you look at it, and I don't know if you can see it back there, this is the nucleoside, 70% quantum yield. Single-stranded RNA drops by 10, 20-fold, duplex almost 0. 2-aminopurine undergoes significant quenching upon incorporation into oligonucleotides. All these neighboring chromophores kills its emission. Thiopheno G is much more robust. But beyond that, the biggest problem is not that it quenched like 50-fold. Because nowadays, fluorimeters are so sensitive, you can use this trace here to do a lot of studies. But the problem is that frequently what happens is that this residual emission comes from biologically irrelevant conformations. Why is that? As I told you, as a free nucleoside, when it's exposed to solvent, it's highly emissive. It's also known, because it doesn't match Watson-Crick pairing, it's also perturbing its environment, which increases its dynamics of going in and out. So now you might be seeing here the fluorophore projecting out in a biologically irrelevant conformation. So one has to be very careful to not fall into this issue that you see a signal, but it's meaningless. Okay? So we know that thiopheno G, and we've done NMR and computational work and whatever, to show that its emission is reflecting the truly populated conformers. And a lot of this work was done mostly in Yves Melis's lab in Strasbourg. I owe him everything. I always tell him that he makes me famous, and he's really an amazing biophysicist. So let me just wrap up the whole thing with talking a little bit about opportunities. I told you about purine and pyrimidine metabolism. I'll tell you a little bit about cofactors, and we'll finish with antibiotics in the sort of theme of ribosomes. So we talked about using those deaminases for high throughput screening of deaminase inhibitors, really important molecules. We've done that. You can take THA, TZA, or even the diamino analog that gets deaminated by the enzyme to G, actually. Each one of those molecules has a different emission spectrum, a different kinetics of deamination. So you can actually, it's very helpful for high throughput assays to have sometimes molecules that don't deaminate very fast. Because technically it's very difficult to add inhibitors if your reaction is over by the time you edit the enzyme. So there are some technical glitches, but we use that to uncover new inhibitors, collaboration with Seth Cohen in my lab, in our department, who's working on pharmacophores that actually bind metal ions. Remember, ADA is a zinc enzyme. And so we identified by screening hundreds of molecules using this assay, we've identified new motifs. We expanded it to other aminases that are very important. One in the amylase is very important for neural development, even speculated to be important in traumatic brain injury. We found out that we can monitor this enzyme, but not with the thiophenol, but only with the isothiazolol, G. This is the nucleobase now. It's working on the nucleobase, not the nucleoside. Cytidine deaminase is a very important enzyme that tends to deactivate chemotherapeutic agents. We can use our fluorescent analogs, even perturbing ones, to monitor its activity and also to learn about those molecules. It's something that I haven't talked about. These tools allow you to learn about the tolerance of the enzymes to those modifications. So we found out that cytidine deaminase actually has a big pocket. It'll tolerate this methylthiophene in the active site and deaminate very effectively. I'm not going to talk much about that. If you just think about it, it's amusing. Most of the cofactors, 98% of them, have nucleotides in them, right? NAD, SAM, secondary messages in bacteria like cyclic dinucleotides, coenzyme A, they all have either adenosine or G. We can make all of them with modifications anywhere you want to by feeding those enzymes that make it in nature using the triphosphate. So we published most of it. I'm not going to talk about it. I'll just finish with one example where we start moving to molecules that you may not have paid attention yesterday because it was very small. Others use puromycin to study her protoribosome. Here's the structure of puromycin. It has a dimethylamino group. It's essentially dimethylated adenosine with an amino acid connected to the 3' position through an amine. Very interesting antibiotic, but like some of the antibiotics that Professor not mentioned, it's not selective. It inhibits both bacterial as well as mammalian ribosomes. Interestingly, this molecule has some interesting photophysics, and we asked, can we actually make an emissive puromycin analog? Made the dimethylbenothiophene emissive, maybe 100-fold more than that, but this is 0. 100 times 0 is very, very low. But we used a trick that Luke Lavis developed from Genelia, where you actually replace dimethylamino groups with a cyclobutyl. This is much more emissive. And in fact, we can tune the emission, and we found that the difluoroderivative emits in the visible and has a very decent quantum yield. So now we can, for the first time of our studies, we can actually image a molecule with a modified small molecule. It's not like a major fluorophore. So this is taking neurons from mice or rats and exposing them to this antibiotic that is used to study protein biosynthesis. This is just a nucleostain. This is imaging of this fluorophore using the DAPI channel. For the first time, we can see it in cells, in neurons. And this is just to show that if you treat those, you fix those cells and you treat them with antibodies for pure methylated peptides, namely peptides that were terminated by this antibiotic, you can see that our molecule is found exactly where those peptides are. And in fact, you can take it one step forward, and you can even use anti-ribosomal antibodies and overlay everything and realize that, yeah, this molecule is localized in the ribosomes or next to the ribosome. So really first time for us, one of the most recent papers, I'm waiting to hear from Angewandte, I hope they'll buy it. And I'll just wrap it up and tell you about how we arrived here. So we started these native bases, the nucleotides that are in nature, amazing molecules, but totally dark. I told you a little bit about these primitive molecules that led us to a much more informed alphabet. We then, along the way, discarded the quinazolines that are a bit more perturbing, and we even discarded other motifs that you might think about, and even other isomers that you might think about. You move the sulfur from this position to this. These are not highly emissive. They're okay, but not very well. Put in oxygen instead of sulfur. The molecules are reactive. They do Diels-Alder chemistry. You're dead. So we continue with the more challenging synthesis, arrived at the thiazolo alphabet, and as I pointed out to you, I really like the fact that now we have a bunch of emissive purines. We're deviating a little bit from isomorphicity now in order to understand photophysics. We learned about the methyl groups, the CF3 groups. I have a hypothesis that solvation of the Hoogstin phase here is really important to the dynamics of the excited state and its decay. So we're trying to push water away and see if the quantum yields indeed go up. And now we're actually playing with epigenetic modifications such as N6-methylated A. I told you a little about this dimethyl, and even highly modified molecules that emerged out of Luc Lavis's idea. This is a reference, one of the major reviews written by Luc Lavis, telling you about those cyclobutyl substitutions. So it remains for me to really, I haven't done any of that. I was just sitting in my office, and my students obviously have done this. Some of you may know Srivatsan from the early days of our work, and I really just want to tell you that it's been a pleasure to be here, and I really want to thank you for inviting me. Thank you.
Thank you, Professor Tor, for an exciting talk on molecular engineering to study mechanisms of biological processes within cells. So though he has not talked about the rigor that he has put in the synthesis of the molecules, that is the actual hard work I believe in. So thank you, sir, for the wonderful. Now we have time for a couple of questions.
Thank you very much. Nice work. And so I have a question. So you developed the fluorescent base, right? So work used in RNA. And the most exciting point is that you may detect the timing when the messenger RNA interact with the specific transfer RNA, but I couldn't, you explained, but I couldn't follow your explanation. Could you detect the timing or duration when the specific messenger RNA having your fluorescent base interact with the transfer RNA?
Absolutely, I appreciate the question because it gives me a chance to talk for another 10 minutes. Enjoy. I'll avoid feedback. I've skipped a few technical things. The most important thing probably to state is that this is done in vitro in what the professionals will call sort of synchronized ribosomes. So you inhibit certain stages, or you don't provide certain factors, or you add, say, the tRNA at a very specific timing where the ribosome are essentially stalled and waiting for it. So you can, otherwise it's heterogeneous and all those kinetic processes will overlap. So in vitro, synchronized, and what I was trying to explain about what we've seen is that because the field is usually goes with either single molecule fluorescence or even ensemble, but looking at Fred, there's certain processes that they cannot see because they rely on distances changes, right, or orientational changes in order to get a FRET signal. So what they were able to detect is that when the right tRNA comes in into, say, the A site, it needs to undergo a conformational change, which is called accommodation, to allow for peptide bond formation. So that was, until our work, like the fastest process seen, because when tRNA comes in, initially, there's no real change in distance. It comes in before it undergoes this change. So what happens in our case, we think, is because our nucleoside now is waiting at the A site for the tRNA. Okay? And we know that base pairing typically in our modified nucleosides causes quenching. So now we have a process that we can monitor because the fluorescence intensity changes. So tRNA comes in, and this is the process that we kinetically determine prior to accommodation that was seen by FRET. So the reason we were so careful in stating that was that I don't know how to independently measure this process. I mean, I don't have any other tools but using our tools to measure this process again. So we were very careful by stating that, well, the fastest process that had been seen was accommodation. Ours is now faster, so it must precede that. And therefore, we provisionally concluded that it's the pairing of the codon and anticodon.
This is the decrease of the fluorescent intensity and the increase.
No, because again, for that you need to let just the ribosome do its work, but we did it in synchronize, one step at a time. So we measured discretely those kinetic events, not continuously. Thank you.
Hi, Professor. Thank you for an exciting letter. So I know that you explained very well about the relation of the viscosity and the fluorescence, okay? Mm-hmm. But I'd like to know something about more in detail, because when you measure the viscosity and you did the rheological behavior, because we know that the viscosity sometimes changing during the time, okay? I would like to know something about it, because if changing something during your measuring, if there is a changing of the organization of the chain, do you know about something? I'd like to know if you talk something about. Thank you.
It's a very important point, thank you. So I have to make a statement here because we were using specifically dioxin water mixtures. Now, dioxin water, if you think about it, is a very unusual solvent system. For us, it served really well because we were looking for a solvent system that will not, that will have a mix of hydrophobicity, hydrophilicity, hydrogen bonding capability, donors, etc. Okay. So where's the problem? The problem is that dioxin water, unlike most binary solvents, doesn't change linearly. The viscosity is not a weighted average of the two solvents. It's actually parabolic. So what we were seeing here is a complete mimic of the viscosity. In fact, we published it a few years later when we finally figured it out that we actually took from the literature the values for our dioxin water mixture on one axis and then plotted the emission intensity, and it was just overlapping. So it's a peculiar system, and so it's, in a way, you can think about it as an artifact, but it's because this particular solvent system, at about 2/3, maybe because of the fact that dioxin has only hydrogen bonding acceptor, and water has 2 hydrogen bonding donors and 2 acceptor, 2 lone pairs, is very peculiar. On 60–70% yield, it maxes out. It's like the most organized, and then it drops both either a higher percentage or lower. So it wasn't dynamic viscosity, it was just, doing steady state emission with a solvent system that unfortunately we were not familiar with in the beginning, and then realizing that although it gave us what we needed in this particular highly beautiful linear range, it has some issues. So you can probably use other solvents and will not have intensity changes. We don't know much more about it. We just know that we were using, perhaps wrongly, not being aware of the fact that this is a really unusual solvent system. So that's the artifact.
Thank you, Professor To.
Sir, actually, we have this AMBER simulation package from your USC group. We have research license. So can we extend these studies to some simulations to get the dynamical nature of these hydrophobic and hydrogen bonding interactions? Already we have our AMBER simulation package and these structures are available.
You should try that. I don't know. I'm curious if you talk about computational work and what hampers me, I think, in the community. It's really very difficult to do computational work about the excited state. But if you want to measure structure and mimic those things, that's an interesting project on its own. But what I'm trying to learn from computational chemists is that can you actually tell me something about the excited state dynamics? Because as I mentioned in the beginning, this is a property I cannot design. So but if somebody can tell me in advance, hey, just don't make this molecule, it's not going to work, and you save me a year, why not?
The excited state dynamic, that means I think the parameters, the molecular parameters for such studies are not available now. But the actual ground state structure and crystal structure, we can do the simulations as far as my...
Good.
Yeah, okay, thank you.
Just a few fundamental questions. This nucleoside-based antibiotics, is it targeting the 16S ribosomal RNA site or some other sites?
So puromycin is essentially, although it's such a tiny molecule, it actually mimics the charged end of tRNA. So if you remember Ada's sort of videos, it's actually, it has a free amino group that it can use to attack, and it actually terminates protein synthesis, but it actually mimics a charged tRNA in a way. It's unbelievable that such a tiny little antibiotics mimics the whole tRNA structure, but it does go to the same site and it does terminate synthesis.
Okay. One more question. So you are talking about this viscosity sensitivity. Have you ever checked the possibility of having a terminal alkyne in place of the alkyne which is placed in between? Do you think will it make any difference?
Alkynes are problematic because, at least from basic electronic conjugation, they're obviously sort of cylindrically symmetrical, right? You'll probably, if you think about putting it, say you have the pyrimidine, say a thiophene, and putting an alkyne here, yeah, it'll be a fluorophore, and it'll probably have viscosity sensitivity, but we've never made these molecules. You want to make it?
Would like to try?
Sure.
Thank you.
Okay, thank you, Professor Tor, for a nice and interactive session on engineering of biomolecules. Thank you, sir, and let us give him a big applause for the one.
Thank you.
That was really an enlightening talk. I express my sincere gratitude to Dr. Yitzhak Tor and also to Dr. N. Manoj. And I thank you all for patiently listening to the session. Now I request Dr. N. Manoj to present the memento of appreciation to Professor Dr. Yitzhak Tor, and I kindly invite Professor Tor to receive the same. Now, I would like to invite Dr. Jason MJ Assistant Professor, Department of Chemistry, Sacred Heart College, Tevra, to present the memento to Professor Dr. N. Manoj, and I kindly request Professor Dr. N. Manoj to receive the same as a token of love. An important announcement. Now we will be having a short tea break, and I request everyone to gather back at 11:25 am for the preliminary lecture 5 by Professor Dr. Dervaldo Santos Rosa. And also, the poster presentation participants are required to remove their posters from the poster boards during lunch break. Thank you.
A warm good morning to all who have assembled here. We are after break, and I'm sure that you all are enthusiastically waiting to sharpen your research aptitude. Let's resume technical sessions of 21st Professor K.V. Thomas Endowment Seminar and 4th International Symposium on New Trends in Applied Chemistry, NTAC-2023. Now, we are gonna lend our ears to Plenary Lecture 5 by eminent and our guest, Professor Dr. Derval dos Santos Rosa on biodegradable porous materials for recovery of metallic contaminants from contaminated water. This session will be chaired by renowned Dr. Srijit Shankar, and I'm highly privileged to introduce him to you. Presently, Dr. Srijit is the Senior Scientist in Photosciences and Photonics Section, Chemical Sciences and Technology Division of CSIR NIST, National Institute for Interdisciplinary Science and Technology, Thiruvananthapuram. His research interest is on the development of smart and functional materials, coatings and thin films for energy applications, including energy management and conservation and multifunctional formulations and smart coatings. He has numerous publications and patents to his credit. Dr. Shankar has been recognized by several prestigious awards, including the Kerala State Young Scientist Award 2020 and 3rd BRICS Young Scientist Award representing India at the 3rd BRICS Young Scientist Forum at Durban in South Africa for the year 2018. He is a feather in our cap as he is an alumnus of the Department of Chemistry, Sacred Heart College, Tevara. With immense delight and honor, I invite Dr. Srijit Shankar to chair the session. So please.
Thank you, and very good morning to all of you. Let me start by thanking the organizers, Professor Franklin and Professor Ramakrishnan, for giving this opportunity. And it's always a pleasure back in this hall at Sacred Heart College, Tevara. And I take it as my privilege to introduce the next eminent speaker, Professor Derval dos Santos Rosa from Brazil. He received his doctorate in chemical engineering in the year 1996 from UNICAM, and then he had a postdoctoral stint at the University of Brighton in England. He has served as a project coordinator, section and division manager at Telebras Research and Development Center for a long term from 1986 to 2001. He was the president of the College of Pro-Rectors of Brazil and was responsible for transferring some technology developed by the national companies in Brazil. He was earlier a full-time professor at the São Francisco University and until 2008, and is currently an associate professor at the Federal University of ABC in Brazil. His areas of interest include materials and metallurgic engineering with specific emphasis on polymers, working on biodegradation, recycling, and so on. He has experience in basic and technological research projects financed by different developmental agencies and companies. He has more than 80 publications in renowned journals, 3 books, and 19 book chapters, along with a few patents. Today, he'll be talking to us about biodegradable porous materials for recovery of metallic contaminants from contaminated water. Professor Rosa, the floor is yours. Thank you.
It's okay. Good morning, all. To me, it's so pleasure to be here and for this opportunity to talk with you and maybe to establish some collaboration. Okay. Today I will talk about the biodegradable porous materials for recovery in metallic contaminants from contaminated water. So before I start, I'd like to present some where are you from. I'm from Brazil. I don't know if you have ever heard about Brazil, okay? Brazil is a country in South America. It's a big country in area like India, okay? And I'm located in São Paulo state. Our region, if you compare Brazil, have 215 around that a million people living there. In our region in São Paulo is 46 million and people living there. My university is located in ABC area. ABC, the name is from the name of the city, who call Santo André, São Bernardo, e São Caetano. This region, it's very crowded because there is a lot of companies there. So our university is located that. It is a new university. It was founded in 2005. It's a young university. If you observe in my CV, as he said, I worked in a lot of companies, and after that, I go at the university, okay? But our university has 2 campi, and all the faculty holders are PhD. We are a public university. If you know, is tuition free. We are looking for accessibility and refuge service, human rights, sport, recreation, and affirmative actions. This is a show view of our 2 campi. So another point of our university, this building is just we are using for the research. We have around 16,000 students in undergraduate students, in around 2,000 graduate students, and we have 800 and professors and administrative staff. So, of course, you know, sorry, it's very sensitive, okay? No, I'd like to, okay. Now, I would like to say something about our university. We are interdisciplinary university. Of course, to understand a little bit, we changing the pedagogic project. We working in interdisciplinary situation. Like my center, I work as in materials engineering, but we have together social scientists working together because we think that the solution for the complexest problems in the world is necessary to talk the different areas. So we have at the moment 25 undergraduate courses, 9 master's programs, and 70 doctoral programs. During this pandemic, I'm young, okay, I have 62 years old, but during this pandemic, I thought about my function at university. I observed that there is a lot of problem because sometimes we do some research and talk between us. The society sometimes don't know about what we are doing. When we are locked in your house to teaching by internet, it was difficult to me. So I decided, of course, do you know, you are a YouTuber? No, I'm research. But during this pandemic, I thought in create some system that to talk with the young university. So I invited the young university look for this, put in yourself and follow this system. This channel, I intend, I interview most 100 research. I interview some industries, and we produce a lot of mini docs to show the community what we are doing. So I think at the moment it's so important to do this, because there is a lot of students thinking why I want to study a lot. This is the point. So our group, we have we have been working in a lot of area, in recycling, in surface modification, natural fiber and biocomposites, nanocellulose, encapsulating active. Now I will talk about porous materials. This development, so we starting a new period, because we had a very big project around $1,000 million by FAPESP, because we observed that there's a lot of problem in water in the world. So the contamination water research, of course you know that there is a lot of activities in industries that they produce a lot of products, and of course you know, but sometimes you don't know that they produce a lot of contaminants. So especially sometimes when we look for the World Health Organization, they establish some high production, according to the UNN, there is a lot of almost 4 billion of people still living without safe sanitation and with the treatment to health and environmental compromise as located is economic. So we are looking, sorry. We observe, we pay attention, especially in water and wastewater. Maybe, of course, in our country, we observe the water treatment, but there's some problem about this situation, because sometimes after this treatment, we have a lot of water and contains some and potentially toxic elements. This is complicated, because sometimes we take some medicines, and after we use it, we urine it and go to the water, but during the treatment not remove something. And especially when we're looking for the system of treatment, we observe a lot of problem, okay? Incomplete removal, formation of secondary waste, the physical chemical, use excessive consumption of chemical products, and the oxidation, especially advanced oxidation, they form some intermediate products that there is a lot of problem. PTE, like the potential toxic elements, usually is related with metal and metalloids elements or ions. So today I will talk about this situation. If you observe, you have, at the moment I pay attention about the 6 ions, okay, but today I will talk about something too. and copper. There is a lot of disease that I observe when you drink some water. And we have some chromium that the companies produce about it, and there is a lot of problem with cancer. So if you look for this, the situation in the world, more young people are having some problem if you compare a long time ago. It's very complicated situation. So, and when are looking, sorry, when are looking for these PTEs, as I said, I'm looking for manganese, cadmium, chrome, copper, and nickel, and zinc, and manganese. So, I don't know in India, I prefer to say about Brazil, okay? We have some specification there when I'm looking for the water with our drink. But if you observe like this, nickel, the OMS, the Organization Mundial of the Health, okay, established this limit. But in Brazil, the environmental ministers established this. There's a lot of difference in the word that say. So, the question and the problem is, sometimes we drink the water with the metals. This is the problem. So, I said to you, there is a lot of treatment, okay? But in our case, we decided to work in a sorption process. Why this? Because it's low cost, efficient to remove this metal, and special in this concentration. And the absorption, of course, you know that is phenomenon that mass transfer the substance to a surface of one solid phase. Of course, and surface interaction, it's so important for to understand about this. So we choose some porous materials. Well, today, to understand about porous materials, I think it is important we worrying about the two situation, okay? Porous size and composition of the materials. We have been working with hydrogel, membrane, and hydrogel, aerogel, hydrogel, and membranes. So it's important to understand about the size, because we need to understand the interaction of the metal and materials, okay? And the other point is necessary to understand the connective of the porous. So, I know that there is a lot of classes of systems that contain some porous. Oh my gosh. Okay, there's a lot of classes of pores, but we are looking for organic polymers and special biodegradable polymers, okay? The class of the multi-additional pores is so important for to research some to get this type of material. So we are talking about some this type of materials. Well, about the aerogel, you know that these materials have ultra low density porous adsorbent materials which promise properties that so good that as ultra low density, low thermal stability, and photonic insulation and large surface area. How can we prepare this type of materials? It's simple. When usually we prepare some solution and make some aggregation or a jellification, okay, if to cross-link the chain, okay, and after that drying it and tempering it. There is a different of methodology that I would like to understand a little, but to talk about the aerogel, I started to show something about we developed with Paulo Camani, Midun, know him, and so we started to understand how can we prepare the aerogel more environmentally friendly. So we look at the literature and observe that it's important to know about the efficiency of the cross-link agent. So Kamani research about the difference of the relation of the cross-link agent and analyze the behavior of the pores. And to understand about the size, how can we building the size of the aerogel? This is so important because we need to understand the size of the materials that we prepare. It's so important to analyze it. And we analyze that there is one relation of the starch and citric acid that increase the cross-link. This is so important to understand the size of the pores. So if you look for this situation, it's possible to understand about the size of the pores. You observe that the photomatography show us the porous structure, and if you do some statistic analysis, it's possible to observe the small pores in proportion 1 by 1, and large pores in other proportion. So, but this is important to, you know that aerogel is important for to absorb the water, so to attract the water. And then this paper just to look for the size and they analyze the relation about the absorption of the water. And we observe that when we have the cross-link agent concentration controlled the size of the pores, when it's possible to observe the different behavior of the absorption of the water. Until this moment, we don't worry about the metal absorption, okay? Just to understand the structure, how can domain the size of the pores. So, hydrogel is another type of materials that we have been working. A hydrogel are three-dimensional porous polymeric network and capable to absorbing, retaining a high amount of water without dissolving, okay? So it's important that sometimes we will have some hydrogel, but there's no mechanical properties, and it's not possible to use it in water treatment. So it's easy because these materials has a good mechanical properties, tolerance of vigorous external agitation, because if you use it in a treatment, it's so good to understand this behavior. So it's easy to prepare this material, and I show you one results obtained by Clara, is a undergraduate students who studied eco-friendly using carboxymethyl cellulose to understand when you put nanocellulose or nanoclay. It's interesting because these two additives, that's one organic and one inorganic, it's like that because when you put nanoclay, sometimes there are some organic compounds inside of the layers, okay? But we are looking for this behavior of this. So we studied 3 different nanoparticles from different types of, and we observed the hydrogel present a good water absorption, and the different composites were efficient for to continuous release, like fertilizer in water in soil. And Clara observed that is if you compare, for instance, nanocellulose, montmorillonite is a nano clay, okay? And there is another clay that whose name is vermiculite. Is a different type. Today I don't discuss more about it, but it's important things that we understand the effect of this situation. So because sometimes we are looking for the metal absorption, okay? But sometimes it's important to understand the behavior, the effect of the nanocellulose, the organic and the inorganic. This work was very important for us to understand a lot about it. So we work to membrane, okay? Firstly, you know that all the time we are looking for the environmental materials. So we usually use biodegradable materials, but sometimes I observed in the literature that the problem is they use some elements or compounds to produce the porous. It's very dangerous. So in this study, we working with to develop some new compounds to produce some porous. So firstly, membrane, of course, you know that is materials that has possibility to remove some contaminants, especially you need to take care about the size of the pores in membrane. Of course, you know that microfiltration, ultrafiltration, nanofiltration is the different type of size of membranes, and it's possible, if you choose the size, it's possible to get the virus, it's possible to get some different type of this. And in our lab, we develop a different size of membranes and study the different methodology to prepare the membranes. Because it's very simple sometimes. Of course, when we're looking for the water treatment, there is a lot of companies produce the membrane, but they use I don't know how can I say, but it's expensive process. So one simple process, when you use the inversion of phase, it's easy. And inversion of phase, at the moment, this is one type of the process that we use in our lab. We working in 3 or 4 type of methodology and produce a lot of membranes. Sueli investigated 3 type of porogenes, but we Sueli just look for the glucose, sodium chloride, and sodium acetate. And in this case, we pay attention about the environmental impact of the porogenes. So we produce this type of membrane. We use the biodegradable polymers, whose name is PBET, or polybutylene adipate coterephthalate, and we observe the size of a lot of poros, and observe and changing the different quantity of these porogenes. So we choose the best condition to prepare the biodegradable membrane. So in this case, we decided to use cellulose and polyabsorbate to promote a high porous. Well, the porous promote impact, of course, in mechanical properties, and but because when you use this membrane in treatment water, we need to necessarily to think in the mechanical behavior. So we investigated about it, because sometimes when the mechanical properties going down, sometimes we use nanocellulose to increase it. We having a lot of working in this area. So, but the other point is important when you use life cycle assessment. Is a system that is partial to measure the really impact of the process. Because sometimes we say something about, well, we worrying about the system, the ecological, developing a new materials, but it's not possible to say this correct. And then our lab used the life cycle assessment to use, and we have facilities to show in 17 categories like this when we use to show about the CU2 equivalent, to measure about this. And we decide the best condition and the best process. So, to conclude some part, okay, porous material sorption, like aerogel, hydrogel, and membranes, present potential of water treatment. However, to interact with PET, sometimes you need to changing the materials. If you remember, I said at the beginning, we are looking for the size of the poros, and then I show you some papers and to have one idea that we are doing there. But now I starting to show something about how can we changing the surface of the materials. So, and the modification use chemical to promote more interaction with the metal ions. To understand a little more about the PET sorption using functionally porous materials, I have been working in 4 ways. Using clay minerals, because if you remember, Clara said to us that is a good possibility and different behavior. We looked for biochar produced from residue. We are just produce some products, some additives using residues, nanocellulose, and
quelante agent. So if you remember, sometimes I ask some researching about the possibility to put some additives or what the interesting with the to get the metals ions. So I turn Paul again, and this is some production with me done. We interact to produce, if you remember, Paulo investigated the different proportion of the cross-link agent. And in this case, he looked for cadmium and zinc. And he observed something that this proportion, and we observed that the low string gauge rate, high surface area, and good mechanical properties, and high absorption efficiency of cadmium was found in aerogel in this proportion of the relation of the agent and starch. This aerogel we prepared using starch. Of course, you know that they remember about the size of the pores, but the important things that you look for, if you put some different particles like nanocellulose, is important to understand the behavior of this. The other work that we develop aerogel or cryogel with the chitosan. And chitosan is a biopolymer that's used a lot in in our area, but it is very good potentially to remove toxic metals. Marcelo started to obtain chitina to modify the chitosan and to prepare aerogel using the chitosan, and in different size, in different condition. And we observed that after the incorporation of microcellulose, this is situation, because when I use nanocellulose, one behavior. When you use microcellulose, is other behavior. The surface area is so important to say that to understand about the situation. The cryogel structure favored increase the surface area, and the density is like 0.02 between 0.06, and the pores are irregular and interconnected. And so, but the interesting things, Marcelo analyzed in other moment chromium, and it was very good results. Cryogel create a good affinity with chromium. We changing a little bit the chitosan, of course. We are in during the patent process here, so I don't speak a lot of these, but I would like you understand that the oxyonium or chromium, it was very good when you use the chitosan. So the divalent zinc ions was positive charge and may have undergone electrostatic repulsion, but this is not absorbed in this type of materials. So summarizing, the chitosan cryogel with microcellulose were potentially solvent for the toxic ion, and mainly chromium 6 ion. And the microcellulose contain must always balance keep some functionally group-free remove. Aerogel is a very good material when you thinking in to remove the heavy metals and especially when you use different methodology like freezing drying. Freezing drying, we are using this in our lab, but sometimes we worrying about the capacity to prepare it because there is no quantities possible to use this. So Danielle studied last year about the capability of to remove the chromium, and he took very good results and looking for the mechanical properties because to use it is very important, and pay attention about the influence of cellulose nanofibers with the acid, special citric acid. All the time we worried about what type of cross-link agent use. There is a lot of type of cross-link agent in the literature, but we prefer use sometimes the chemical that is not cause some impact in the environmental. So in this work we study thermodynamic cinetic for to understand a little more about the chromium absorption by cellulose foam. The effect of the citric acid contained on cellulose foam, it was very important, like as we met in Paulo work. So the results of the removal of chromium, it was we observe a pseudo second order behavior of the mechanism of absorption, and the interaction of the dichromate, the mechanism was very interesting because when you changing something in materials like changing the secondary linking, it's very important because the behavior of the materials change a lot. So hydrogel is one other materials that we are looking. Recently, Jessica investigated biodegradable using gelatin and composites in hydrogel and filled with cellulose and analyzed the behavior with chromium-6 adsorption. And she studied it and using residues, eucalyptus residues. The eucalyptus residues is so important that we observe. If you remember, when you get the residues, for instance, this eucalyptus, if you remember, there is cellulose microfibril, and inside lignin, and between them, M cellulose. Sometimes I remove the lignin and the M cellulose and put just cellulose in our materials. But sometimes I use a pre-treatment, but not use a lot of acid. Just to put a little, sometimes use microwaves and something pre-treatment. It's so interesting because we want to get more hydroxyl in materials to be interesting in ions, okay? And this is the point that Jessica investigate. Of course, I will summarize here some points, but the filler alter the gelatin molecular vibration and form a new hydrogen bond. It's interesting for when you analyze the sorption of the ion metal. special, we pay attention about the thermal stability, and we observe high thermal stability. Well, the hydrogel, we did the mechanisms of the kinetic students and observe if the effect of the micro the residues of the eucalyptus and the presence of no cellulosic components alter the hydrogel and cross-link, and consequently move the interaction of the chromium 6. For you have one idea, the best results that Jessica obtained, the sorption capacity was around 13 milligrams per grams of the hydrogel. Other students developed some biochar. You remember the other point that we studied? Biochar is a materials that usually there's a lot of work in literature, but the biochar that we are working just using some residues, because we need to put value in residues, and we prepare the hydrogel, and we test the different quantity of the biochar, and with 3% of the sample, the presence of pores are more evident with the large number of the cavities. So the size of pores. So it's very important to analyze it, and we observed that the hydrogel exhibited a water absorption greater than 290% for the all samples. The inclusion of the high level of biochar increased removal capacity of the chromium. So the hydrogel we are observing is a very good materials for to remove the ions or the metals. And in this work, we observed that the novel sustainable composite is hydrogel contain nanocellulose to remove this. And we pay attention about the chromium and again the chromium and copper. And we measure the size of these, and again we observe the effect of the CNS in the size pores, and we observe the different behavior, the presence of the cellulobiose hydroxyl group turn the materials hydrophilic and increase the percent of the water absorption. So we observed a Fickian diffusion model, and we studied the behavior, and we studied the biodegradable materials. So in our lab, we usually test the biodegradation, especially in different methods. In solid, like in soil, put the solid in soil, and looking for some period the behavior of the materials. And sometimes we observe the you put the materials in enzymatic methods, and then observe the behavior of these materials. We choose the type of the enzymes, and it's so important to observe the behavior of the materials. In this case, the hydrogel were biodegradable, showing a max reduction in around 80% in a short time, especially 2 months. Of course, you know that, Professor, you using the hydrogel, cryogel, and these materials, porous materials, to remove the metal, but you will put in the soil again, not, but I don't know, I would like you remember that the cinetic situation, you remove it with interaction, the materials with the metal. But sometimes it's possible to change PG or something like that and remove the metals, okay? We study it a lot and remove and get the metals and remove it before we do the biodegradation situation. But the other point is very important situation. This is a very important area because we starting to work now that when this type of porous materials get the metal, it's so important to use it. I have two students working it, using these materials without remove the metals inside of these materials, but I use these materials for to catalyze some area that we observe some impact. Like, for instance, there's some region that's problem with gasoline. So they put this material, some area contaminated, and put this material with the metal and increase the oxidation of in this oxidation of gasoline, and to remove the contamination in that area. This is important studies that we are developing. So to understand a little bit, because our interesting, of course, you know that I had worked in a company, so I said for my students, Renan, we need to get some products, and Renan prepare some membranes, and he put the membranes in some devices, and prepare a little device to put in a system that to remove the chromium. And the first time in our lab, prepared the device. In this work, we prepared some membranes with nanocellulose, and it was so good because we characterized the size of the nanocellulose obtained by residues, of course, and looking for the behavior of it. After that, it's not so good, the results. So, but we changing a little bit about the nanocellulose structure. In this case, we put phosphate. When we put phosphate, it was so good, the results. We changed the surface of the materials, and the behavior of removal of the chromium is very high, 93%, when you put phosphate in hydroxyl of the cellulose. This is an organic reaction, simple organic reaction, and cheap, and then it's possible to obtain some device that remove chrome. And we observed that in this case we use some membrane and using PBAT, a biodegradable polymer, okay? So in this way, using some membrane, Rafaela prepared a pectin-based composites, and the same way, in this case, we prepared some this membrane, but we looked for the effect of the mechanical properties, because as I said, sometimes when you think in application, it's important to resist some pressure when during the use of the membrane, okay? And in this case, Rafaela prepared some membranes, And we observe the very good results mechanical, and we observed the kinetic model, and when we applied this and observed that the behavior and the dye source, and in this case we tested with dye currents, okay? And so dye sorption as function of the time and the different PEG, and observed that it's removing a lot of quantity of the ion. So, to conclude the modification, we tested a lot of additivos. And in this case, Noelle tested the curcumin for to put inside of membrane. It's very interesting because she prepared membranes using the AIPS and NIPS methodology, and different type of the methodology, and prepare in different content of nanocellulose, curcumin, and something like that. In this case, Noelle obtained the low content of used nanoclay and curcumin, and it was observed a very good membrane. And in this paper, we publish, we discuss about the price of the membrane. It's very cheaper. We obtain, because the biodegradable, when you thinking biodegradation or biodegradable polymer, it's so expensive. So I think it's very important we pay attention about the price. So in this case, we remove 28%, just 28% of the copper. So it's difficult because you say that's not so much, but when you look for the literature, it's okay. Okay, I finish. This case, we observe a lot of situation in this metal. Well, I think to conclude my presentation, it's possible to say that biodegradable sorption is important to understand the secondary sources of the effluents, and if you understand how can interact the ions with the porous materials, it's so important. So it's possible to regenerate the absorbent. We studied about a lot of things that, and it's important to analyze the impact of environmental. So I would like to show some a little about my experience, but I would like to thank you very much for my group, okay? And I would like to invite the UFABC. UFABC is very well located in São Paulo City, close to São Paulo City, and 45 kilometers international airport. There is, it's close to the beach, and there's a lot of very good place there, close to there. So thank you very much, Announce, for this opportunity to talk to you.
Thank you, Professor Rosa. In view of time, we have time for a couple of questions only.
In your experiment with chitosan, you got a selectivity for chromium, and you say that it is the electrostatic interaction between the ammonium and the oxyanions of chromium. If so, why there is selectivity? Because it can, in principle, attract any anions, not only chromates.
No, I think when you think in selective interaction, I think firstly we need to think in what the preferential fact is promote the interaction of the ion and materials. Of course, you know that there's chemical interaction and physio interaction, okay? If you observe, I talked about the size of the pores and the modification of the materials. Because sometimes it's very complicated to think in just one way. Sometimes it's important to close the pores and put a little group, chemical group, for to interact more with the ion. Now we are looking for to understand this situation, because maybe if you observe when you put phosphorus and you put amine groups, and it's changing. Of course, here I don't show all the results my group is doing, but we constructed some map that to understand this question. But we think that's the important thing to change some pores, but sometimes you modify the materials. Another point that is interesting, sometimes the interconnection of the pores, because sometimes when you apply the porous materials, they don't flow a lot. So it's complicated to use it in a practical situation.
Yeah, but when it is phosphorylated, you have completely negatively charged polymer actually.
Yes.
That time you are getting much selectivity than the ammonium case, 93%.
Yes.
So that's again surprising, right? If it is an anion-anion interaction.
Yes, this is the situation that I come to understand, because it's so difficult, because sometimes you protect the materials, because if you remember, we put the phosphate in cellulose, okay? But sometimes the materials, this cellulose is encapsulated, so it's not exposed to your group, okay? This is one other point that we are looking for.
One more question.
Sir, when you say porous material, how much surface area you are expecting for this kind of porous material? To say it as a porous material.
Okay, but we measure by using PET, okay, of course you know. But it depends of type of polymers. It's not easy to answer your questions, because sometimes I understood that the behavior of the materials changing. It's different when you work a PBET if you compare with gelatin. And the other point is that the cross-link agent changing the materials.
At least a range of surface area is there? No.
Yes, of course, yes.
Okay, one more question is that you are showing water uptake capacity of your material. So you have shown gravimetric results, like over the time how much weight gain it is happening. So are there some other techniques which we can characterize the water adsorption?
Yes. We have two methodology, okay? Sometimes use some kinetic to determine the kinetic methodology to determine this capacity, okay? And we establish some protocol in our lab, and then control this measure by chromatographic during some period, and then it's possible to calculate it.
Thank you, sir.
Okay.
Okay, as we are running late, we'll close the discussion now. I think Professor Rosa would be available for further discussions during lunch. Please join me in thanking Professor Rosa for a wonderful lecture. Thank you.
Dervaldo Santos Rosa for the lecture, and sincere thanks to Dr. Srijit Shankar for sharing wholeheartedly. Now, I request Dr. Srijit Shankar to kindly present the memento of appreciation to Professor Dr. Dervaldo Santos Rosa. I welcome Professor for receiving it. So please. Next, I call upon Dr. Senju Devasiguti to present a memento to Dr. Srijit Shankar as a token of love. I welcome Dr. Srijit to receive it. Thank you all. Kind attention, dear participants. The oral presentations will begin at sharp 1:30 p.m. in Professor Ada Yunath Hall near the Malicious Hall in the ground floor. Thank you.
It's a great pleasure having everyone here this afternoon. Let's begin the 6th plenary lecture of NTAC-2023, which will be delivered by Professor Dr. V.N. Rajashekharan Pillai on the topic Research and Innovation Opportunities in Applied Sciences. The session will be chaired by Professor Dr. Sunir C.V., University of Kerala. I am profusely elated to take an opportunity to introduce him to the gathering. Dr. Sunir C.V. joined as an assistant professor in the Department of Chemistry, University of Kerala in 2012. His research interests include photophysical properties of donor acceptor systems, photo-induced electron transfer, solar water splitting, solar energy conversion, and microporous organic polymer. He served as a research assistant professor at Kyushu University, Japan. He is a member of Indian Society for Radiation and Photochemical Science, Society for Polymer Science India, and Indian Association of Hydrogen Energy and Advanced Materials. So, on the behalf of one and all present here, let me extend a hearty welcome to you, sir.
You want to come here, finish? It's there, huh? Yeah, yes, it has been displayed. Yeah. No, I don't want this. This is all right. This is all right.
So I thank the organizers for inviting me to this conference. So in this session, we have a plenary lecture from a great personality, a stalwart of the Indian higher education system. So Professor V.N. Rajashekharan Pillai, and he is affectionately called as VNR. So I would like to give a brief biodata of Professor VNR Pillai. I think he has requested me to cut short the biodata because he has a very long biodata. So Professor V.N. Rajashekharan Pillai has been an actively a part of many higher education and scientific research establishment for the last 48 years of service. He has shown as a teacher, researcher, professor, and executive head of education, science and technology establishments in the country and abroad in these years. So I will just go to his credentials, here education and all. So he did his post-graduation in the year 1968 to 70 from NSS College, Pandalam, University of Kerala. And later he joined for his PhD studies at the Department of Chemistry, University of Kerala. And also he did his postdoc from the University of Tübingen, Mainz, Germany. He was also a visiting research professor at University of Louisiana, Switzerland. So he created an internationally renowned research group in the area of polymer-supported peptide synthesis, photoremovable protective groups, and conformational studies of peptides and proteins. He has trained more than 60 doctoral and postdoctoral researchers under his direct supervision. The top executive positions which he occupied include the Vice Chairmanship and Chairmanship of University Grant Commission, Government of India. He was the Executive Director of National Accreditation Assessment Committee, and he was the Vice Chancellor of Indira Gandhi National Open University and also Vice Chancellor of Mahatma Gandhi University, and also has the charge of the Cochin University of Science and Technology. He was also the Executive Vice President of Kerala State Council of Science and Technology, and he has many laurels others to his credit. So his lecture will be more applicable and will be interest of all the persons present here, because it's a very general talk, and it is titled as the Research and Innovation Opportunities in Applied Science or Chemistry Research. So I invite Professor V.N. Dasyan to deliver his plenary lecture. Thank you.
Teacher and researcher in the university system in the country for the last 52 years. My lecture is when the organizer invited me for this particular function, I said, chemistry is history for me, so what should I talk about? I am not doing any chemistry now directly. Therefore, I am not going to talk chemistry, formulas, research, nothing of the sort. But I am administrating and in the higher education system for more than 38 years in this country. I am thankful that this particular college has invited me to talk in this seminar, in this international conference on new trends in applied chemistry. When Dr. Gopalakrishnan asked me for a title, I told I will definitely not talk about applied chemistry alone, because I don't believe in classifying chemistry as pure chemistry, applied chemistry, and other chemistries. There is only knowledge and its application. But if you have the knowledge, you will also know how to apply it. If you have the basics of chemistry, and then the context of chemistry, then you will definitely know how to apply that chemistry. And therefore, of course, these are all convenient classifications, and you have seen during the last 2 days, you have seen international speakers speaking about the various advances which are happening in chemical sciences. The very vocabulary of chemistry has been changed, very vocabulary. When I started in 1971, the things which we used to say, they are totally different. Probably you may not even understand many of these words. Now you are adding several adjectives to all these things, and then of course again the basic chemistry, the fundamental laws of nature remains the same. No? Therefore, it is all chemistry. I am glad that large number of research scholars are participating in this activity. And during this on sideline discussions during yesterday and all that, I have seen good number of teachers, whom of course I have several of them I have taught also. Teachers working in the colleges and in the country, colleges in the state, in chemistry. And I have been coming to this college. The young students may not be knowing it. I have been coming to this college even before the Mahatma Gandhi University started. As an examiner in chemistry from Calicut University, I used to come to this college as an examiner in chemistry, proper practicals in chemistry. During those days, it was Kerala University. So as an external examiner from Calicut University, I used to come here into this college. So, to some extent, I know the in and out of the chemistry education system, chemistry higher education system in the state of Kerala. Of course, I worked outside Kerala also. Now I am heading a university, one of the very prominent private universities in the country, 80 years old, in Bombay, in the city of Mumbai. It's a corporate university, of course, as Vice Chancellor. So I told I cannot speak chemistry because I am not doing chemistry, even though I am teaching chemistry now, but I am not doing any chemistry now, teaching a few hours every week in the area of polymer science I teach even now. So I suggested that I will just speak about maybe some sort of a reflections on what are the things necessary for enhancing the quality and relevance of chemistry teaching in the universities and colleges in this country. And for the external, of course, Professor is only the external person right now here. For the external expert, Professor, it's also important to know that this country is going to have undergoing a paradigm shift in its approaches in science education, in approaches in science, in research, and in the national education, in the education policy also. We are going to convert almost 50,000 colleges in this country to universities, independent universities. That is the challenge before us. These colleges, for example, this college is much bigger than many of the universities in this country. This college is much bigger than. So we are going to convert in this country 50,000 colleges of this kind into universities of teaching, research, consultancy, extension, and all that. It is a huge challenge for a nation like this. Of course, there are also opportunities. And when we just talk about chemistry, I told that I will talk about the innovation opportunities in chemistry. I remember in my university, present university where I am working, in 2018, Professor Radha Yonath came and inaugurated 100 biology startups. We have chemistry startups also in large numbers. Of course, startups were usually in IT-related areas. That of course is continuing, but chemical startups, biology startups, innovations, all these things are going to be very important. It is therefore, for example, in this college itself, I just gathered through, during the tea break from our MSc students about the two courses, MSc Chemistry and MSc Applied Chemistry. You have 18 seats. You can correct me. You have 18 seats in chemistry and some 15 seats or 18 seats in applied chemistry also. And you have common course and all that. Now, even the premier institutions in this country, like ISIS, of course, Professor Suresh is there, they are also thinking of adding more to science, adding more, not just limiting to science, but adding more to science and science education and research in the premier institutions. And therefore, it is very important that even in our universities, our colleges, I said college, this college is this undergraduate teaching, postgraduate teaching, research, maybe some consultancy. You have a sister school, no? School is also run by sister school here, and social service activities. These are the things which have to come together, together in a university. That is when universities come up. Of course, I was also heading the National Assessment and Accreditation Council of the country, NAC. You might have seen three A certificates of your college in the college in the front. So, in assessment and accreditation, a lot of new things are happening. For example, when it comes to universities, the weightage for research is 40%. For when it comes to colleges, it is, I forgot about it, but I think it's about 20% or something for colleges. So, research has to be enhanced. Research as a component has to be enhanced. And research possibilities have to be enhanced. and more number of full-time research scholars need to be in the colleges, in the autonomous colleges. More research guides, more people who are taking up consultancy, looking at Cochin and what is happening in the industrial capital of Kerala. What are the things you can just look into as a chemistry researcher. This is the comprehensiveness of higher education. This is where we are going to. For example, you heard just now from the professor from Brazil about the hydrogels and its applications in metal removal and all that. Of course, every day we see, of course, from this coastal city, we hear about the marine pollution and lot of things, how these things can be utilized. Of course, I am also a trained polymer chemist. As I mentioned, I am not talking any chemistry. I am a trained polymer chemist, organic chemist and polymer scientist. So there are, if you have gone through all these papers and plenary lectures, you will see that science, chemical sciences extending its wings to various other areas. From Professor Tor, you heard about without understanding physics and all that, you will not be able to do much of the things in chemistry. Without understanding biology, without understanding basic sciences, life sciences, you may not be able to do much in chemistry. And chemistry has been an interdisciplinary science all the time. It is a central science bridging probably mathematics on the one side and the life sciences on the other side. Only when we mix these possibilities, that is adding to the context. But you should definitely study the basic. We should all teach and we should research. We should make the students study these things. Then only the chemistry education. Why I am saying this as a preamble? I know that I have 40 minutes, around 40 minutes, 35. Okay, it's all right. Okay, I will cut short because this is not going to be a very important. Conclusions. Nothing will be there. Inconclusive is the thing which are it will be. Anyway, it is very important that we should add maybe awareness about the other disciplines. Why I am saying that? For example, in the new university which I almost started, we advertised for 200 positions of full-time research scholars with a monthly stipend of 45,000 rupees. Chemistry full-time research scholars. We call them research and teaching assistants. But I did not get even 10 applications. That is one side of it. And then if you just look at the priorities of research, during the last several years, you can see that the priorities of research, not only in sciences, research has been considerably changed. For example, it is not just individual research which is getting supported. It is mission-oriented research which is going to be supported. Look at in this year's Nagpur Indian Science Congress policy document announced by the President. Look at the national education policy where research is supporting. You will see that I am telling all these things I know that large number of teachers are here. And large number of teachers from the collegiate and university education system in the country is here. And students who are going to come up. So there are excellent opportunities. Of course, whatever you are all doing, these are all wonderful work, no doubt about it. This has to be done. And this you do it with rigor but when each country, for example, this conference is supported by ACS to some extent, ACS and American Chemical Society and the other research society, UK yeah. So two chemistry top bodies in two countries, UK and USA. And ACS and the London Chemical Society every day publishes about the priorities of chemical research. What is the priority of chemical research in 2022? They publish it. And they do with a team of experts and analyze the trends and they say that this is the trend of chemistry research. Similarly, London Chemical Society also, English Chemical Society also, they also publish every country. And if you just look at our own documents, you will see what are the priorities of chemical research. And this is now happening not only in chemistry, other disciplines also, but I am limiting it to chemistry. So I thought of just mentioning some of these things, how just press it, no? Okay, so we'll say what are the things. For example, artificial intelligence and big data analysis is going to make a big change in chemical research. In the analysis, for example, in water research, in environmental sciences, in understanding pollution, in understanding ecology, the artificial intelligence and big data analytics is going to add to it. When you go for projects and all that, even now, people now ask, how you are going to apply this thing. For example, this is a great intervention in chemical research, which is, so I just extracted it from 5 countries' different priorities of chemical research, 5 different countries, professional societies. Professional societies, they have identified, and these are the challenges in chemistry research. For example, big data analytics. I am not an expert. Don't ask me any question on big data analytics or anything of the sort. But you know that big data analytics, artificial intelligence, in drug discovery, in molecular discovery, design of molecules, all these things, it is going to play a very good. And therefore, it is also very important in chemical education when it comes to postgraduate and undergraduate education. Please put the elements of this into these students. Even research scholars need to understand how the data can be better utilized. Data is the king, you know, there's a phrase, data is the king. So how your data are very important. You make lot of measurements. I have been just from morning onwards, I have been hearing the research scholars' presentations, excellent presentations. They have collected lot of data. Maybe even they may are not very sure about the ultimate application, but these data are very important. And then you will find some of your data being used by some people somewhere at any time. And therefore, analyzing this data and preserving this data, analyzing this data, making use of the technologies, computers in advanced computer science, artificial intelligence, and big data analysis is very important. And this is going to change the face of chemical research. It is changing the face of chemical research, but it is going to further change the face of chemical research. So, next generation active materials. Earlier we were just looking at natural products, isolation, characterization, and all the times. And then we were trying to mix natural products with artificial things. Now, Professor has mentioned how new things are, for example, bioconjugates. I mean, identify the active systems and then supporting on this thing, put all these things together. And there, of course, there is, we are looking at sustainability, biodegradability. The other day, this Friday and Saturday, Sunday, I was in Delhi. And Plast India, it's a big organization on Plast India exhibitions were doing it. Thousands of companies from all over the world coming to Pragati Maidan. And you should see the type of things which they are promoting and how, for example, new plastics can be designed, how the molecular systems which are necessary for creating the plastics can be designed, all these things. Of course, we also we have also similar organizations in India, ICPE, Indian Council for Plastics in Environment. If you just look at the latest cover page of CNGN, I don't know how you, of course, I am talking like a teacher now. Of course, you are all researchers, but it's very important. In the latest issue of Chemical Engineering, the cover page is about the new plastics. For example, people are trying to find out how the plastics can be sustained, sustainability in plastics. So new material, bioconjugate materials, new generation materials, and then new chemical strategies to modify hydrogens. You heard just now one. And or biocompatible methods to stabilize proteins and peptides. I worked in the area of peptides long ago. I worked with PEG bound peptides. How peptides hydrophobicity, when a peptide is a little bit more hydrophobic, by attaching polyethylene glycol to that peptide, how the hydrophobicity can be adjusted. And it was published in Accounts of Chemical Research long ago. It was all history, as I mentioned. So even now, this, of course, even in the 2 plenary lectures earlier, I heard about the use of peptides. Of course, yesterday, Professor Ada Yonath also mentioned about for example, how peptides are being synthesized. How, for example, these ribosomes can just design, probably small peptides are required in large numbers as medicine, small peptides. How peptides can be synthesized, peptide synthetic machines, ribosomal machines, artificial ribosomal machines for synthesis of peptides, all these things. People are working on it. These are all, now it's probably dream, but dream may come true in the years to come. So stabilized proteins and peptides, biomaterials are changing the detection and treatment of disease. In addition, engineered systems reveal new insights into biological processes. Artificial systems, you engineer systems and then try to compare with the natural process, including stem cell signaling, cellular motions, and tissue repair. These are all the current. For example, if you just look at this particular itself, you will see at least 65. I saw 65 articles in 2022 published as trends in this area. Trends in this area, and similarly, many applications in health strategies. So biomass and bio-waste thermochemical processing. For example, waste recycling is the most important, most serious agenda for each and every one of us. The other day, somebody was telling everybody, for example, I have to take care of my waste. Even in, of course, in Cochin, I read the news that people are not taking not taking care of their wastes. So it is going to be a big thing. And then new chemical reactions. Of course, we are going to hear further lectures on new chemistries. You are going to hear further lectures. How these new chemistries can contribute to maybe breaking of bonds in a neutral way, in a biocompatible, in a natural way with this thing. So we have to think about new thermochemical reactions, liquefaction technologies. For example, the solid waste can be converted to liquefaction technologies, catalytic upgrading. For example, we studied about catalysis. Some of the good papers were there. So what are all these things? These are all for this thing, refining, economic analysis, and other areas. So then of course we have been hearing about COVID for 2-3 years about the COVID, etc. But we have a year before COVID, tuberculosis was the most, probably the most prevalent disease in the whole world. And now you have seen the type of collaboration happen for developing COVID vaccines. Maybe we have to just think about such approaches in probably redefining strategies for TB-related medicine. So drug resistance, as Professor Yonath mentioned about the drug resistance and effectiveness of current treatments, and recent advances in drug discovery and diagnosis promise new efforts to combat this global threat, which may come back to forefront as a COVID resilience. This is also going to be, and lot of things are happening, and therefore lot of opportunities are there for all the researchers which you are doing in working further on this line. This, of course, in Kerala we have probably the smoking is reduced, but as a global problem, even now the smoking is a big threat to. If you see cigarettes, e-cigarettes, and cannabis, particularly are increasing the cases of lung injury cases. If you just look at the WHO reports, even now you can see that lung injury diseases arising out of these events are very large and alarming. And therefore, we have to just look at conventional and innovative chemical tools in understanding the toxicity of tobacco and its related products, as well as transformation of e-cigarette constituents and their use. These are all, you will think that, how am I going to contribute it? We are all contributing. I am contributing it, he is contributing it, he is contributing, everybody is contributing it. That is the way we have to work together and approach things. Of course, chemical industry. You hear about almost every day. Of course, I work in Mumbai. The hazard treatment of in industries. So lot of things are happening, and then we have to think about with the help of the new design strategies and that we have to think of new process and chemical industries which avoid which ensures process safety at all levels. I'm not going to. This is available. I am not going to read everything now. So, catalysis and global energy transition. Of course, you are also part of the green hydrogen policy or something. Somebody was mentioning. India in 2022 February we announced the green hydrogen or green ammonia policy. It has been read as green hydrogen or green ammonia policy because we are and you have a big document. You have a big document. You have to read about the newspapers in February 2022. It was announced. For example, this is going to be changed. It may even take a chemistry revolution in the sense that ammonia, production of ammonia, that's the basis of all agriculture. For example, all agricultural things are happening because of the ammonium sulfate and ammonia production. And when for example, when the process of ammonia, industrial process of ammonia is going to be changed, there is going to be a lot of chemical things. So the new hydrogen policy, and we have to understand development of efficient materials and devices. Probably when you think as a group and all that, you should also think about when you carry out synthesis, when you carry out new reactions, how exactly these green hydrogen or oblique ammonia policies. It is not only of India; it's all over the world. But we have we are some of the pioneers who drafted the policy and started implementing it. And then healthcare applied. Almost all the papers which you have discussed, you have a drug element there or treatment element there. Maybe again we have to just go back to the antifungal drug discovery also. Fungal diseases cause millions of deaths each year and can increase the morbidity of other bacteria and viral infections. So applied chemistry, healthcare, lot of things are happening. Without life science, without proper integration of life sciences into our applications, into our research, probably things may not be that application oriented. So tropical diseases, there are a number of neglected tropical diseases. For example, if you just look at numbers for these diseases, you will see millions of people with such disease also. But these are not really considered in a very big way. Probably we have to think of new medicine. This is the 2022 analysis, not my original thing, anything. This is not the 2022 analysis of the world. So search into new and refined diagnostic and treatment methods. New vaccines. Of course, we have seen during the COVID period how the scientists succeeded in developing vaccines. It was collaboration. When the national education policy was announced by the Prime Minister in February or March 2020, so I don't remember the exact date. On that day, I was hosting a meeting in Bombay. Dr. Kasturi Murugan was presiding. What will happen to the experimental research in the country if this COVID continues like that? Laboratories are closed, students are not coming to the laboratory, instruments are rusting. So 3 academies presidents were there. Kasturi Rangan was also there. And at 3 o'clock only he got a call from the Prime Minister when he was sitting there that the national education policy is going to be implemented. We were wondering about what will happen to experimental sciences during that. But then after that year, you know that Nature and Science publishes every March or February, I don't recollect. They publish the contributions of science, the status of scientific research. Every year they publish. And that was the year. The COVID year was the year which happened maximum collaborations in scientific achievements. maximum collaboration and maximum, and it was declared the year of science also, scientific research. The reason is people from all walks of life, irrespective of whether they are in a well-endowed institution or a small institution, whether he is from a small university or a small college, people collaborated in a very significant way, and that is, we have seen the results during the period, the development of new medicine, new vaccines, new treatment methods, whatever this is because of the collaboration. That is a strength. So we have to just look at the development of new vaccines for improving the quality of life and health management systems. Everything for such things in there. Probably such approaches, such stories can lead to much more effective collaborations in the years to come, and therefore we have to be. Am I audible? I don't have my. I'm audible, no? Can hear me, no? Thank you. So. Okay. So this is all. I just select 10 points there, 10 areas of collaboration. Then, of course, I will just 2 minutes more. We have the national. Yesterday, some teachers were asking me, because it is ultimately the implementation of anything can happen through teachers. And of course, Professor, we have a new education policy in the country, and it is called National Education Policy 2020, and it is going to be a big transformation as and when it is completely implemented. So a lot of importance is going to be given to research, how the institutions can be upgraded. So these are the two or three areas, because these are all our teachers and researchers in our collegiate and university system. I just thought of sharing, because I am also in the implementation committee of the National Education Policy as an academic. So several, maybe Karnataka started implementing, Maharashtra also started implementing it, and how the integrated program can be started. For example, this is a college. I am not advocating for the National Education Policy and implemented 4-year integrated, or the 2+ or the BSMS program. BSMS program is there in 40 institutions in the country as of now. Integrated BSMS programs. Of course, they are all well-endowed institutions. But this is also well-endowed institution, no doubt about it. You have our chemistry department, physics department, life sciences, all departments are humanities, social science, all these departments are there. So complementarity can be brought in. Multidisciplinarity in higher education can be brought in. For example, it is very important that a chemistry student should also understand a little bit of technology. And this multidisciplinary education was happening in this country in one or two premier institutions. I will tell about BITS Pilani. For how many years? More than 60, 70 years. Engineers should study all sciences. Similarly, chemistry people should study a little bit of engineering, machine drawing, computer, all these things. This was happening, and it is high time that our students get an opportunity to go the multidisciplinary, and then 4-year degree program and 1-year MSc program. To me, of course, I have been a vice chancellor and I have been an institution builder also. I don't see any difficulty, because you are already running 3+2 program. 3+2 is there. And then from there, if it is going to be 4+1, there is not going to be additional infrastructure. There is no necessity of immediate additional infrastructure or additional human resources. It is only a question of our adjustment to a new change. And if it worthwhile, try to do it. And then, of course, this Indian multiple entry and multiple exit. Okay. So that is of course, it was not considered as an academic thing in there, but a large number of students were dropping out in the country. And then in order to just give them, for example, they were dropped out, give them something, some certificate, that was the purpose. But this was happening, for example, in the US education system, in the community college system. This was happening. After 2 semesters, a certificate, 4 semesters, an associate diploma or associate degree, and after 6 semesters a degree, and after 8 semesters an honors degree. This is also happening in the country. And those who want to do after honors during the 4th year, if they are going to do one full-time year research only, they can directly go to the PhD. That advantage is also there. And MSc is only 1 year. And without an MSc, one can go after 4 years directly into research if they have taken up research in the last year. These are all advantages. Please note that out of 50 students, 5 may want it, 5 may require, 5 may benefit out of it, and that is very important. And others may go benefit by an exit. And therefore, we should not say, I'm not advocating anything. We should not say a no to anything. We should try to find out a way to find out how we can probably reap the benefits out of it. So these are some of the things which, of course, I mentioned. For all these things, funding will be a challenge for overall implementation of India. Then one more thing I will stop. For example, research is happening in the country, but quality of research, the number of papers, it is going. It should not be a factor. I do not know how there was one paper in Nature just a few days ago, paid authorship, big article in Nature about paid authorship, the several $1 million racket. I have the reference. So paid authorship, for example, paid authorship means not just a paid journal or anything. For example, I am not doing any research. I know that he is doing a wonderful research. I will be very friendly with him. I'm not taking an example. Can I just, I might have done something, discuss something. Can I get a name in your paper along with you for that authorship? Don't think this is happening in a big way, unimaginably big way. And this racket is there. And then in terms of, this is a very, very systematically run, really peer-reviewed paper, international conference. But there are international conference and international journals which are there, fly-by-night operators. You will see international conference in science, technology, medicine, humanities, social sciences, and all that. You can get a paper. Please see that. I am also recruiting large number of people. I have been part of recruitment of teachers at several universities and other institutions. And now, if somebody has one good number of papers and one paper in such fake journals and all that, that will be the end of the career of that youngster. And therefore, you have to be extremely careful in publishing. It is not in the number, it is in the quality. Of course, UGC has come out with that other extreme now. For PhD, they need not publish any paper. That should not be taken in that perspective. They can publish. When we were all doing PhD, there were no restrictions. Even now, in many premier institutions, there is no number and all that. But there are people who have submitted without paper, but who have done excellent research. One paper published PhD, excellent research. And just for the number game, not only for research scholars, but for the teachers also. I'm a teacher, so I have the right to address the teachers also. Just for form filling exercise, don't do anything. Just form filling and then ticking, and don't do anything. Of course, Assessment Accreditation Council, NIRF, that ranking, this ranking, they will all ask this. But please be sincere and please ensure that only high quality publications are coming out of each and every one of the research scholars from any institution. That is the way to quality improvement. And by doing research, you are going to benefit. For example, it is just because of the young research scholars doing research, you have an opportunity to come and meet up. You have an opportunity to come and meet up. And you are going to make a presentation somewhere, some university, maybe in India, outside. There are a lot of opportunities. These are great things for a research scholar. We have all reap the benefit out of it, and therefore be confident. I am an incorrigible optimist. I sincerely believe that the type of concentration, the type of focus which you are giving for teaching, research, and then of course the other components should also come seriously: consultancy, extension, community development, interacting with the community. you will accept. Thank you very much. I will not take any questions because this is not none of my research or anything. This is only a reflection from a teacher. Thank you. I jokingly said, but if they have any questions.
Thank you, Professor VNR, for that excellent, exciting, brief talk regarding the opportunities and challenges in chemistry research and other scientific research, and in linking that to the changing scenario of the higher education and research in the country and around the world. So, if you have any clarifications or if you have any questions particularly related to NEP, National Education Policy, you will get a teacher, students, you will get a first-hand information because you will be in the part of a policy making. So please, if you have any questions.
They are all ready for lunch.
I surprise you, okay? I have one question.
I am ready.
Okay. Thank you very much for your exciting reflections. I observed that you have a lot of experience, and so you said a lot of things that is so important for us. So sometimes you say something about we know, but we didn't it. Okay. You tell something a lot of subjects, but I would like to discuss with you. I have your opinion because sometimes you said about the number of the paper and a lot of things, but when and a lot of countries analyze some project and ask our CV and say, how many papers do you have here, the other things. You tell us about the other point that at the moment we needed to think in different way. We needed to work in multidisciplinary area, but we was born in some area, like we are in chemistry, okay? There is a language, chemistry, talk in specific language. When we are talking with biologists, people working in the biological, there's some difficult to talk because they don't understand what we are talking. So you say something about your that you think about the multidisciplinary, but I'd like to know how can we breaking this wall in this area, because sometimes we need to patience for to understand and to have to working together. So I'd like to know what your vision about this, because there is a lot of sometimes if you want to change in your mind and going up, we need to change. And so I would like to.
Yes, thank you very much. Of course, that is the hard reality. That's the hard reality. For example, of course, I don't know, but the question was clear. You have hearing the question. So every subject has its own vocabulary and language. That's the point. I also mentioned it. But not that vocabulary is going to be totally different. It has already transformed because of technology. Because of technology, that language. For example, there are mathematics postgraduates in this country, mathematics postgraduates, who retired as distinguished professors of chemistry. There are physics people who have retired as who has contributed as microbiologists. But in the higher education system, I was chairing the University Grants Commission of the country also. In the higher education system, even now, for example, he told 69 I got MSc, 68 I got MSc in chemistry from Kerala University. I cannot get a post other than as a lecturer in chemistry. Even now I apply because that is the qualification, basic qualification. And therefore now the new institution, for example, Suraj Institution, It is not just there, are you giving degrees in chemistry, physics and all that? No, it is in BS, it is in science. For example, degree, a postgraduate degree in science. If you know the international things, for example, a PhD is called doctorate in natural sciences in Germany. It is what there are natural sciences. So that division should slowly go. It's going, it is disappearing. And then in the processes during the last several years, you are asking about our country, last several years, we have created single discipline universities. For example, engineering university, Ayurvedic university, medical university. Now we are saying that they are not really universities. They should all come, other disciplines should come. I fully endorse the views that a university is a place which is open to people, open to ideas, open to differences, and open to places. And therefore, only if you say that we have got university education, we should have a doctor or engineer, a professor in a particular subject. They should also understand the human sciences, the social sciences, and other disciplines also. But specialization can go in one way. Maybe the language of talking to other disciplines, that also should change. I should understand the biology. I should understand mathematics. I should understand physics, the language of physics. I mean, not that I am going to master in that. I will be master in my own subject. I will be a chemist, but I should be able to assimilate the language of others. That is the multidisciplinarity which we are talking about.
Any other clarifications from Professor VNR? Any students or teachers?
Sir, the new things and advances in even chemical sciences and all in sciences, I think these advances are known to a few or minority belong to national institutes till now. Even in the local colleges, that means lot of talents are there. They are still unaware of these things that belong to, that means the advance in researchers and advances in various sciences happened in these things are, that means those people belong to these national institutes seriously involved in the curriculum making and syllabus making of local colleges. That means not.
What prevents them? They are doing it. For example, whenever I have contacted anybody in any national institution, I think it is what is it? It is our approach, and there are large number. For example, when you say about it, I am proud that if you just look at the ICERs and other national institutions, at a time more than 50% of students are from this part of the country in ICERs and all that. With Malayalam, I could survive in many of the ICERs outside Kerala because that is happening. Our school students, our school students. But the question, that is why I mentioned teachers. That's why I mentioned teachers. For example, it is very important if this college approaches any national institution in the country, if they are not responding, to tell me, I vouch anybody in the country, they will respond to you positively. That activity has to be taken by us, proactive. And it is happening. People will be happy to come over here. And that is why new institutions are emerging. New institutions are emerging. Our colleges are coming in a very big way. That's the message I wanted to give also. Thank you.
Okay. Question.
Thank you, sir, for the excellent lecture. As an extension to Professor Ebi's question, in my personal opinion, one thing that prevents colleges, even though there are excellent teachers, great infrastructure, everything that prevents students to get an exposure is the lack of research experience that they get. For instance, at least colleges in Kerala has a 2-month research project as part of their MSc program. So in this new educational policy, can we expect a change, at least a semester of hands-on project experience, whether be it in the...
I forgot your name? What's your name?
My name is Srijit.
So I started in 1983. I started even before the university. Mahatma Gandhi University was named. I was here part of the university. Okay. 1983 onwards, I used to send one full semester of the chemistry students to national laboratories and industry. 1983 onwards. Now, there is nothing which limits an autonomous. I was also chairing the committee on autonomous colleges long ago in English. So in autonomous colleges, there is nothing which prevents your students to go for one semester to a 2 semesters. I asked some of the students, I don't know whether they are all, 2 months, but one full semester. You are asking whether in the national education policy something is there. I mentioned that 1 year. Out of 4 years, 1 year you can send them to anywhere. Not only in this country, anywhere in the world. And that credit is getting transferred. We all started implementing. One full year they can. And then in the national education, I do not know whether this college has already taken part as the Academic Bank of Credits, ABC. No. Academic Bank of Credits, are you part of it? Okay. So 40% of the credits, yesterday I talked to you, it is not 20%. 40%, according to the news, for the autonomous colleges, university allows 20%. According to the national education policy, if I am a student, and if this is a university, I need to take only 60% of my total credits from this university. 40% of the credits can be from anywhere. It can be through Swayam, it can be through open and distance education learning, it can be 2 months in industry, it can be through an entrepreneurship, I saw an advertisement. So 40%, so out of 100, 40% credits can be earned from outside. And that means you have to create a network. You have to create an ecosystem which is working with this college. And that's why I mentioned you have an ecosystem. You have a college of social science, for example, even under the same management. You have a college of social work. Social work. You have a college of engineering. You have a hospital. You have a school. Many things they can do there also. But we have to, unless and until we do it, nobody else will. So to your precise question, the national education policy, one full year out of 4 years, if they want. One full year can be outside the institution.
Okay, so as we are running short of time, I think we will stop this session here right now. So if you want to interact with the Professor Wiener, he will be available here.
Or you can mail me and I will give you the model.
Okay, so please join me in thanking Professor Wiener for his excellent talk. Thank you. Thank you.
That was an insightful talk. I would like to thank all for your time and attention. I request Dr. Sunir CV to present the memento of appreciation to Professor Dr. V.N. Rajashekharan Pillai, and I kindly invite Professor Rajashekharan Pillai to receive the same. Now I invite Dr. Deepak D. Prabhu, Assistant Professor, Department of Chemistry, Sacred Heart College, Tevara, to present the memento to Professor Dr. Sunir CV, and I kindly request Dr. Sunir CV to receive the memento as a token of love. A few announcements. The oral presenters who have not submitted their presentations are requested to submit their presentations in pen drive to the technical team Dr. Jason M.J. and Kavita J. during the lunch break without any fail. The parallel session of oral presentations has started at 1:30 p.m. in Professor Ada E. Yonath Hall on the ground floor. I repeat, the parallel session of oral presentations has started at 1:30 p.m. in Professor Ada E. Yonath Hall on the ground floor. The poster presentation participants are requested to remove their posters from the poster boards during the lunch break. Now, we will have our lunch break, and I request everyone to gather back at 2:15 p.m. for the plenary lecture session delivered by Professor Dr. Kana M. Sureshan. Thank you.
Afternoon, one and all. I hope you all had a delicious lunch. Now, we are moving on to Plenary Lecture 7 of NTAC 2023, which will be delivered by Professor Dr. Kana M. Sureshan on the topic Crystalline Polymer via Topochemical Click Reaction. The session will be chaired by Dr. Srijit Shankar. I am very delighted to introduce the chair of the section, Dr. Srijit Shankar, Senior Scientist, Chemical Science and Technology Division, CSIR Nest, Thiruvananthapuram. He is one of the most prominent and reputed scientists in Kerala. He was a visiting scientist at the Weizmann Institute of Science, Israel, and a Humboldt Research Fellow at the University of Kiel, Germany. He joined CSIR Nest with a DST Inspire Faculty Award and later migrated to the Ramanujan Fellowship. He was appointed as Senior Scientist at CSIR Nest. Dr. Srijit Shankar has been recognized by several awards, including the Kerala State Young Scientist Award, 3rd BRICS Young Scientist Award representing India at 3rd BRICS Young Scientist Forum, Durban, South Africa. With immense pleasure, I invite Dr. Srijit Shankar to kindly chair the session. Welcome you, sir.
Thank you, and good afternoon to all of you. So it's my pleasure to introduce one of the celebrated scientists, teachers of the state, of the country for today's session, Professor Kana M. Sureshan. He obtained his PhD degree from the University of Pune, followed by a JSPS postdoctoral fellowship to work at the Heim University of Japan in 2002. Later, he moved to the United Kingdom and worked as a research officer at the Department of Pharmacy and Pharmacology at the University of Bath for a tenure of 2 years. In 2006, he was awarded the prestigious Alexander von Humboldt Fellowship, which he tenured at the Max Planck Institute for Molecular Physiology at Dortmund, Germany. In 2009, he returned to India to work as a senior scientist at the Institute of Life Sciences in Hyderabad, and after a rich expertise in the industrial sector, he took up the academic position as an assistant professor at ISET Thiruvananthapuram in 2014, where he is currently a full professor. He has been the head of the department and currently the Dean of Infrastructure and Planning. He has been recognized with a series of awards. The Innocentive Award from Innocentive USA. He designed the shortest route for the synthesis of a tubercularly in the context of India. In 2019, he received the prestigious Bhagyatara Award inspected by the Punjab University. He is also an elected fellow of the Indian Academy of Sciences and a recipient of the Technology Innovation Award instituted by Government of India in the year 2020. He has very recently received the Rajiv Goyal Prize in 2021 and has also been elected to the International Advisory Board of the prestigious journal Angewandte Chemie. He also serves as the editorial board member of a large number of journals, and he is also an official office bearer of the Humboldt Association Kerala chapter. And on a lighter note, it's a topic to debate whether Professor Sureshan is Sureshan the scientific speaker or Sureshan the public speaker. He, I think, has delivered the largest number of lectures after the Nobel Prize was awarded last year for click chemistry. And with this brief introduction, I invite Professor Sureshan for his lecture on the topic, crystalline polymers via topochemical reactions, click reactions. Thank you.
Hello. Thank you, Srijit, for that great introduction. And also I thank the organizers for giving me this chance to talk to you. I think, today we will be talking about polymers that are crystalline polymers. Normally, if you synthesize polymer in solution, what you get is an amorphous material, because the moment you evaporate the solvent, from the solution phase synthesis, you don't get a structured or very crystalline material. It will be amorphous material. But, of course, all of us know that crystallinity is orderness. Orderness gives a lot of properties to materials. So, we want to take that property, those properties from those orderness, if it is possible. I mean, can we make crystalline polymers? Is our question. So this is the idea here, because of course you cannot crystallize any polymer, because polymers are really large molecules and they have large degrees of motion. So because of which they can't polymerize for thermodynamic reasons. So the solution is, a possible solution is to crystallize the monomer and polymerize in the crystal itself. So you are doing the reaction in the crystal section. So you make monomer and crystallize in the polymer. That means you don't need solvent, you don't need any other catalyst or any other additive for polymerization. Just you need monomer crystals. So such reaction which happens in the crystal are called topochemical reactions. Okay. So this is the idea here. This I don't think this works. You can use this. Oh, great. So idea is here actually you take monomer, you consider this blue head and red head, they are complementary to each other. That means that once they are in proximity, they react. Of course, you should add features to the monomers in such a way that they assemble like this. The blue lobe will be proximal to the red lobe, the dumbbell I am talking about. Okay, the dumbbell lobe. There are some interactions, non-covalent interaction, because of which the red head and the blue head will be in proximity in the crystal lattice. If so, the reaction can happen on its own or some mild activation to give this kind of covalently linked polymer. So the challenge, of course, is to bring this kind of arrangement in the crystal lattice, having the blue head and red head, the complementary motifs at proximity in the crystal lattice. So such reactions, if it happens, you will get polymer in the crystal form. So this is the reaction which we are interested in. You know the click chemistry. Of course, this year click chemistry got Nobel Prize. So this is one of the click actually. So what you see, this is not click chemistry. This is only Huygens reaction. This is just a 2+3 cycloaddition reaction, dipolar cycloaddition reaction. Just like 4+2, the Diels are type reaction. This is another reaction, 2+3 reaction. So it's a thermal reaction. Actually, you get a mixture of two products depending on the orientation of this R1 and R2. It can be anti-parallel or parallel. If it is parallel, you get 1 5 disubstituted compound like this. If it is anti-parallel, you get 1 4 disubstituted compounds. So in actual reality, actually, there is no selectivity. If you heat these two monomers in solution, you don't get a selectivity at all. You get a mixture of both the products. So that reaction was Huygens reaction, discovered in 1960s, early 60s actually. So because of this gives two products, and people were not interested in this reaction at all actually. So this reaction was not used by people much actually, the Huygens reaction. But this problem of selectivity was later solved by copper catalyst. That's what the Nobel Prize was for this year's. This is behaving like, yeah. Why we are interested in this reaction is because there is a thermodynamic drive. There is a 65 kilocalorie per mole exothermic reaction it is. So there is a drive for the reaction to get to a lower state. The monomer can reach to a lower state if it reacts. Okay. So also, this is the transition state for the reaction actually, wherein the azide and alkane are at proximity, and also they are either parallel or anti-parallel, so that their orbital can overlap. These are pericyclic reactions. So orbital overlap is the feature which drives the reaction, right? So the orbital has to overlap. So this is the arrangement that is required, either this or that, parallel or anti-parallel. It cannot react when it is like this. There is no orbit overlap, for example. So this is the transition state. And if it is at this stage, it automatically reacts because it has to, it can release energy. It can get to a better place in terms of energy. So of course, this kind of arrangement is possible in crystals. You can get this kind of arrangement in crystal, because crystal, there are other reasons by which the groups are having limited mobility. And if you can lock the molecules, monomer molecules in such a conformation, you can do this reaction and you can get a polymer. So at the end of this one, I will learn Kathakali, because this is to change this one and that is to change that one, right? So the challenge is here. So you have to make a monomer crystal. This is one monomer. And azide and alkane has to be at proximity in the crystal lattice. Then we can get crystal of the polymer. This is the polymer actually, in which the two motifs reacted and you got the triazole linkage. Now something else happened. Again from beginning. Okay. So these, how do we design such molecules, such monomers? All these monomers, all these molecules are sugar-derived molecules. All of them have this diol actually. The two OHs I have marked in red. They're trans di-equatorial actually. And all of them have this kind of arrangement in their crystal lattice. All these crystal structures are known actually. So in other words, if you have this feature, this is bound to form this kind of arrangement in the crystal lattice. This is based on the crystal CCDC database search actually. These are all reported structures. Now, so if you have something like this diol functionality and azide and alkane, this is what we expect. If so, you can call it as a supramolecular fibril. And if you look along the fibril, this is what you see, because the fibril is going behind the screen. And in a crystal, of course, you'll have several such fibrils, because the crystal is 3D object actually. So several fibrils will be like this. And this is the most probable arrangement, because azide and alkane can have attractive interaction, because of which they can be at proximity. If so, I can do reaction along this direction and I can get polymer actually in this case. So this is the concept. So we made this material, we made this monomer, and this is the crystal of course, and this is the packing actually. As expected, it is forming this zigzag hydrogen bond. And in the other direction, this is in AB plane, and in C direction you can see the azide and alkane are at proximity in an anti-parallel fashion, just in a ready to react orientation. Now upon heating this one, it will, if you heat this at 90 degrees centigrade for a few hours, actually 24 hours, and you can redo the crystal structure again, you can see that the crystal structure is intact with this hydrogen bond there, no change at all. But what change has happened is this, there is a covalent reaction, covalent linkage, that is the triazole has formed from the azide and alkane. So monomer has become polymer in a single crystal to single crystal fashion. So it is a crystal to crystal reaction. So you take only monomer and you get the polymer. Sometimes you don't need to heat also. So this is what monomer you make and you get the polymer actually upon heating. Sometimes you don't need to heat, just keep at room temperature, it gives you the product. So this is some similar structure. This is called inositol, wherein you have only carbocyclic ring actually. There is no heterocycle there. There is no oxygen there. This is isomer of glucose actually, C6H12O6, but fully carbocyclic. And there naturally it cannot be polymerized because there is no electrophile and nucleophile in the system, unlike normal sugars. So we thought we can use the same strategy here. We can introduce an azide and alkane, and we have this essential feature which is the trans di-equatorial diol, two of them. So because you have two of them, this is what is expected. A 2D layer will form through hydrogen bond. And then between the layers will be stacked in 3D actually to make the crystal. And if that is the case, so the azide and alkane will be at proximity like this. If you say this is azide, this is alkane, between the layers they will be at proximity, then we can do reaction along the stacks and you can make polymer along this direction. So this is what we tried here, and this is what we have made. Again, I will not bore you with the synthesis of that. Very easy synthesis. And this diol, this is the crystal structure as expected. It is forming a 2D layer, hydrogen bond layer. And this is one layer, this is another layer. Between the layer, you can see azide and alkane are at proximity. They are talking to each other. Now, upon heating, they undergo reaction. Complete reaction actually. This is slow. Yeah. So 80 degrees centigrade for 6 days actually. If you heat, it's completely reacted to the polymer actually. And this is the polymer structure. Again, single crystal fashion. You can redo the structure of that polymer. So like this, we can do, we can do much more complex system. This is a disaccharide called trahallose. We can introduce an azide and alkane. And that also, I think I should stand here and that also reacts. That also crystallizes this disaccharide having azide and alkyne. That also crystallizes into two different forms from two different solvents. Then, of course, this is to show that they are two different. These are powder XRD spectrum showing that they are different crystal forms. In one form, you can see chloroform molecule actually. This is a solvate of the other one. And otherwise, it is very similar actually. So once the chloroform goes, this goes to the same state actually. Polymorph 2 becomes polymorph 1 actually. After the solvent escapes, it goes to this structure. And both reacts actually close to 93%. That means it's almost quantitative reaction, quantitative polymerization to give this kind of polymer of even complex system, which is a disaccharide. Our monomer itself is a disaccharide. And this is another system. This is also a sugar reduced form of sugar called mannitol. Mannitol derived compound having azide and alkane. In this case, there are two molecules in the asymmetric. In other words, there are two conformers of the molecule. In the solid state, there are two conformations for the molecule, two different conformations. You heard of chair and board for the cyclohexane, right? Those are conformers. So similarly, this molecule has a lot of flexible bonds actually, and because of which there are different conformers. In the crystal, there are two different conformers. And both the conformers, conformer A and conformer B, they are self-sorted. That means conformer A is always talking to conformer A. I mean, they are proximal to conformer A, conformer A, conformer A, conformer A. They are aligned like this. And conformer B is again self-sorted, of course. Conformer B, conformer B, conformer B. Now, interesting thing is that in conformer A, it is parallel actually. Azide and alkane are parallel. That means once they react, you will get 1,5-disubstituted triazole. And conformer B is anti-parallel like this. So that means once they react, you will get 1,4-disubstituted. So you are going to get two different linkages actually. And two polymers in the same crystal, one having 1,5 linkage, the other one is having 1,4 linkage. So this is what actually we got. We got a mixture of two polymers, 1:1 mixture. It's called blend of this one actually. Two molecules, two polymers in the same crystal. Anyway, that is not a planned research. That was an accident, good accident actually. Sometimes it happens in research. Now, if you think it's really good, but if you think it's a nuisance, sometimes you can think this is a nuisance because you want only this one, but you got this an additional product. Then how do you control? In solution state, we control the selectivity by changing the solvent, changing the catalyst, changing the condition, all those things, right? You can get selectivity by changing all this catalyst, all this condition. But in solid state reaction, you don't have solvent here. You don't have catalyst here. You don't have anything here other than the monomer crystal alone. So how do you change the selectivity if you want to? So that is the question here we are addressing. So this is an idea actually, the idea from one of my students actually, PhD student. So she said we can take an isosteric crystal. I mean, isosteric means similar size, right? Isosteric molecule, same steric molecule, right? Isosteric molecule. And it could be isomorphous also. Isomorphous means that they have similar crystal structure. So not only the chemical structure, but also the crystal structure. Isosteric and isomorphous. And if you have such isosteric crystal, there is a possibility that it will form isomorphous structure. So that means if you have something similar to this, that will also form similar crystals having two molecules in the symmetric unit, two conformers. But this is non-reactive. Actually, this is a dummy molecule, which is looking very similar to that, but it is not a reactive molecule. Then, if you have some similar system, you can take 1:1 mixture of this. Then, half of them will be the reactive, the one which is having head and tail, that is the reactive monomer. The other one is having only two heads actually. Or two heads means it cannot react. Head and tail only can react. So this is a dummy molecule, aligned dummy molecule. This is aligned monomer actually. So if such a co-crystal reacts, you get only one polymer. So this is how you solve the problem of selectivity in solid state. Make a co-crystal and polymerize. This is a good idea. I thought it will not work. I told her don't do this one, but she did not obey my order actually. She has done this actually without my knowledge, and it has worked. And it has worked, and I will tell you which molecule it is. So she has taken this molecule. You can see very similar. Actually, up to this, very similar. Only this alkane is replaced by azide, isosteric. Similar, steric size is similar. And this is the crystal structure of this. This is the crystal structure of that. Very similar packing, isomorphous now. Isosteric isomorphous structure. And she has combined this. This is the monomer. This is a dummy molecule. 1:1 she has taken, and this is what she got. She got a co-crystal as expected, and you can see the monomer crystal is aligned for polymerization at the top layer. This is a monomer crystal aligned for a reaction, and this is the dummy molecule. Dummy molecule of course cannot react, just as a space filler actually there in the crystal, that is. Again monomer, again, so this reacts. This is another form of the polymorphic form actually. So this also has an additional chloroform. Now once the chloroform goes, this goes to that again. So to save time, what I'm saying, this is the one we have to worry about now. It's co-crystal 1. So co-crystal 1 is having monomer aligned and the dummy molecule aligned. Monomer reacts, giving only one type. Here it is expected as 1,5-di substituted because parallel orientation. So, and that's what she got. It's reacting completely, of course. And finally what you get is a mixture of a polymer here. This is the initial, this is the initial one wherein you have two isomers. That is our problem. Now we have solved that one. In this case, this is the polymer, this is the dummy molecule. So in the crystal, so you have only one polymer. We initially had two polymer. By co-crystal, we have solved the problem of selectivity here actually. We got only one of the polymers. So of course now another system is nucleic acid. Nucleic acid is also highly, of course there was a talk actually in the morning or in the yesterday I think on nucleic acid. So this is also highly hydrogen bonded system. So this is again all our cytosine derivatives, known structures. All of them have very similar packing actually. This is the packing. They form a dimer because of this NHN hydrogen bonding, the pink hydrogen bond, this one, this kind of hydrogen bond, and they form a dimer. Then through NHO hydrogen bond, they form a molecular tape actually. This is all conserved in all these structures, non-structures. Now we want to use that cytosine as our guiding motif actually. Cytosine, C for cytosine, we take a cytosine derivative having an azide and alkane at the 5' and 3' of deoxyribose. Now, because of the cytosine dimerization, this is what is expected. Because of the azide alkane loving each other, this is what is expected. Then we can do reaction between these two, and we can make a DNA actually in the crystals. In a solid state DNA synthesis structure, of course homobasic. Of course it is a homobasic, only cytosine based DNA, wherein you don't have a phosphodiester linkage between the sugars, but a neutral triazolic linkage. So this is what the idea was. Yeah, this is the molecule we have made, having at 5' alkyne and 3' azide and the cytosine. This is the crystal structure, dimerization as expected, and also it's forming molecular tape along that direction as expected, and also it is bringing the azide and alkane at proximity. Then you can heat this molecule, this crystal, And you can see this is the monomer NMR, this is the polymer NMR. Polymer means the DNA actually. But this is really insoluble, and also the crystal breaks after the reaction. So because of which we could not get the final crystal structure. Nevertheless, we have other characterizations like MALDI and other characterization to show that it was the DNA polymer. This is a similar system, having only difference is having an extra benzoyl group here. Because of the benzoyl group, you have an additional pi-pi interaction between the molecule, and that brings it much more closer than the hydrogen bonding alone. So now the distance is much more closer, 3.1 and 3.5 angstrom unit between the termini, and they are in a ready to react orientation. Upon heating just at 60 degrees centigrade, it reacts completely to give the polymer. This is the DNA structure actually, wherein of course you have an extra benzoate. The phosphodiester is replaced by the triazole. Again, single crystal reaction. Next is of course proteins. Can we make protein-like molecules, pseudoproteins or protein mimics? Of course, this is our guiding principle. Of course, you take a small peptide, tripeptide, tetrapeptide, dipeptide, all those things, having this kind of head and tail. There are two possibilities for beta sheet forming peptides. It can be parallel beta sheets like that, all the head will be in the same direction in the stack, or anti-parallel, or in the stack adjacent molecules will be in opposite, head and tail will be opposite. This is anti-parallel, that is parallel. In either case, between the two stacks, the head and tail will be at proximity. Doesn't matter whether it is parallel or anti-parallel. This is one stack, this is another stack. Between the stack, head and tail are at proximity. Even in the parallel case, between the stacks, head and tail are at proximity. So that head and tail are our Z and alkane. Then this is what is expected. We are bringing the Z and alkane at proximity, then we can do reaction along this direction. We can get polymers of peptides, which you can say as pseudoproteins. So first system we have taken is this one, having a valine-alanine system. This is the crystal structure. You can see this is a parallel case. Azide and alkane between adjacent stacks are at proximity, and that reacts almost 90% upon heating. Of course, by IR also you can understand the reaction by the diminishing of this azide stretching frequency there, and it reacts almost completely, and you get the polymer up to 7 kilodalton size, up to 28 mer in MALDI. If you take GPC, it's much more bigger actually. So in MALDI, this is the problem. You don't see the higher mers actually in this case. So again, this is a crystal to crystal reaction. You can see from the powder XRD. Powder XRD shows sharp peaks, means it is crystalline. But unfortunately, we could not get the final structure. This is also optical, polarizing microscopy image actually before and after actually. The birefringent shows that it is single crystalline. If it is not single crystal, you can't see that birefringence. So it is a single crystal molecule, single crystal of the polymer, but unfortunately we couldn't take the crystal structure. The reason is here, because after the reaction, all of the crystals get twisted. All the crystals get twisted in right-handed helical fashion. All crystals are right-handed helically twisted. Now, why it is twisting to only one direction? So to address that, of course, these are made up of amino acid, which are chiral molecules, which are made up of amino acids. These are amino acids which are having a chirality L amino acids, right? Natural one are L amino acids. We started with LL dimer, both are L. Now we made the mirror image of that, and when we heated that, they are going to the opposite direction. You can say, I don't know, this light is disturbing actually. This is having about 9 twists actually in one crystal. This is another one, the optical, the mirror image of that, and that is having several twists actually. You can see the crystal is getting twisted in opposite direction. This experiment says that the molecular chirality has a say in which direction it has to twist actually. So first report of its kind actually. Also this makes a very good gel, this same molecule in different solvents and also water. And if you remove, what you get is a fibrillar material, which is you can call zero gel or aerogel. And that is also having a beta sheet kind of arrangement. Of course, that information you get from IR data. And that also reacts. But in this case, the reaction happens along the thickness of the fiber. You see the small fibers, right? So the thickness of the fiber, that is the direction in which the molecules are aligned for polymerization, not the length. So in other words, if I change the thickness of the fiber, if I can't change the thickness of the fiber, I can change the length of the polymer. Or in other words, I can change the degree of polymerization. Of course, changing the thickness of the fiber is easy in a gel. By changing the concentration of the gelator, you can make much more thicker fibers. So by changing the concentration, you can make the change the thickness of the fiber, by which you can also change the degree of polymerization. This is what we have shown in that paper. So this is another similar system, again diphenylalanine. This is forming a beta sheet. This is known to form beta sheet. This we have taken, and this is the crystal structure. And this is the packing diagram. You can see in this oval shape there are 2 alkanes and 2 azides. They are not in a ready to react orientation, but these are connected by flexible linkages. That means they can rotate and they can move a little bit and reach a orientation for reaction actually. If it reacts, there are 2 possibilities. The chain can be propagated along this direction or that direction. If you heat at 60 degrees centigrade for a few hours, it completely reacts. You can see the triazole peak, only one peak. Very selective reaction. And that reacts by rotation, as I have mentioned. This is the polymer structure. This has reacted in this direction. There are 2 possibilities. That way also it could have been possible, but the crystal has chosen this kind of propagation of polymerization. Now you see 2 dots there. This is water actually. These red dots are water. There was no water in the monomer molecule, monomer crystal. But during the reaction, it is creating space because of the motion. To fill that space, it's sucking water from atmosphere, dry atmosphere. There is a lot of water, right? The air we breathe has a lot of water. So this kind of material which can take water from atmosphere are of very high interest actually, because now people are interested in tapping atmospheric water. Currently, only 40% of the global population has water throughout the year. At least 1 month we don't have water. I mean, 60% of the global population. After 10 years, only 10% of the global population will have access to water throughout the year. This is the reality, and everyone felt that, and there is a lot of research going on in this direction, especially on MOF, metal organic frameworks, because metal can coordinate nicely with water. So such materials are being developed for harvesting atmospheric water. But the problem is when you use metal water linkage is much more stronger. That means to release that water you need more energy, heat. So that's not economical. So this is a pure organic polymer. There is no metal. And this water goes at very, very low temperature. Even at room temperature, this water can be tapped back. This is the data which shows that this is the TGA, thermogravimetric analysis at 50 degrees centigrade. This can be completely removed. Even at room temperature, this water can be removed by blowing air or nitrogen. So, and this can be repeated a number of times. We have done 30 cycles of hydration, dehydration. Each cycle takes only 6 minutes. Just remove water and keep outside, again it sucks in water. So it's not irreversible, it is reversible, and you can tap. This particular material can produce 18 liters of water per day per kilogram actually. And now you ask me about the relative humidity. Can it take water in the Gulf countries, for example, where the relative humidity is relatively poor? Yes, it can. This is the data. This is the relative humidity. Even at 30% relative humidity, it takes water. So anywhere in the globe, this kind of material can take water, absorb water from atmosphere. This is a possible application, but now not, because it's very costly. 1 kilogram of this material costs a few thousands actually. Okay. Yeah, so this is what? So this is a monomer, then that goes to polymerization that sucks in water, and you can tap that water in a single crystal fashion. We have also demonstrated in the lab tapping water, actually distilling water out of this material. Of course, these are different forms of carbon. Only difference is, of course, money. There is a lot of difference. 1 gram of the first one, you're a billionaire, or at least a millionaire. but this is such a cheap material, you will not get even 1 paise for 1 gram of that. Right, same material, but if you burn 1 gram of both, you will get same amount of carbon dioxide. What matters is only the packing. The packing dictates its property. Only the packing. So now, this is just a packing of a simple element that is called allotropes, right? Allotropism. When it is molecule, we call it as polymorphism. Different packing of a molecule is called polymorphism. So can we make polymorphs of the polymer? I already told you in the beginning when I started my lecture, crystallizing a polymer is impossible almost. Now you are asking me to crystallize a polymer into different forms. That is impossible of impossibles actually. So, but our system it's possible because you have seen that monomers can crystallize into different polymorphic forms. Right? This monomer, for example, it can give different crystals actually, different polymorphs of the monomer. And all of them are having this arrangement which require for the polymerization. And all of them reacts and you get different polymorphs, different, same polymer, but different polymorphic forms, different structural arrangement. This is anti-parallel chains. This is parallel chains with two conformers. This is only parallel chains with one conformer like that. 3 different structures we have made. Properties we are currently investigating. This is another system, glycine. So this kind of glycine, continuous glycine units are present in some of the natural proteins like natural silk. Silk is very strong because of this domain actually, this particular domain which is crystalline. So there are 2 possibilities of this kind of arrangement versus that kind of arrangement. That's called polyglycine 2. This is normal lamellar packing. That is a hexagonal packing. That is much more stronger. So we want to see whether introducing some triazole in place of one of the med bond, what happens, whether it goes to this or that. So we have made this dipeptide and tripeptide. This is di and the other one is tri. And here is the result. This is the dipeptide crystal ready to react in an anti-parallel fashion. Just keep the crystal at room temperature for a few days. You don't need to even heat actually. After some time it automatically transforms to polymer. Monomer automatically converts to polymer, actually the crystal. So actually this is not beta sheet, this is like this, crisscrossed, and because of which what you get is a cross-laminated polymer. That means one layer of polymer like this, next layer is perpendicular to that, again like this, it's a cross-laminated polymer. So this is a new topology in polymers we have introduced. And this is the other one, the next one, the tripeptide. This also has very similar arrangements, very similar distance, very similar arrangement, again cross-laminated polymer, 2 structures. So this is cross-laminated polymer. This is lamellar packing, this is cross-laminated. This is much more stable, of course you can see from this macroscopic image. So that stability you can see in the thermal degradation also. This is the structured polymer of polymer 1. This is the other polymer, tripeptide. Both decompose at very high temperature, about 400 degrees centigrade. If you take the same polymer, and if you make an amorphous material, very easy to make amorphous material. Take the crystalline polymer and dissolve in HF5P as a solvent, and evaporate the solvent, you get the same polymer, but in non-structured form or amorphous form. That decomposes at much lower temperature. So this shows that thermal stability is much better when it is structured. Of course, it has other properties also, which again we are currently investigating. Of course, we get very interesting structures like this. This is a glycine phenylalanine system which is having this kind of arrangement, because of which it gives a helical sheet actually. So it's not only beta sheet, also it's helical. Each chain is helical. So this kind of new topology actually. It's at the same time it is partially helical and also partially beta sheet like arrangement. Yeah, this is again very similar system. 2 hydrophobic amino acid you can see. Again that forms a twist-stack topology. So the crystal packing is such a way that the monomers are aligned for polymerization, but adjacent layers are twisted by 60 degree. Because that crystal packing is P61, the space group is P61. That means adjacent molecules are in the screw axis actually twisted by 60 degree. So instead of cross-laminated packing, you have a twist-stacked polymers actually in this case. Very simple. So essentially you can make polymers in solid form in different structures. most of the polymers we use for any application are in solid form. Solution we don't need, right, for any application. All the polymers we use, whether it is plastic or any other polymer, is in solid form. So we have to worry about the polymer structure in the solid form, not in the solution. So that's what I have shown. Some structures can be, we can have some control using this kind of chemistry. This is another example wherein I'll show you the result directly. So idea is here, you have to have the reaction head to tail like this, so the reaction is like this. Then you get this kind of beta meander structure. This is another form of protein structure, actually beta meander it is called. Beta sheet, again there is a sudden turn and again going back and forth. This is a very strained system because there is a turning actually. And this you can make in solid state. Once you dissolve, of course, this will not prefer that strained state. Then it will go to more stable alpha helical form, actually once in solution. Then you can remove the solvent, which is methanol. Then you get alpha helical form of that. So same crystal, same polymer, you can have beta meander versus alpha helical form. And the real example here is, of course, this is not by design again. We got this by accident. We just want to make the polymer of this one. This particular one, it was reacting like this. And we are getting that beta meander structure. And in solution, it is going to the helical form. You can see the CD data. Because of time, I'm going to the last slide actually. This is another reaction, new reaction which we have invented. This is teak reaction, topochemical enazide cycloaddition reaction. This is the alkyne, previous one. In this case, only alkene. This also gives a 5-membered ring. But only thing is that previously you get an aromatic triazole. Here you get a non-aromatic triazolene. Now this can easily eliminate a molecule of nitrogen and it can go to aziridine stage. So aziridine is very useful functionality in organic chemistry because it's a highly strained 3-membered system. Of course, you can activate that with a Lewis acid or otherwise, and you can open with a nucleophile. The aziridine ring can be opened with a nucleophile. Now, if this is part of a polymer, actually, this, for example, this is polymer. You are having this aziridine in the polymer backbone. In other words, your backbone can be modified. Even polymer backbone can be modified after the reaction. So that is the beauty of that reaction. So this is the structure. This is the structure having phenylalanine, azide and alkene. If you remember the watered one, this was having only difference is alkyne here and alkene here. So much difference. So such a simple change has a lot of difference actually. And this is having a very different, again P61 space group stacked, and it reacts in a single crystal fashion, giving triazolene, the new chemistry. And so you get crystal of this triazolene. Of course, you are doing this in a stereo-specific manner. You get only one chirality here because you are generating a chiral center during this reaction. Because of the chirality elsewhere, that is stereo-specific at that center. And of course, you can remove nitrogen from that by heating or by shining light, and you can get aziridine-linked polymer. This is another one, very similar to that. Similar one. In this case, what is happening is the molecules are helically arranged. Monomer molecules are helically arranged. Triazolene, alkene and azide, and that undergoes reaction and you get a helical covalent polymer. Helical non-covalent polymer becoming a helical covalent polymer. Helical covalent polymers are very important actually for a lot of applications, including chiral separation, for example, as a stationary phase for chiral chromatography, for example. So yeah, this is the again stereo-specific at this center, and we get this kind of chiral helical polymer, and you can see, I don't know, what you see is the bubbles, which is nitrogen actually. So the nitrogen is escaping from that crystal actually when you heat. This is in liquid actually, in a paraffin liquid actually. Oil, we have put the crystal and slightly heated, then you can see it's releasing nitrogen. Also shining light is fine. Then you get the aziridine-linked polymer. And that's what I have shown you what is topochemistries. I have shown you using sugars, the various sugars, you can make sugar kinds of polymers. Also we can make DNA kind of polymers. Also we can make protein-like polymers. And we also do other topochemistry. Today I don't have time for that. And of course, I don't do reactions. I only do talking. So these are the guys who do the reactions in my lab. These are the guys already left from the group. They are in different parts of the globe doing postdocs. And this is not really the current group. Yeah, yeah, he's almost about to go. He just finished. Otherwise, yes, these are MSc students. Those who are sitting are MSc students. I thank all of them, and also you, and also for the funding agency. Thank you very much.
Suresh, no doubt your outstanding journey since last 8 or 10 years. I have a question regarding when you make this myo-inositol based polymeric that stacking things. Actually, myo-inositol it is exist in the regioisomeric form. So I can suspect that when you form these polymers, maybe have you encountered any polymorphs, maybe one or two kind of polymorphs on it?
You mean this one? You're talking about isomers?
Yeah.
No, actually this is inositol has 9 different versions of inositols actually.
Yes.
So they are configuration isomers. They are different configurations. The OH is up or down, that sort.
Yeah.
So here we are making a rock like myo-inositol which cannot break the bond actually. So it's only bond formation happens at the azide and alkane. So the ring doesn't have, no change is happening. Ring oxygen actually. The oxygen connection, nothing is happening. So unless you break the CO bond, this
no, your azide and alkyne position are fixed, right? In the myo-inositol?
Yes. 5 and 2.
5 and
at the symmetric position.
2 and 5 position.
2 and 5 position. Because all are bond breaking cannot happen.
No, yeah. My worry is that if it is a silo, then there will be no problem, I guess. But
Silo also we have done. Silo also, Neo also we have done. Silo also we have done. There is no issue with there is no question of breaking the CO bond, right?
No question of breaking, but some kind of polymorphs means other pattern may be.
Polymorphs may be possible. Polymorphism is different. That is structural.
Yeah, structural integrity.
Different packing is possible. That we have not observed actually. So if you get, I got several in other cases different forms of the monomer actually. That's what he is asking. So we can get in any molecule different polymorphs actually. Structurally there is no same. There is no difference. Molecule is same, but they have different supramolecular structure. That's what is polymorphism. So that is possible.
And another thing that, as you mentioned, that you try to mimic some of the alpha helix or beta sheet structure in your pattern as a polymer. Is there any idea for use it as or mimic some of the biological system to address it?
The problem is that these are insoluble after this triazole linkage. We are getting very, very large polymer actually. So they are insoluble, almost insoluble in most of the cases, unless you use some HFIP or something. So in the real biological system, which is aqueous system, I think it's a challenge as of now. Solubility is an issue. But other applications like the water harvesting, and also we have something about which I have not told today, which is a mimic of collagen actually, which can take 1.6 million times its own weight actually. That is the record actually. 1.6 million times, that means 16 lakh times its own weight. So such a strong material we have. So such a material application we can think of. I don't think biology yet. Maybe for implants we are thinking the same material which we are collaborating with Sri Chitra to make bone implants actually. This is much more stronger than bone.
For extension, that interaction, that means the strand interaction, non-bonding interactions, similar to biological system, other than this hydrogen bonding, any other non-bonding like alkane or pi-alkane, you mimic the nucleotide system, that is the bonding of non-bonding interaction between these two strands, or then you mimic the peptide systems. What about the nature of that interactions? It is similar to biological systems?
Yeah, mainly the main driving force is the the hydrogen bond. In all our system is hydrogen bond is the main point. Of course, there are other participating CHO, NHO, sorry, not NHO, CHO, and of course van der Waals interaction. All those things are there. Of course, it is there. I mean, only crystallographic evidence. We can do NMR, but we are not interested in that particular aspect.
Do these polymers have a permanent porosity? If so, whether we can use that pores for applications?
I mean, porosity is the one which has taken water, very small porosity.
Okay, so again, something like conductivity or columnar conductivity.
We are trying to do the conductivity in this water form. We have a new faculty joined who is interested in studying the conductivity protein. So we have a much better system, a pseudo protein which is having a water channel. So we are collaborating with it because we don't have expertise in this conductivity experiment. That we are trying. Also, PSO electricity we are trying. By applying pressure, we can generate electricity from this kind of peptide polymers.
Okay. And you have shown one chiral polymer, and why you cannot get a single crystal data for the chiral crystalline polymer?
We got that.
You got
the last one.
Last one, yeah. Okay, it was there. Okay, and also these non-covalent interactions actually favors the formation of the covalent bond, and still in the polymer, those interactions actually maintains the crystallinity, right?
Yes. In most of the non-covalent interactions in that there is slight change in positions actually. For example, NHO hydrogen bond, the position of this NH and oxygen, slight change there. The hydrogen bond is still there.
Okay, it is there. Okay, sir. Thank you.
Sir, this is in continuation of that porosity and utilization. So in one of the earlier work where I think Hema utilized that diazo system, where at the end we get the monomer is trapped in the pores. So suppose if we have any other different molecule, I mean that pores are how much diverse in accommodating molecules with different functional groups?
Yeah, that's a very good question, and maybe I should have told when the question was asked about the porosity, that Hema's examples of that particular one, you can make porosity by washing off that particular monomer. If you put that crystal in solution, monomer only will dissolve and you get porosity actually. But what that porosity is, that I don't know, I did not check that, but it is porosity. Other molecules we did not try because we have to have this isomorphous structure.
If the solvent undergoes slow dissolution, it may slowly release also in that cases.
Yeah.
Okay, thanks.
We can have one last question from the students. Okay, if there are no more questions, please join me in thanking Professor Sureshan for a wonderful lecture. Thank you.
It was a valuable and very informative session. I hope all of you got a great knowledge about the topic crystalline polymer via topochemical click reaction. I would like to thank Dr. Kanam Sureshan for the valuable session, and I also thank the chair of the session, Dr. Srijit Shankar. Now, I request Dr. Srijit Shankar to present a memento to Professor Dr. Kanam Sureshan as a symbol of honor, and I also request Professor Dr. Kanam Sureshan to receive the same. I also request Dr. Shalomon Kiti, Assistant Professor, Department of Chemistry, Sacred Heart College, Devra, to hand over the memento to Dr. Srijit Shankar as a token of love. Thank you all.
Next, we are entering into our 8th plenary lecture on the topic Recent Advances in Cancer Nanotheranostics using Surface Enhanced Raman Spectroscopy by Professor Dr. Kaustubh Kumar Methi. This session will be chaired by Dr. Franklin John, Head of the Department of Chemistry, Sacred Heart College, Tevara. It's my pleasure to introduce him to the gathering. He is a recipient of the well-acclaimed NIH postdoctoral fellowship at Johns Hopkins University, USA. Some of his major research interests are nanosystems for anti-cancer drug delivery, organic synthesis of thioureas, and ketene imines for inhibition of non-homologous end of double-stranded DNA. He has research collaborations with various universities that include Indian Institute of Science, Bangalore, Cochin University of Science and Technology, and SRTM University, Maharashtra. He is a visiting faculty at Department of Marine Biotechnology, CUSAT, and also serves as a coordination committee member of Marine Extracts and Genetic Resources of Bioactive Molecules, Department of Marine Biology, CUSAT. He has received various awards and honors, including that fellowship and Kairali Research Award for the Best Researcher from State Government of Kerala. May I request Dr. Franklin John to please chair the session.
Good afternoon. It's my pleasure and privilege to introduce Dr. Kaustubh Kumar Methi for the plenary session for today afternoon. I met him a few years back, and I recall him and as a soft-spoken scientist. He did his master's and PhD from University of Calcutta, and he started his career in the industry and later on went for postdoctoral fellowship at Postdoc, South Korea, and University of Georgia at the very famous Complex Carbohydrate Research Center with the G.J. Boone's group. And as a carbohydrate chemist, I would say this is one of the prestigious centers of excellence in carbohydrate research. And Dr. Methi joined back to industry research, and later on he joined NIST Trivandrum, and now he's a senior principal scientist and professor at CSIR National Institute for Interdisciplinary Science and Technology, Chemical Sciences and Technology Division. He has received many distinguished awards during his career. To mention a few of them, he received the Service Excellence Award from Singapore Bioimaging Consortium, A-Star Singapore, CSIR Technology Award, Ministry of Science and Technology, Government of India. He has many international publications, 14 patents, and having a high H index for his research accomplishments. He's working on cancer diagnostic tools, especially surface enhanced Raman spectroscopic probe. And I'm extremely glad that I could also associate with some of his research work to develop SCRS probes. It's my pleasure and privilege, and I welcome you, Professor Dr. Kaustubh Kumar Methi. The platform is for you. Thank you.
Thank you, Dr. Franklin. At the outset, I'd like to thank organizers, especially Dr. Ramakrishnan and Dr. Franklin for inviting me in this conference. What I want to talk about, I think a lot of chemistry demonstration has been shown by Professor Sureshan, and it is kind of more or less application-based work which I try to accomplish last 10 years in CSR NIST. All of you know that a lot of diagnostics tools are already developed and it is already in clinics, but discovery of Raman spectroscopy and its advanced form of the Raman scattering, which is called the surface enhanced Raman scattering, and its biomedical application, especially its biomedical application, starts from 2020 onwards. So its recent journey, I like to elaborate, and which already established and which is already in pipeline. So before I going to start particularly this topic, I just show you what is actually we are doing in my group, what kind of areas we are covering. So this is our, actually we are having a chemical biology group, and mostly we are focusing in 4 major areas. One is the diagnostics and digital health. Actually now the trend is coming, as Professor Biener is telling, that the new modality of education is coming in interdisciplinary fashions. So the digital health, everything, every diagnosis will be in your palm. So that is the concept is coming. So in this area we are working, and mostly the therapeutic area we are covering usually on the cancer and the neurodegenerative disorders, and we are using the modality of Raman spectroscopy as well as the fluorescence. Another area we are working on the multimodality drug delivery system development, which is the coin today, the theranostics. Theranostics is a combination of therapy and diagnosis in a single nano construct, and the progression of the therapy is to be monitored by the different diagnostic modalities. In this area, we are working in multimodal therapy. Actually, we know that the chemo, radio, and surgery are the most prevalent therapies for the cancer. But now, apart from that, there is a combination of chemo and photo, chemo and immuno is coming up, which coming is a personalized medicine modality. So this area we are addressing some extent some of the challenging problems. Apart from that, in the area of medicinal chemistry, we are working new phytochemical entities. You have heard about the new chemical entities, NCEs, but we try to coin it using the phytomolecules as a active core and to make it semisynthetic modifications to new branch of active molecules, which is called the new phytochemical entities. So we are trying to promote new phytochemical entities, mostly addressing to the anti-cancer hits. And another most important area, as a carbohydrate chemist, I also think about to work on the glycobiology, and there we have also initiated some of the challenging problems, as Professor Sureshan mentioned that regarding the click chemistry. Last year Nobel Prize got Caroline Bartuzzi, which is first developed using the click chemistry the glycan imbalance or glycan positions in the cell surface, and that is discovered in, and the first paper is published in Nature in 2000, and the recognition comes last year with this novel idea of recognizing the glycans through click chemistry. So we are also addressed in this area some extent. I will show some of the examples on this work. So outline my talk covers mostly the, as mentioned, the surface enhanced Raman spectroscopy or surface enhanced Raman scattering. What is actually called the surface? What is the this terminology comes? How from it is terminology comes from the Raman spectroscopy, and this search. If you work on the search, there is few of the keywords and few of the techniques you need to know initially before it comes out to the application side. So I will cover some extents of the search substrate and what is called the search tags, and then its biomedical applications. Mostly I'm covering the detection of the cancers with different cancer biomarkers, how precisely it can be detected, and before that the general concept of the cancer nanotheranostics. It is very important to know the applications, when you do work in the cancer nanotheranostics, how the nanotechnology tuned in the nanotheranostics, that also will be covered in some general concepts. Then I will show you about some of the diagnostics modality and imaging modality through the SERS modality, and SERS used as a event theranostics, more therapy as well as the diagnosis, and our development of the portable Raman spectrometer, which we have attempted in CSIR that fashion. So as the onset, you know, the inelastic scattering of photon is called the Raman scattering, which is discovered in long back 1928. But you know that this scattering, Raman scattering, inherently is very weak. As it is inelastic scattering, very few, 1 upon 1 million, one particle or one photon can be coming as an inelastic photon. So this weak inherent Raman scattering maybe inhibit many of the detection modalities, and eventually in 1974 one British scientist, Felsman, what he found that it is just kind of serendipity. He tried to observe the Raman fingerprint or Raman scattering from the pyridine molecule, and he suddenly absorbed in the silver electrode and put it in the pyridine molecule on it, and he find that there is a huge enhancement of the Raman fingerprint of the ring breathing vibrations of the pyridine. And this historical achievement or historical development comes is a huge advantage, mostly in the area of the biomedical applications. And this certain enhancement of the Raman scattering or bare Raman scattering is called the enhanced Raman scattering or surface enhanced Raman scattering. So you need a surface which should be a nanodiaphan surface which can enhance the Raman scattering quite a huge amount, and it is generally around 10⁶ to 14-fold enhancement can be occurred. So in principle, the idea and the mechanism of the surface enhanced Raman scattering based on the two ways, one is the electromagnetic scattering and other is the chemical enhancement. But in these two coincide, actually what happened when the light introduced to the hotspot of metal nanodiaphan surface. So these plasmonic coupling nanoparticles, when comes in a nanometer gap size, and then there is a huge electromagnetic enhancement occurs, which eventually enhance the Raman fingerprint of the particular molecules in its either in a ring breathing or any kind of functional moieties. So that is the idea of getting enhanced Raman scattering. For that we need a metallic nanodiaphan surface and the molecule of interest on it. It should be positioned in a hotspot regions. So how it can be enhanced? If you see your interest of analyte is here, here and here. So when it is coming in a plasmonic band gap or plasmonic position, so you can get the enhanced signal compared to the other positions. So positioning to the analyte in a plasmonic hotspot regions gives that enhancement due to these two mechanisms. One is the electromagnetic and one is the chemical enhancement. So for that there are lots of Raman substrate, or it is called the SERS substrate, are developed, mostly colloidal nanoparticles or nanoparticles in other forms can be used as a SERS substrate. Silver, copper, nickel nanoparticles also used as a SERS substrate. So different shapes and their orientations can be used as a SERS substrate for getting this enhancement. So as I mentioned, if you know about the area of biomedical applications in the SERS, you need to know some of the keywords. One of the keywords is called the SERS tags. So SERS tags means if you want to detect certain bioanalytes, you need to prepare a SERS nanoparticle tag. SERS nanoparticle, suppose you are taking a gold nanoparticles, it should have two ways. I just show you in the next slide how the tags is prepared. But eventually, if you incorporate a Raman enhancer or Raman reporter molecules, which having some specific fingerprint, which can be used as a marker peak to be incorporated in the nanoparticle, and then this nanoparticle can be established or stabilized with some biocompatible polymer so that there will be no leach out of the Raman reporter, and then it should be conjugated some of the targeting moieties. Either it should be a monoclonal antibodies or in a aptamer or in a target specific proteins. So whole conjugates is called the search tags. So it is like that, where you can conjugate a monoclonal antibody, actually the antibody which can recognize the particular antigens of interest, that can be incorporated through a bioconjugation and with a specific chemistry, and that can be incorporated in the surface of the nanoparticles. So this is called the search tags, which eventually used to detect the different kinds of bioanalytes and specific proteins. So there are two ways we can use this Raman substrates or search substrates. One is the level-free search, where the nanoparticles can be incorporate any kind of interest of molecules. Either it should be any kind of biomolecules or pathogens which come in contact with the nanoparticles. So you can see when it is come in the contact, direct contact, certain molecular fingerprint can be evolved because of the certain orientation of the hotspot, and that can be tracked. So this is called the level free. On the other hand, if you have the search tags, means what I said in the earlier, that the nanoparticles should be conjugated with the Raman reporter as well as the specific targeting moieties. Either it is a monoclonal antibody or it is a specific protein. So that can be used as a search tag that can eventually capture the protein of interest or analyte of interest through a sandwich complex. So that way we also detect the bioanalytes or biomarkers. So this is called the search levels. So level based and the level free, two are the two techniques to detect through the any kind of bioanalytes of interest. So if you see the total spectra of the Raman fingerprint, if you think about in a biological window, mostly the fingerprint region is like that, where you can specific region you may group it for the fingerprint specific to the DNA, proteins, DNA lipid in combinations, lipids and DNA lipid and proteins. So this art can be tracked very minorly even in the naked eye, or what Professor Wiener said that is a coming in the new technique using the Raman. It is called the artificial intelligence. I am telling you about the artificial intelligence on it. So the raw Raman spectra, which can be grouped here, or certain molecular fingerprint can be tracked. Like that I am telling you, here you can see the peak around 1000. Actually it is the ring breathing vibration of the phenylalanine. So any kind of bioanalytes, you can easily track the position of the phenylalanine around 1007. That peak can be tracked and you can easily track on it. So the idea is that if you can group the Raman fingerprint from whole the spectral region, and there is the ways which can be utilized to further or make it more classified form, you can detect it through level free. So what is that? It is called the chemometries. Chemometries is a smaller version of artificial intelligence. So where actually it is a science where the chemical system and the data-driven means are come together. So whatever the spectra you have grouped, that can be processed in a different mode of this processing software, and you can classify it in a supervised model, and you can make a different classification groups. Small change of the Raman fingerprint, either the peak shift or the peak intensity or new peaks coming to appear, you can easily make a group, and these classifications can give you a clear idea about the grades or disease which are the stages. So eventually this is the ways for the grouping of this Raman fingerprint can be classified, and after this, when it is coming in the data driven means, there are many kind of multivariate analysis is there which is clubbed through the spectra and which will give you a better classification model. The classification model will be like that, where you have the bunch of Raman spectra of 3 different grades. One is the normal, one is the disease grade 1, disease grade 2. So you have 3 grades of Raman spectra which can be classified and which can be grouped in this pattern, and then when you validate this one, certain kind of unknown samples or unknown Raman spectra, if you get it, then you can easily match this unknown sample which fall which groups. That is the beauty of the chemometry as well as this new version of the artificial intelligence. So where actually what we can analyze as a retrospective analysis of the patient samples means the patient samples which is exclusively given as an unknown. This kind of samples is called the retrospective patient samples, which can be accordingly grouped in different ways. One way is you can easily group the severity of the disease. The disease may be mild, moderate, or severe. So that can be grouped using this spectroscopic technique, which is clubbed through the chemometric model. So this is one of the huge applications coming up nowadays using this chemometry as well as the Raman fingerprint analysis. So in biomedical applications, what I'm going to talk about, actually if you see that last 6 to 7 years, there is a huge work has been done in this advancement of the search in the biomedical applications. One is the clinical detections of the diagnosis, monitoring of the cancer therapies in different grades, and also the dissection in surgical dissections, the patterns of the progressions of the cancers can be detected through the Raman fingerprint analysis of the certain kind of biomolecules which is eventually upregulated or downregulated in the course of this disease progressions. And then definitely the monitorings of the molecular events, pathogen detections, and definitely the biosensing and imaging. So the area is hugely propagated in these all domains, especially in the biomedical application, where this surface enhanced Raman spectroscopy is now propagating hugely, and it is clubbing now with the artificial intelligence. So actually this paper is published in 2020. It is a review, and around, if you see that one, around more than 50 authors are around the globe are there. Actually they sat together and evaluate the past and the future of these techniques, or past and the future of this history. So one interesting sentence they put up in the abstract, actually that is, as I mentioned, that it is discovered in the 70s. So 45 years since the discovery of the SARS, it blossomed as a rich area of research and technology. But definitely additional efforts are still needed to become it is a routinely used analytical and commercial products. Actually it is coming another 5 years time, definitely it is coming as a well-known practice in the pathology or clinics, where this can be clubbed with the artificial intelligence. Actually all of you know that Professor Richard Van Duyn, who we lost during this just before the COVID, and with his memory this review is written, and it is hugely, especially I request the student community to see that one, and you can see the journey, how it starts and how it is evolved is the coming days. And apart from the SATs, as I mentioned, I am going to talk about mostly the ACRS based applications in the cancer diagnosis and mostly other diseases. So there are several other modules of this enhanced Raman spectroscopy are already in place, and there are a few of them and which can be used, out of which the stimulated Raman spectroscopy, which is now parallelly working with the SATs, now it is coming up. So we are also planning to establish the stimulated Raman spectroscopy, which can come as a better precision in terms of the detection. So that is also coming up in time course. So now, as I mentioned, I will talk about some of the general aspects of the cancer nanotheranostics. But before that, if you think about how the nanotechnology is evolved, especially in the biomedical applications, you need to know how this nanoparticles and how it can be modulated. So this review, just if you go through, you can get an idea about the evolutions of the nanoparticles, which we can make it as one of the best bioanalytical tool or tags. Then you need to know about the size. Size already well defined. It should be generally, if you make an ideal diagnostics probe, it should be within 100 nanometer, or you can go extend little more, but within this range it will be the best way to make it. And definitely you have to modulate the surface shape, and it is the materials what we want to take it and the size. So these are the components are very, very essential to make a tags which can be evolved in a theranostic probe development. So in order to make a more precise theranostic probe, there are certain challenges are there. Just I will read out and I will come out from this one. So if you make a nanotheranostics probes, there are three major things. One is the biomedical payload, carrier, and the surface modifier. So this is your kind of nanomedicines or nanotherapeutic probe, where you have to come up with the biomedical payload, which to be a therapeutic drug, or in combinations any of the drug or any of the potent other therapeutic moieties like genes or siRNAs which can be clubbed, along with some of the targeting moieties and along with the spacer and the carriers. These are the well-known components that can be tuned as per your requirement of the theranostics probe. So in case of the biomedical payload, that means the theranostic molecules which having a therapeutic modality, generally it is two ways, either it is the imaging agents or the therapeutic agents. So it is like that, the imaging and therapeutic agents should be clubbed here, and the progressions of the disease you can easily track through the imaging agent. So it is kind of real-time monitoring of the disease progressions, which you have to think about or imagine. Our nanomedicine should be like that, where both the things are coexist together and it can be solved in real time. And these are the imaging modalities, all are well known. But what I want to show you that apart from that, ACRS is coming out as another alternative imaging modality. So that I'll show you in the next few slides. So regarding the therapeutic agents, generally we know that the chemotherapy, which is very well known. But apart from that, have you heard about the antibody drug conjugate, that is the ADC? That can be used as another modality. Then targeted gene therapy, hormone therapy, and other therapeutic modalities combinations which can be utilized in a cancer nanotheranostics or theranostic probes. But before that, when you talk about the cancer, there are 10 hallmarks of the cancer so far established to know how disease can be progressed. And on that basis, if you can pick from any of this hallmark, and you can usually choose which kind of therapies to be given or which can be therapeutic modality to be chosen for that one. So that is the idea of making the therapeutic agents. And in the nanotheranostics, actually, as I mentioned in the last things, mostly the chemo, radio, and surgery, that are the most established therapeutic modality has been proven. But apart from that, so these are the therapeutic options which we can use in a theranostic way in combinations, coming from the immunotherapy to the hormone therapy. And also there are other modalities also encountered here. But apart from that, when I talk about the nanocarriers, then one of the most important things is the carriers. So these carriers may be either polymeric, lipid, dendrimers, or the inorganic carriers. So when you think about the therapeutic modality which you want to develop, so when you talk about the organic nanocarriers, it should be the polymeric or lipid bilayer, and there we can introduce the payloads inside it, and we have to use the hydrophobic and hydrophilic balance on this payload. So that is the one area to make it. Either it will be a nanocapsules or nanomatrix or micelles or dendrimers. So far these are the well-established theranostics probes to be developed. And if you consider the inorganic nanocarriers, it will be a hollow nanoparticles, and other it will be mesoporous nanoparticles, and the carbon tubes or carbon dots, which is now established to be a good modality of the carriers. So there are many reasons where you can use to get these nanocarriers to the target site. That means the nanocarriers to be in the more towards the tumor site. In order to make it more to the tumor site, there are certain points to be noted. One is that it needs to be highly soluble in the blood. It should be not removed from the RES uptake, and it should have optimum size range and the biocompatibility. So that can be utilized by using this spacer module. So that can be used in the surface of these nanocarriers. And in the biological barriers, there are two major things. One is the physiological barriers and the cellular barriers. So if you talk about the physiological barriers, these are the physiological barriers and these are the cellular barriers. So in the physiological barriers, then nanoparticles are translocated in quite different mechanisms. One is the transcellular lipophilic pathway. Actually, you heard about the blood-brain barrier. When it need to cross the blood-brain barrier, then it should have the lipid-soluble nanoparticles. When it crosses to the absorptive transcytosis, then you have to need the cationic nanoparticles. Like that, it can be grouped where is the physiological barrier to be encountered. And another is the cellular barriers. When you do the cellular barriers, then it should cross or it should translocate in the cells, then it have the direct or some indirect mechanisms to enter the cells. So this can be a tunable reason where the nanoparticles can be utilized for this delivery purpose. And now is the one of the final slide where I can show you how the modality of the cancer nanotheranostics coming up. So this side I put all the therapeutic modality, and other side it is the imaging modality. So far the established one, if you see the chemotherapy can be clubbed with the imaging, optical imaging, also CT and also the MRI. Like that, radiotherapy and photothermal therapy having some combinations. So a particular combinations, if you choose it for a particular module of the therapy, it can be coming up in this group. So in a cancer nanotheranostics, first things, when you try to develop, you have to choose what will be your therapeutic modality and what will be the diagnostic modality. So that is giving a good classifications or good idea to come up or new theranostic modalities. Now I will show you some of the recent advancement of the cancer diagnosis using the Raman scattering. And here, as I mentioned, that the molecular diagnostics or digital health or digital diagnosis coming up mostly as I am covering only the cancer and some of the neurodegenerative disorders. But as you know, there are the modalities we can, what I am talking about, the Raman scattering or SARS-based immunoassay, and that can be clubbed with the artificial intelligence. So these two are clubbing in the digital diagnostics. So some of the examples I will show you. Before that, there is a clear idea about this modality, the SARS modality, with the fluorescence, bioluminescence, and the photoacoustics. There will be several pros and cons are there, which can easily differentiate and which can easily distinguish and what is the greater advantage of the SARS. SARS, the greater advantage is that it's high sensitivity. Even it can be possible to detect the molecular level. Single molecule detection is possible among these other three. So that is of the huge advantage by limiting the penetration depth, of course. So one thing that when you talk about the SARS biosensor, so this is the nanoparticle and all other the overexpressed biomolecules are there that we need to detect, and that can be tuned definitely with the complementary molecular techniques which is well established. Suppose you heard about the Western blot, PCR, fluorescence in situ hybridizations, flow cytometry, that can be complemented here. So in the first example, this is one of the outstanding paper. It is published long back by Sumingni in the Emory. This is probably the first paper for detecting the biomarkers, cancer biomarkers, which is overexpressed in the cells through the SARS tag. You know that what is the difference between a cancer cells and a normal cells? Actually, the cancer cells, the certain expressions of the receptors is quite huge, which is compared to the normal cells. Normal cells, that kind of receptors are there, but their expression is not much. One such expression is called the EGFR, endothermal growth factor receptor. So these receptors, which is highly expressed in the cancer cells space, so how we can detect it? The tags which is prepared, which having the complementary antibody on it, and which can easily make a strong bond when you club it. So in this work, it has demonstrated that in the cell culture or even the cells, if you incubate your tags and then after a certain time, if you can take the Raman spectra after washing on this media, then you can get the Raman spectra of the Raman reporter attached on it, which is coming in the dotted line, and the red one is the pure tags. So you can easily detect the expressions of the biomarkers, which is highly expressed through this tag, very uniquely and very sensitive way. So this is another very interesting works. I will show you some of the pioneering works last 10 years happened. Then we will also definitely show what we have done in these areas. As you know, the cell division is a very concerted process. And major things is the mitosis, which is a complicated and the dynamic process which is coming up. And in this process, actually it is induced apoptosis in the cells, and the cell divisions, when it comes, you can see that is the mitosis having the 4 different stages: prophase, metaphase, anaphase, and the telophase. And these stages can be tracked using the Raman fingerprint of these 4 moieties. One is the SS vibrations, CS vibrations, and there are 3 major aromatic amino acids, phenylalanine, tryptophan, and the tyrosines, which can be easily tracked through the fingerprint, and it can be tracked. And once this progression, this is the dark field image in the real time, you can see the cell division is happening in the left side, and corresponding the Raman fingerprint of this vibrational frequency can be easily tracked, which is finally demonstrated that the cell division concerted process which can be tracked through this technique. Another very important work is published that if you induce the apoptosis, the cell death is happening, but this cell death process, as I mentioned, the certain molecular changes is happening, and these molecular changes, one of that phenylalanine or phenylalanine associated proteins. So it has been tracked that there are major fingerprint of the phenylalanine which can be tracked in time course time during the apoptotic progressions, and that can be clubbed with the metabolomics and the proteomics. In the metabolomics level, we can also see that the phenylalanine prevalence is quite high, and also in the proteomics, it is also tracked that the phenylalanine metabolism is perturbed. So this is one of the very interesting work which is published in the Al-Said group, which has given that they mentioned that one of the key things, the phenylalanine, which is increased highly and in the metabolisms and the proteins, which resulted a network analysis of the, and you can find that phenylalanine metabolism was perturbed. Another very interesting things, while we are working in the cellular level in through SARS, so when the cell death is occurring, what is happening? 3 major things happening. One is the protein denaturations, protein degradation, and the DNA fragmentations. That can be minutely tracked here. You know that the phosphodiester bond, which is keeping this DNA duplex integrity, and when it is breaked, there is a certain fingerprint. One is the 830 and another is the 1585. That can be easily tracked when this POP is stretching, POP backbone is breaked during this induction of the apoptosis. Similarly, the protein denaturation, protein having 2 states, one is the native and is the denatured states. In the native state, all the time the disulfide bonds are there. So when this disulfide bond is breaked, it comes in the denatured states, and that can be tracked through this Raman fingerprint analysis. Mostly you can see the prevalence of the phenylalanine is quite high when it is coming up. So like that, there are certain chronology of these changes happening during the cell death process can be tracked. So as I said about the imaging, this is one of the interesting paper where they can complemented that the MRI imaging as well as the SARS imaging during this surgical resection process. So that can be also clapped if you use the Raman tag, which can easily complement when this surgical resection is coming up at particular region, the changes in the biomolecules, and that can be imaged, and which is fully complemented with the MRI. So now coming to our work, we have started majorly in 4 different cancers. One is the prostate, cervical, lung, and the breast. And we have extensively done these investigations, especially the diagnostic probe development. with the collaborations of the Regional Cancer Center and the TMC Mumbai. And there are few works we have already established before that. Actually, as I mentioned that the search tags, we have prepared kind of Raman reporter molecules. This is kind of the cyanine dyes which is prepared having the three different color range. These are three different actually color we have positioned, but three different color range means three different Raman fingerprints which can be tracked. So if you incorporate the tags in the tumor, suppose the tumor is progressed with certain kind of protein expression or certain kind of xenograft model where the certain kind of protein expression is there, and the tag is corresponding antibody is there. So if you take the Raman spectra from the skin of the tumor, you can easily track which kind of antigen antibody conjugation is happened. So this multiplex study which we have demonstrated that if you have at a time 2 or 3 biomarkers, and if you track whether there are 3 or 2 or 1 biomarkers are present, this multiplex study can give you a nice idea from the analysis of these tracks. So that we have developed, and with this, the first work what we have mentioned here, the detection of the cervical cancers. In the cervical cancer, there are 2 expressions is hugely coming up. One in the cell surface, EGR expression, and in the nucleus, there are another expression is that which is called the P16 and Ki67. That is another protein expressions. We prepared both the tags with the respective antibody, and both the tags we have incubated in the cell culture with the cervical cancer, and we grouped that in the Raman mapping. You can see in the Raman map, the blue color in the cell surface, which is, if you click that blue color, you can get the corresponding spectra of which is actually used for this cell surface receptors. And you can see the blue color in the nucleus, it is false color generated, where it can be grouped in the cell surface. So in the nucleus. So any kind of blue color, if you click it here, you can get the corresponding spectra, which can easily tell you that the tag is conjugated in the nuclear biomarkers. So we have demonstrated that one. Then more clinical samples. Actually, there is a cervical cancer is a long window cancer. Actually, it has around the 15 years existence. So it becomes a metastatic cancer. It requires 15 years. So within that period, if it can be detected, it will be cured more or less 100%. So what we did it, actually 3 gets exfoliated cells from the cervix we have collected, and these exfoliated cells from the 3 grades, one is the normal, one is the intermediate, actually it's called the HC and the CC. These 3 grades of the exfoliated cells from the clinical samples, we have tried to make the probe, and the probe is, here you are using the gold nanostar, and the gold nanostar you put the silver tip on it. Actually silver is the better search substrate, search enhancer than the gold. That's why you used here at the tip. That way we have tuned it, and then the Raman reporter and the conjugated antibody will be there. So we have graded, this is the normal, and this is the HC, and this is the fully metastatic cancers. So we can see that the intensity of the spectra can be analyzed, where you can see the prevalence of these 3 grades can be detected. So that is way we have developed. Another, as I mentioned, that in the level free way, where we have done that 3 ways, the exfoliated cells from the single cell, cell palette, and the isolated DNA. So these 3 ways we have checked the Raman fingerprint on it, and this Raman fingerprint can be through the artificial intelligence in chemometric modality, and there are well classified groups are already established on that, and then we will get the specificity and sensitivity, which can be, actually the cervical cancer, the gold standard is the pap smear test, which can be complemented with these techniques. And what we did it, that 3 major grades can be classified, and in that we will get around 82% sensitivity for this single cell, cell palette also 82, and from the DNA it is more than 90% sensitivity we are getting using these techniques. So another, I will show you some of the other cancers. Now cervical 2, now we have checked, we have prepared a probe for the prostate cancer. It is nicely, you know that tetraphenyl ethylene, it is a AI agent, aggregation-induced emission coming up with these molecules, and that we can tune as a Raman probe or Raman reporter molecules with indolenial group to be attached here. And from there, we used a small peptide sequence. This particular peptide is called the peptide substrate. It is susceptible for the PSA, or it is a recognizing motif of the PSA. There are small peptide cores are already established for the recognitions of the different kinds of protein highly expressed. So these peptides are highly expressed and highly recognizing motif of the PSA. So what we did, this peptide we conjugated with the gold nanoparticles. Actually, gold thiol, very good strong covalent bonding is happening. So you use the thiols at the terminal. And the nice way what we did it, actually when this probe, when you use the PSA, in presence of PSA, there are first this amide will be cleaved off, which is attached to that probe. And once it cleaved, then the Raman reporter molecules, which is the TP molecule, far away from the nanoparticle, and the Raman signal will be get diminished. So you may get the signal drop hugely, and we can find out the limit of detection 0.5 nanogram. Actually, if the PSA level is around below 10, then it is fine. It is somewhat okay, but it is very dangerous if it comes below above 10. So with this, we have also established the detection limit around 0.5 nanogram per ml in the serum samples. So we have also demonstrated the lung cancer detections in multiplexing way. Actually, it is a cocktail of both the fluorescence and the Raman probes. When actually where it is done, when fluorescence is on, Raman will be off. This switch off, switch on mechanisms we have prepared using 3 different probes, and we have demonstrated the 3 major biomarkers, EGFR, CK, and the napsins, 3 major biomarkers of the lung adenocarcinoma that can be detected in the multiplex fashion. Now coming our most interesting work in the breast cancer, last 2 years we have worked exclusively in these breast tissue samples for the multiplex diagnosis. So in the breast cancer, actually 3 major hormone receptor, it is called the prognostic markers. It is called the estrogen receptor, progesterone receptor, and human epidermal growth factor receptors. So if among these 3 receptors, if one is present, or 2 is present, or all 3 is present, accordingly the treatment modality will be different. But so far in the clinics, the diagnostic modality, none of these 3 biomarkers cannot be detected simultaneously. We have demonstrated that 3 biomarkers can be detected simultaneously using 3 multiplexing detection probes. So we have used 3 different tags, which is conjugated to the ER, PR, and HER2 with the respective antibody and respective Raman reporter for the signatures. And we have detected, suppose the 3 biomarkers are present, the representing Raman peaks are presenting, this is at the tissue samples, representing that one. If 2 is present, we are showing, and if none of this is present, it is called the triple negative breast cancer, which is very, very notorious, and there is no treatment modality so far exclusively used for this TNBC, but detection of the TNBC is very, very challenging. So with these probes, we also showed that TNBC can be also detected easily using these probes. So we got this duplexing and the triplexing around 70 to 75% for the duplexing, and for single biomarker we achieved around 90% sensitivity in this detection modality. And another thing is HER2. This HER2 detection is using on the fluorogenic probe, which is called the FISH analysis, that can be detected, or this level of the HER2 also very crucial, whether it is a +1, +2, or +4 regions, that can be also analyzed through the Raman fingerprint analysis. Still, there is the challenges in this. To evaluate the significant number of Raman reporters in the multiplex peaks is very challenging, and there is a non-specific binding of the gold nanoparticles in the tissue samples, and the cause of the false positive results, that is also hugely challenging. So we are still trying to solve it, mostly in this point, non-specific binding. Sometimes the nanoparticles will be sticked on the, especially in the tissue samples, that can be tracked in this way. So now I switched about cancer to neurodegenerative disorders. Recently we have also initiated a ICMR funded project where we try to make a modality. Actually, there will be no such diagnostic modality for the Alzheimer or Parkinson disease so far. So some of the counseling and some of the very simple tests are there to assess some of the experiments. But there are certain biomarkers for the Alzheimer's like A-beta versions, A-beta 42, A-beta 40, tau, phosphotau, these are the. But eventually, for the detections of these biomarkers, no standard operating clinics are there. So we developed a sandwich mode of complex where this both monoclonal and polyclonal antibody of the A-beta 42, which can be used on gold and the iron oxide nanoparticles, and can be tracked with in a sandwich mode of complex and can be detected here. So we have initiated and we have tried an attempt from the serum samples so far with this Raman fingerprint analysis of this sandwich complex. 10 femtomole of the detection level can be analyzed. So it is now the challenge in the serum sample. As serum sample, the abundance of these biomolecules, especially these biomarkers, are quite high. Actually, this resides if you check from the CSF. But CSF is a totally invasive way. So invasive way, it is very difficult. So we are trying in a non-invasive way to detect these Alzheimer biomarkers using this modality. So we have succeeded. And in the COVID period, we have also attempted here through Raman modality, through search tags to detect this COVID antigen. Actually, what happened, we used to do the RT-PCR, which is the gold standard, and we are using the nasopharyngeal swab, which is the standard way of the collection, but there is a little bit Hertz condition are using for that one. So actually in the case of the COVID, the most important is that the prevalence of the spike proteins. If you see the COVID virus, the periphery is the spike proteins. To detect the spike proteins is a very crucial, which we can try it through saliva samples. So we have tried the saliva samples of the healthy and COVID positive one. And first we have done some of the model study using these spike proteins. These are the incubated spike protein. We find very good classification between this COVID positive and the which one is the healthy one. So out of this saliva, out of 52 samples, all 52 are classified as a healthy, not COVID infected. And out of 38, all 38 are the classified as spiked with the spike proteins. Also, we have checked one way that COVID healthy those who don't have any COVID infections, those who have COVID infections, and those who have recovered from the COVID. All three saliva also giving a clear some kind of classifications. Although this is very, very preliminary data, but we cannot conclude it. But from the Raman fingerprint, some of the biomolecular changes happening even after the post-COVID data or post-COVID, that can be also classified in these techniques. So we have 10 minutes, 5 minutes. So now I will going to show some of the theranostic work. And as I mentioned about the theranostic modality, all we coming about the PTT, chemotherapy, PDT, now coming out with some of the search modality for the theranostics, and among which one of the model paper, every time I want to show this one, actually you know the doxorubicin, which is linked through the hydrogen bond with the gold nanoparticles. And what happened, dox having some inherent fluorescence. So when you have incorporated in the gold, there will be a quenching of the fluorescence happen. There will be no more fluorescent. So when it comes inside to the cells, in the cellular pH, which is below 6.5, actually lysosomal pH around 4.5 to 5, and that region, the hydrogen bond will be cleaved from this linker, and dox will be free, and what happened is fluorescence will be turned on. On the other hand, when it is come to the contact with the gold nanoparticle, its search fingerprint will be quite high. Mostly these are the signature Raman peak of the dox, which is coming slowly, gradually declined once this hydrogen bond will be cleaved. So the progression of the dox release can be tracked in this modality. So there is one interesting work is recently published that this is also a TPV mode of molecules which can be tracked, which can be used in the
self-assembly mode of the silver nanoparticles, and three things. It is a silver nanoparticle as a core, and this is the oxidized interface, it is there, and AIE cells with the surface. So in that work is a multi-modality probe is developed, where they have shown AIE fluorescence as a fluorescence modality, along with CT and RT, is along with the having this PA, and this is the photothermal therapy, and the photoacoustic imaging also can be has shown in this modality. So is the multimodality probe is developed. With this, I am going to show our one of the interesting work here, that here we have used a Raman reporter. It is a photothermal chemotherapy, where the gold nanorod, which can be used as a therapeutic modality, as the nanorod having a photothermal effect, which is used here. You can see here, this nanorod is a link to with the doxorubicin through a hydrogen linkage, and there is a peptide. It is specific to matrix metalloproteinase. Actually, the matrix metalloproteinase is overexpressed in the cells. So this peptide is linked with a Raman reporter molecules, is a squarine dye molecules, and when it comes, when in the cellular regions, this hydrogen bond will be clipped, dox will be released, and if you shine with the laser, then the heat generated from here, which comes, is a PTT effect. So it is a photothermal chemotherapy coming from the dox, and the photothermal therapy from the nanorod. And the degradation of the apoptosis you can see from this bright field image, and you can also complement it through the DNA backbone cleavage as well. So this is kind of one of the work which I have accomplished, is that dox loaded mesoporous silicon nanoparticles, and we have exclusively showing here the dox release mechanisms, and also the apoptotic event which can be expressed here. And actually what happened, the mechanism of the dox, when dox is released in the cytoplasm, slowly it goes to the nucleus, and the DNA intercalation happens. So that process also we have tracked through the Raman fingerprint analysis. You can see here B to C transaction or D to A transactions can be also tracked through the Raman fingerprinting. And also we worked in the melanoma, where decarbazine is a drugs which can be utilized in the nanorod, and we also established here in this sequence. And a very recent work, last year we have published here. It is a kind of a multimodal drugs. We have used dox prodrug as well as a drug which is a drug resistance inhibiting molecules, which can be clubbed together, and we have shown that we can increase the drug resistancy, or we can remove the drug resistancy power in this modality. So far there are list of molecules. If you know the cancer nanotheranostics or nanoparticle based, these are all established. One of them is that called the Doxil, is a liposomal dox, which is also now launched by Sun Pharma in India, which can be also approved it. And these are all either clinically trials or are approved, which is used for nanotheranostics way, or is in personalized nanomedicines. Last work, which I am going to do, as we are working in the natural products, these are the molecules which is obtained from the Hydnocarpus ortingalblumi. Is the molecule is called the hydnocarpin. Hydnocarpus is coming, a fruit is called the globus fruit. In Malayalam it is called the maruti. So the seeds we are using, and these molecules we have used to semisynthetic modifications, and we make the isoxazole and isoxazolone two parts. Actually it has the primary hydroxy. This primary hydroxy is oxidized to aldehyde, and then we will do the 1,3 cycloaddition reactions and make a versatile of NC synthesis. One is the isoxazole moiety and one is the guanidinium moiety. And what interesting thing is that these two molecules also having some of the Raman fingerprint, and this is coming as advanced heat molecules, showing very good activity in lung and melanoma, and also having the Raman fingerprint. So the internalization of these molecules can be tracked in the cells in the time course manner, means when it internalizes, how long it resides in the cells, how the metabolism works, and how it can be excreted. That can be tracked. And most interestingly, what we observed that cytochrome C, which is one of the hallmark of the intrinsic pathway of the apoptosis, which is released from the mitochondria to cytosol, we have tracked first time that the cytochrome release from the mitochondria to cytosol, which is evolved in the time course manner, as well as the DNA Raman fingerprint. So this is one of the nice demonstration. And in the last, as I mentioned that Professor Sureshan has mentioned that click chemistry and the last year Nobel Prize of the Caroline Barthosi of his unique work about the metabolic glycan leveling, we have also attempted the glycan leveling. What is the glycan? Actually, in the cancer cell surface, these are assemblies is there. It is the assembly of the carbohydrate structures. It is called the glycan. And in the top of the glycan is there the sialic acid. So what interesting thing is that Barthosi first proved that if you use some of the monosaccharide code like glucosamine or mannose-amine, and if you incubate in the cells, then this glucosamine through biogenetic pathway come as a sialic acid and sits top of there. And through click chemistry, she used azide in the sugar moiety and used some fluorophore with the alkyne, and then he showed that the fluorophore mostly fluorescence in the cell surface, and then proved that the sialic acid biosynthesis happened in the cell surface, and that can be proved through click chemistry. So that is the work actually in this Barthosi's work. So what we attempted, we used the alkyl chain. This alkyne which is used is the first time is the monosaccharide, is the glucose amino sugar, and which is attached to the alkyne, and which also we tracked through that one. We incubated in the cells, and what happened? These cells also used form the sialic acid top of that and using this alkyne. And this alkyne having out of fingerprint Raman peaks around 1900. And we track the Raman fingerprint of the alkyne here. So this molecule biosynthetically transformed to the sialic acid and sits with the alkyne. We also proved actually there is a process around in the for making this biosynthetic pathway. Sometimes it is 72 hours, sometimes it's around more than 72 hours. We have optimized that one. But what interestingly we do it, we have using 3 cancer cells having their metastatic progressions. One having very low metastasis, one moderate and the high. Triple negative breast cancer having the high metastatic progressions. So you can see that those who having the high metastatic progressions, the alkyne peaks are coming up more highly intense compared to the moderate and the low. That can be tracked in this glycan imaging process. And another proper works we have also done. It is an iridium based NADH sensings, and here we have also worked in both fluorescence and the Raman way, and we have tracked here is the energy sorting process, this iridium complex, where is a bimodal luminescence sort sensings and as well as the photodynamic therapy. Here also we have shown that fluorescence turn on and the Raman starts turn off process in these molecules. And that is another work for cancer nanomedicine. We have also showing that pancreatic cancer, where both the 2 drugs in synergy, one is the natural product embalin and another is the c-MET inhibitor RPI, which can be clubbed in a synergistic ratio, and which has also progressed in that patients, and we have shown the high therapeutic efficacy. So now I am going to close. Before that, we have also developed the portable Raman spectrometer. And that is one of the initial trials, and Dr. Yusuf who developed here, and in this journey during this mega projects we have worked out, and we have also compared that one, and for this development we also recognized the technology award. Now coming up the last things, that the current situation of these traditional disease targets and disease mechanisms and the personalized medicines, what our futuristic goal. So definitely this starts coming up in a futuristic way in this region, and this is the trends which we try to integrate, that integrative diagnosis which can be clubbing with AI-enabled diagnosis. That is our goal and motto. And this is the current market share of this work, this journey. I think it will be launching way. And in conclusion, I am going to talk about the area we are going to develop here is chronologically is coming up as a mode of diagnostic modality, and which the eventually we developed in times. Now we are coming up, it should coming is a diagnostic modality in a non-invasive and neurally platform, real-time monitoring of any kind of disease. So this is the acknowledgement. Lot of people are involved in this work, and this is my group. There are some old members are here. Both biology and chemistry is work together in our group, and this is their strong hard work and their achievements which I am going to show. Thank you all for your kind patience.
Thank you, Professor Methi. Since we are running out of time, so there is no discussion part. And an enormous amount of research he has done, and it is obviously applicable to real life situations, particularly in this disease era. And thank you so much, Professor Methi, for your wonderful presentation.
Thank you so much, sir. Next, I invite Dr. Ebi T.G., Assistant Professor, Department of Chemistry, Sacred Heart College, Tevara, to present a memento as our token of love to Professor Dr. Kaustubh Kumar Methi. I also request Professor Dr. Kaustubh Kumar Methi to kindly receive the same. Thank you, sir. With this, we have come to an end of all the technical session of NTAC 2023. Now we shall start our valedictory session shortly. All the participants are requested to stay back at the venue. Thank you all.
colleges across India. A very warm good evening and a warm welcome to the valedictory function of 21st Professor K.V. Thomas Endowment Seminar and the 4th International Symposium on New Trends in Applied Chemistry 2023. After 2 days of deliberations, exchange of ideas, and constructive interaction, NTAC 2023 is coming to an end. Though the tangible benefits are yet to be worked out, there is no doubt that our 2-day conference had once again proved to be a major hit among the chemistry aspirants. Once again, hearty welcome to the valedictory function. Let's invoke the divine grace before we begin. I invite Ms. Anjali Tishi for the prayer. Kindly rise for the prayer.
There shall be showers of blessings. This is the promise of love. There shall be seasons refreshing, sent from the Savior above. Showers of blessings, showers of blessings we need. Mercy drops round us are falling, but for the showers we plead. But for the showers we plead.
We are extremely sad to inform you all that beloved father of Professor Tamoki Nobuyuki expired this morning. We shall observe a moment of silence in remembrance of the departed soul. Now, I would like to invite Dr. Zinu George, Assistant Professor, Department of Chemistry, Sacred Heart College, Devra, to welcome the gathering.
Thank you. Good evening. Our beloved Principal, Reverend Dr. George John CMI, most respected professors, Professor Itzhak Tor, Professor Santos Rosa, Professor Kaustuf Maiti, Professor Srijit Shankar, Head of the Department Dr. Franklin John, Organizing Secretary of the Symposium Dr. Ramakrishnan S., distinguished speakers, invited guests, delegates, my colleagues, and dear students, research scholars, and esteemed faculty members from other departments. A very good evening to everyone. And I thank you on behalf of the Department of Chemistry, Sacred Heart College, Devra, for joining us at this international edition of Professor K.V. Thomas Endowment Seminar. This is indeed a grand occasion of the valedictory of our seminar. Let me give a very short summary of the seminar. We were introduced to the world of next generation RNA-based therapeutics by Professor Dr. Ada E. Yonath, who delivered her Nobel lecture and graced the occasion with her inspiring presence for the past 2 days. Then we had the plenary speakers, Professor Dr. A. Srinivasan on porphyrinoids with polycyclic aromatic units, Professor Dr. Tamoki Nobuyuki, building a small molecular robot by combining a motor protein and a molecular photo switch. Dr. Biju A.T. delivered his plenary lecture on N-heterocyclic carbenes. And then we had a cultural performance by our students yesterday night. The next day, we were amazed at the lecture given by Professor Dr. Itzhak Tor on fluorescent nucleosides. And we had the lecture on biodegradable porous materials by Professor Dr. Santos Rosa. Plenary lecture 6 by Professor Dr. V.N. Rajashekara Pillai on research and innovation opportunities in applied sciences. Then Dr. Khana M. Sureshan from ICER on crystalline polymers. And the last lecture was by Professor Dr. Kausuk Methi from NIST on cancer nanotheranostics using SCRS. Now I'm moving on to the duty entrusted to me. Our chief guest of the function, Professor Tor, has astounded us with his easiness and brilliant mind. He is a true legend who has made significant contributions to science. Professor, please accept my greetings. Welcome to this function. We welcome our beloved principal, Reverend Dr. George CMI, to this valedictory function. Welcome, Father. I welcome the organizing secretary and the backbone of this seminar, Dr. S. Ramakrishnan, to this function. Professor Tamoki, Professor Rosa, they have traveled this far, sacrificing their time to exemplify their dedication to science. We are grateful, professors, and we warmly welcome you to this gathering. I welcome Professor Mighty from NIST and Dr. Srijit Shankar from NIST to this function. Welcome, professors. Again, head of the department, Dr. Franklin John, and we welcome all the delegates, research scholars, and my colleagues to this function. And thanks once again for your presence and contributions. Thank you.
Thank you, Jinu ma'am, for your warm welcome. I call upon Reverend Father Dr. Jose John, Principal, Sacred Heart College, Devra, for the presidential address. Welcome, Father.
A warm good evening to one and all. This very boring business that the symposium is over and a valedictory function of very long duration may not be fitting. So my presidential address will be very short. Distinguished guests and eminent scientists on the dais and off the dais, dear participants of 21st K.V. Thomas Endowment Symposium. We started with the basics of the central dogma of molecular biology by Nobel laureate Adai Yanath, starting with a molecule of mRNA moving through the subunits of ribosomes and forming new proteins. And after that basics, it moved to the recent or latest trend in that field of antibiotic resistance. The problem, how can it be tackled with by engineering RNA-based nutraceuticals or therapeutics. So I make it a point that here we spent 2 days in serious deliberations on advanced science, maybe in chemistry, maybe in molecular biology, maybe in applied chemistry, it is specifically mentioned. And all these deliberations were focusing on how can we make this planet a little more better, how can we make human life more easier and safe, and of course, how this knowledge can be transferred to the next generation. I have gone through the presentations there, the oral presentations yesterday evening, and I could find that all the presentations there were having some bearing on practical aspect of science. I sincerely congratulate each and every participant who have presented their oral presentations as well as poster presentations. And I don't know who won the prize, if there is a prize. Yeah, even if there is no prize, I mark all the presentations awesome and highly scientific. I am sure that the lectures, there were 8 plenary lectures, and they were truly international, starting with the Nobel laureate and all of the deliberations, the lectures were of a very high standard, and definitely I hope that you have imbibed something or everything from each and every plenary lecture and the discussions followed. I thank each and every eminent scientists who have come over to this small campus and spent 2 days with us to enrich the young minds so that they may become great scientists in future. So thank you all the eminent professors and scientists who have come here. I congratulate the faculty members of the Department of Chemistry for organizing this symposium in a very, very wonderful manner. From the planning session, maybe from the very beginning of this academic year, they started the planning, inviting, discussing. More than 10 or 15 discussions were made in the department involving the key persons. That's why this was meticulously planned and systematically organized and wonderfully executed. I congratulate the organizing secretary, Professor Dr. Ramakrishnan, Department HOD, Dr. Franklin, all the other faculty members. There were no ups and downs. All were as a team very confident, and they were determined to make this a wonderful, memorable event. I congratulate each and every one of the members of the faculty, and also there are students of the department who have put their support in making this event a grand success. Congratulations to the students also. And with these words of appreciation and great gratitude, I conclude my speech. I welcome you all again. Maybe after 2 years, this kind of international seminar will be conducted. Every year this seminar is there, but such an elaborate seminar will be conducted biannually only. So I personally welcome you all to the next international symposium here in SH. Thank you very much.
Thank you, Father, for your valuable words. Now, I invite the guest of honor, Professor Dr. NTAC-2023, to address the gathering.
Well, thank you very much. I was told just a couple of hours ago that I'm expected to talk, so I'm not really prepared, or at least I don't have anything written prepared, so it's all going to be improvised. But the first thing I'd like to do is obviously thank the organizers and thank all of you for coming to this particular meeting. All the speakers, I think, would admit that we've been spoiled. We probably don't deserve all the attention, but we obviously humbly accept it and enjoy it. So we will continue to do so. The other thing that I perhaps want to mention that has not yet been mentioned, and it's very hard because we had a wonderful summary, I would just say that when I give lectures in such events, it's really mostly for the young generation and the students. The older people in the room, the professors or whatever, we don't need to impress one another and share too many things with one another. We bump into each other around the world in different conferences. We know about what's going on. We review papers, we review proposals. But for the young generation that we hope will carry the torch and continue and do science, I think those conferences are really, really important. And it's possible that you perhaps haven't understood everything. It's just all about inspiration. If you realize the intensity and the passion for science that a person like Ada Yonat, who's 20 years older than me, and although we're from the same hometown essentially, I see her mostly around the world in conferences than actually back in my hometown, because still at this very age, she travels extensively and shares her wisdom and science. I think this is really the inspiring messages that you should take with you and realize that when people are passionate about science, about research, about making the world a better place, good things happen and careers flourish and you get a chance to do amazing things and visit amazing places. So again, I hope that there's a little bit of inspiration left with you, and you take it with you and run with it, and do make the world a better place. Thank you so much.
Thank you, Professor, for your valuable words. We have conducted oral presentations and poster presentations competitions. We are highly delighted that we got a total of 63 entries, out of which 29 were oral presentations and 34 poster presentations. We are extremely gratified to all the participants for their dedication and hard work. Now, it's time to honor our judges. I invite our honorable chief guest, Professor NTAC-2023, to give away the mementos to our judges as a token of love. First, I invite Professor Dr. Paulson Matthew, Professor St. Thomas College, Thrissur, Judge of Oral Presentations, to receive the memento. Welcome, Professor. Now, I invite Dr. Anu Gobinath, Assistant Professor, Kufos, Judge of Oral Presentations, to receive the same. Welcome, ma'am. Thank you, Professor. Thank you, ma'am. Let's move on to the most awaited moment of this evening, which is to honor Let's move on to the most awaited moment of this evening, which is to honor the poster and oral presentation winners. All the awards are instituted by American Chemical Society with a cash prize of Rs 2,500 each. I invite Dr. Thomas Kuti Jose, editor of NTAC 2023 proceedings, to announce the winners.
Warm good evening to all. It's my pleasure to announce the winners of Best Oral and Poster Presentation Awards. We have 6 Best Oral Presentation Awards and 10 Best Poster Presentation Award. Now I kindly invite Professor Ishak Tor to distribute the certificate and cash award. Professor. And the awardees are the oral presentation category, the Best Oral Presentation Award instituted by ACS Applied Materials and Interfaces Journals goes to Leah T, Indian Institute of Technology, Palakkad. Best Oral Presentation Award instituted by ACS Chemical Biology Journal goes to Deepak J. Prabhu, Sacred Heart College, Tevara. Best Oral Presentation Award instituted by ACS Omega to Deepak Patra, CSIR NIIST, Thiruvananthapuram. Best Oral Presentation Award by Journal of American Chemical Society goes to Shamna M, Sacred Heart College, Tevara. ACS Journal of Organic Chemistry Award to C. Rajalakshmi, CMS College, Kottayam. Anybody from CMS? Okay. ACS Journal of Physical Chemistry Award goes to Elsa George, MG University, Kottayam. Next, Best Poster Presentation Awards. Best Poster Presentation Award instituted by ACS Applied Energy Materials goes to Anisha Matthew, CSCR NIAST, Thiruvananthapuram. Best Poster Presentation Award instituted by ACS Applied Materials and Enterprises to Kavya P, Government Victoria College, Palakkad. Best Post Presentation Award instituted by ACS Applied Nanomaterials awarded to Subhan Ahmad AA, University of Hyderabad. Thank you, Professor. Now I invite our beloved principal to hand over the prizes. Next, the Best Poster Award instituted by ACS Earth and Space Chemistry goes to Rubina Shahjahan P, Mahatma Gandhi University, Kottayam. Anybody from MG University, please. Best Poster Award by ACS Environmental Science and Technology Engineering is to Tirtha T, St. Joseph's College, Devagiri. The Best Poster Award by ACS Environmental Science and Technology Water goes to Jishma R, St. Joseph's College, Devagiri. The Best Poster Award by ACS Physical Chemistry goes to Hadia MA, Farooq College, Kozhikode. Best Poster Presentation Award instituted by ACS Polymers is to Abhisha VS, St. Joseph's College, Devagiri. Best Poster Presentation Award by ACS Industrial and Engineering Chemistry Research to Neenu KV, Kusat, Kochi. Best Poster Presentation Award by ACS Organic Letters to Abhirami, University of Kerala, Thiruvananthapuram. Okay, thank you. I would finished. I would like to thank our judges, Professor Pradhaban Sir, Dr. Anu Govinath, Dr. Paulson Matthew, Professor Rosa for their valuable time and support. I also thank all the participants and congratulate all the winners. I wish you all the very best for your future research journey. Thank you.
Thank you, sir. A gentle reminder, all the prize winners are requested to sign the voucher before you leave the malicious hall. Our volunteers will help you out for the same. Participants are the soul of any program. Your valuable feedbacks is really important and will encourage and motivate us to organize more and more such events. Now, I request the participants to come forward to give their valuable feedbacks about NTAC 2023.
A warm good evening, you all. It was a great opportunity, and I thank everyone for this opportunity. So this was a platform for the interactions and communications, irrespective of the borders, irrespective of the language, so irrespective of any of the background, gender, anything, or any other borders like this. So while I was studying in 5th standard, I had a habit of noting down the names of the Nobel laureates for the upcoming local quiz competitions. So I noted it down along with 2 other names. So this name, Professor Dr. Adai Yohanatman's name, but after years I didn't have any of the expectation that I would meet her and I will have an opportunity to witness her lecture in person. So yesterday started with that auspicious lecture. Then we moved on to Srinivasan sir's lecture on porphyrin chemistry. Then Professor Dr. Tamoki sir's lecture on. It was a wonderful topic, that using motor proteins and applying, plus the molecular switch system to make molecular robots. Then we had another Hartians, Dr. Biju sir's talk on heteroaromatics carbines. So in textbooks, I learned about the carbines in the textbooks only. So we could witness the application level and how it is communicated to the scientific community and its applications and all. Then today has started with Professor Tosa's talk. It was also brilliant. The fluorescent biomolecules, nucleosides. It was also wonderful. Thank you, sir. Then our dear sir's talk on Sandoz sir. So the application, that topic was very significant nowadays, because the recovering the contaminants from the contaminated water, and he also used his own country as the reference to study, and that also very encouraging and wonderful. Then we moved on to Kana Sheshan sir's talk. Then my sir's talk. Then I would like to say that this was a wonderful opportunity to grow as a together. We grow up by sharing communicating the knowledge. So while we are reading papers, reading articles, we will see the author's name. So we will be reading that scientific research article, and we understand by ourselves. But in this case, on this sharing platform, it will be like communicating with the authors. interacting with them. So it was a wonderful opportunity to grow together. Thank you all. Thanks.
Very good evening to one and all present here. I'm extremely happy to be a part of this program NTAC 2023, which started from lecture by Nobel laureate Ada Yonath. Actually, last 2 weeks before, we had an opportunity to interact with Professor Venki, who obtained the Nobel Prize along with Professor Ada Yonath, and he was mentioning a couple of times about Ada during his lecture. That time itself, we were curious to know what is her research and what is her contribution. And when we came here, that was well fulfilled, and I was very happy to see her spirit and the way she is handling herself during this old age and traveling across the globe for spreading science. That was really inspirational, and all the plenary lectures were also very informative, and we could learn many things, and we could get inspired to many things in the field of chemistry. And I would like to thank all the organizers of this event, right from the one who thought of conducting this seminar and one who took up the beacon for conducting this, and all the students, research scholars and undergrad students who were really helpful right from the time we reached Cochin till now. And I'm very happy, and honestly I didn't expect this much from a college from Kerala, such a big program, but what I received is really more than I can expect. I'm very happy about that, and we are all going with a very satisfied mind. Congratulations all the participants. Thank you.
Thank you, dear participants, for your valuable feedback. It really means a lot. Now, I call upon Dr. Ramakrishnan S., Organizing Secretary, NTAC 2023, to propose the vote of thanks.
One second. കാരണം ഇപ്പോൾ ടൈം ഇത്രയും ഡിലേ ആയത് നല്ലതാണോ ചീത്തയാണോ എന്ന് എനിക്കറിയില്ല. സ്ലോലി, സോറി ടു സ്പീക്ക് ഇൻ മലയാളം സർ. So it's indeed it's a God's opportunity for us to organize such a symposium. So first of all, we are highly blessed with the presence of our Nobel laureate, Professor Dr. Ada Yonath. So in spite of her old age, in spite of her so much so-called the things, but she agreed to be with us for 2 days, and with a lot of resource from ribosomes to so and so, with her presence, with her interaction with all the people, we are highly grateful to her for her presence. So really thankful to Nobel laureate Professor Dr. Ada Yonath. Thank you, madam, in her absence. And Nobel laureate has arrived here only because of one person, Professor Itzhak. I still remember once my HOD Franklin sir called me and said that Tor has agreed to make Ada to come here. So really thanks to Professor Itzhak, because he has traveled a lot, almost 40 hours by air, sir, I suppose. And even though he has so much air travel, he visited us with less time to sleep and more time with interaction with all the students, all the faculties and all the people. So we are highly blessed by your presence, interactions, and we are highly hopeful that all the students will be benefited from your science encouraging words. We, the Department of Chemistry, our college, is highly honored to have you, sir. Thank you very much. Professor Tomoki Nobuyuki from Japan, Hokkaido University. Just we send one mail, sir, we are organizing in a symposium, can you kindly accept our invitation? One reply, I am accepting your invitation. That one mail to hear, his presence and his talk, everything, such a humble person. And today we received a message that his father expired. So in spite of that, he was very calm, very cool, and he has already, as told, he has discussed with lot of students. So we are highly thankful to Professor Dr. Tamoki Nobuyuki for his presence and for his discussion. Thank you, sir. When we discussing in the department whom do we have our foreign lectures, foreign speakers, our Mithun Dominic Sedi, Professor Mithun Dominic immediately told that he has a very good connection with our scientist from Brazil, Professor Rosa, Dervel dos Santos Rosa. Sir, really thankful for your presence, for your high interaction with all the students, for your encouraging and for your excellent discussion with all the poster participants, and they are highly happy with you, sir. Okay, sir, and we are highly blessed and we are highly thankful to you for your esteemed presence. Thank you, sir, from the Department of Chemistry, from our college. Thank you, sir. Then the chief guest of the inaugural ceremony, Professor Sabu Thomas, sir, Vice Chancellor, MG University. Thank you, sir, for his acceptance as our chief guest. Then our Indian speakers, Professor Dr. A. Srinivasan. Thankful to you, sir. Professor Biju A.T., our alumni. His interaction with the ACS people, that led to our ACS awards. And he is our prestigious alumni. And whenever we ask anything from him, he is immediately ready to give all his sources to us. Thank you, Dr. Biju, in his absence. Then Professor V.N. Rajashekaran Pillai. When Dr. Franklin John contacted him, immediately he consented to be here. So thank you, Professor V.N. Rajashekaran Pillai, for his presence. Then Professor Dr. Kana M. Sureshan from ISER Trivandrum. Thank you, sir, for his speak and for his presence. Then Dr. Kaustubh Methi from NIST. He has a long conversation with me. He used to ask how the people and how everything about the Ernakulam and everything. And really thankful to you, sir, for his your excellent talk. Thank you, sir. Then our alumni and our own prestigious Dr. Sridhar Shankar, sir. Throughout the 2 days you were with us in your presence, and your students have presented a lot. Thank you, Dr. Sridhar Shankar, for your presence, sir. Thank you. And all the chairs from Dr. Joshi Joseph till Dr. Franklin John, we are highly thankful to all the scientists for chairing our plenary lectures. Thank you, sir. Then our poster judges, Professor S. Pradhapan from KUSAT, Professor Rosa, thankful to you for judging our poster presentation. Then our oral judges, Dr. Paulson Matthew, sir, and immediately Dr. Anu Gobinath agreed to be our judge for oral presentation. Thank you, sir and madam. Thank you. And our own principal, Father Jose John CMI. Whenever we tell anything or whenever we ask anything from you, immediately say, yes, you go ahead, we are with you, our management. Sir, we are highly thankful to you for giving us an opportunity to organize such a symposium. Thank you, sir. Our manager, Father Paulos Kedangan CMI, really thankful for all his constant support. Bursar, Father Sebastian, for all his encouraging support and agree to all the things. Then our sponsors, all the poster and oral awards are sponsored by ACS. Thank you, ACS. Then RSC, then elsewhere, then central agencies like DST SERB, CSIR, KSCSTE, then private institutions like Shipyard, etc. All these sponsors, they have really supported us by giving the financial support. Thank you for all the sponsors. Then our former head of the department and former union minister and currently the state representative to the central government in Delhi, Professor K.V. Thomas. He is a soul, he is such a support for all our endeavor. And whenever we call him, he immediately say, we will do, we will do. So really thankful to Professor K.V. Thomas sir. Then all the media coverage and all the YouTube live session people, everybody, you have supported through all our live coverages. Really thankful to all the media and all the YouTube coverage people. Sir, now slowly I am changing to Malayalam, sir. I still no fluency. ഇനി മലയാളത്തിൽ പറയുമ്പോൾ കാരണം ഞാനൊന്നും പ്രിപ്പയർഡ് അല്ല, അപ്പോൾ ഇംഗ്ലീഷിൽ പറയുമ്പോൾ അതെങ്ങനെയാവും എന്നറിയില്ല. ഓക്കെ, അതുകൊണ്ടാണ്. സോ ഈ ഒരു പ്രോഗ്രാം ഇത്രയ്ക്ക് സക്സസ് ആവണമെന്നുണ്ടെങ്കിൽ, ഇത്രയ്ക്കൊരു ഫ്രൂട്ട്ഫുൾ ആവണമെന്നുണ്ടെങ്കിൽ അത് ഓൺലി ബിക്കോസ് ഓഫ് അവർ ഡിപ്പാർട്ട്മെൻറ്റ്. അത് എങ്ങനെ പറയണം എന്നറിയില്ല. കാരണം എന്തൊരു വെഞ്ചർ ആയാലും എന്തായാലും നമ്മളുടെ ഡിപ്പാർട്ട്മെൻറ്റിൻ്റെ 14 ടീച്ചേഴ്സ് അത് വലിയൊരു സപ്പോർട്ടാണ്. ഓക്കെ, സോ ഞാനിന്ന് ഫ്രാങ്ക്ലിൻ സാറായിട്ട് ഡിസ്കസ് ചെയ്തു. സാർ എങ്ങനെ തുടങ്ങണമെന്ന് ചോദിച്ചു. സാറ് പറഞ്ഞു നമുക്ക് ഷംനയിൽ നിന്ന് തുടങ്ങാമെന്ന് പറഞ്ഞു. സാർ ഓക്കെ, സോ ഷംന, സോ ഷീസ് ദ എന്താ പറയുക, പ്രൊസീഡിങ്സ് ആയാലും എല്ലാ അബ്സ്ട്രാക്റ്റുകളും റിസീവ് ചെയ്തു, പ്രൊസീഡിങ്സിൻ്റെ എല്ലാ കാര്യങ്ങളും നോക്കുകയും എന്താ പറയുക, ഈവൻ ഫോർ ദ ടീ സെഷൻ, എവറിത്തിങ് ഷംന, റിയലി യു ആർ എ ഗ്രേറ്റ് സപ്പോർട്ട് ടു അസ്. താങ്ക് യു ഷംന. ദെൻ ഇതിൻ്റെ ഏറ്റവും കൂടുതൽ വരുന്നത് ട്രാവലാണ്. കാരണം എങ്ങനെയാണ് ട്രാവൽ അറേഞ്ച് ചെയ്യേണ്ടത് എന്ന് പറയുമ്പോഴും അതൊരു വലിയൊരു ട്രാവൽ എന്നൊരു സ്മോൾ വേർഡാണെങ്കിലും അതിന് അത്രയ്ക്ക് ഒരുപാട് കാര്യങ്ങൾ ചെയ്യാനുണ്ട്. കാരണം പല സ്പീക്കേഴ്സും വരുന്നത് ഫ്രം ഡിഫറെൻറ്റ് ടൈംസ് ആക്ച്വലി. ഇപ്പോൾ അയക്കണം, പെട്ടെന്നായിരിക്കും ഒരുപാട് എന്താ പറയുക, ഇവിടെ പോകണം, അങ്ങനെ പോകണം, അറേഞ്ച് ചെയ്യണം. അപ്പോൾ അതിന് ഏറ്റവും കൂടുതൽ അതിൻ്റെ ആ ഒരു പങ്ക് വഹിച്ചത് നമ്മളുടെ രാമലിംഗം ഫെല്ലോ ആൻഡ് my own good friend Shalumon sir. Sir, thank you very much for your travels, sir. Thank you. പിന്നെ പ്രൊസീഡിങ്സിൻ്റെ പറഞ്ഞതുപോലെ രജിസ്ട്രേഷൻ്റെ കാര്യത്തിലും ഇപ്പോൾ അവാർഡ്സിൻ്റെ പ്രൊസീഡിങ്സിൻ്റെ എല്ലാ കാര്യങ്ങളും അത് മാത്രമല്ല എല്ലാത്തിലും ഒരുപാട് സപ്പോർട്ടും ഉള്ള മൈ ഓൺ തോമസ് ഊട്ടി സർ. താങ്ക് യു തോമസ് ഊട്ടി സർ ഫോർ യുവർ ഗുഡ് സപ്പോർട്ട്. താങ്ക് യു സർ. പിന്നെ ട്രാവലിൻ്റെ കൂടെ വരുന്ന വേറൊരു ഫാക്ടറാണ് അക്കോമഡേഷൻ എന്ന് പറയുന്നത്. അപ്പോൾ അക്കോമഡേഷൻ്റെ എല്ലാ കാര്യത്തിലും എന്താ പറയുക, എല്ലാം വരുമ്പോൾ തന്നെ ഡയറിയിൽ എഴുതി കൃത്യമായിട്ട് അതിൻ്റെ ഏത് റൂം എങ്ങനെ ചെയ്യണം, ഒരുപാട് വട്ടം കീസിലും ആശീർഭവനിലും പോയി എല്ലാ കാര്യങ്ങളും സ്മൂത്തായിട്ട് ചെയ്യുകയും ചില സമയത്ത് എനിക്ക് തെറ്റുമ്പോൾ ഒരുപാട് ദേഷ്യപ്പെടുകയും ചെയ്യുന്ന ഡോക്ടർ ദീപക് ഡി പ്രഭു. താങ്ക് യു ദീപക്. ജയ്സൺ. പിന്നെ ജെയ്സൻ്റെ കൂടെ കാലാകാലങ്ങളായിട്ട് ഒരു മോണോപ്പൊളി, ടെക്നിക്കലിൻ്റെ മോണോപ്പൊളി എന്ന് പറയുന്നത് ഡോക്ടർ ABTG. അപ്പോൾ അത്രയ്ക്ക് ടെക്നിക്കൽ എന്ന് പറയാൻ നമുക്ക് ഒരു സങ്കടവും വേണ്ട, ഒരു ടെൻഷനും അടിക്കേണ്ട, അത് ഞാൻ നോക്കിക്കോളാം. ഓക്കെ, സോ റിയലി താങ്ക് യു ഡോക്ടർ ABTG. താങ്ക് യു വെരി മച്ച്. പിന്നെ പ്രോഗ്രാം കമ്മിറ്റിയുടെ എന്താ പറയുക ഒരു നെടും തൂണായി, എന്താ പറയുക, എന്ത് പറഞ്ഞാലും അതിനൊരുപാട് സപ്പോർട്ടും ചെയ്യുന്ന ഒരു പ്ലസൻ്റായിട്ട് ചിരിക്കുന്ന മൈ ഓൺ ഡോക്ടർ ജോൺ സെറിയ. കാരണം എത്ര ഷെഡ്യൂളായിട്ട് ചെയ്യുകയും എല്ലാ കാര്യങ്ങളും എഴുതി വെച്ചിട്ട് സാറ് വാലിഡിറ്റിക്ക് എന്താ ചെയ്യേണ്ടത്, ഇങ്ങനെ ഓരോ കാര്യങ്ങളും ഓരോ സ്റ്റേജിലും റിമൈൻഡ് ചെയ്യുകയും ചെയ്ത ഡോക്ടർ ജോൺ സെറിയ. താങ്ക് യു മാം. പിന്നെ നമ്മൾ 2 ദിവസം ഏതൊരു പ്രോഗ്രാം ആയാലും അതിൻ്റെ ഏറ്റവും ഇമ്പോർട്ടൻ്റ് എന്ന് പറയുന്നത് ഫുഡാണ്. അതും ടെക്നിക്കലിൻ്റെ കുത്തക എവി സാറിന് പോലെ ഫുഡിൻ്റെ ഒരു മോണോപോളിയും സഞ്ജു സാർ തന്നെയാണ്. സഞ്ജു സാറിനെ ഏൽപ്പിച്ചാൽ പിന്നെ അത് നമ്മൾ നോക്കേണ്ട ഒരു കാര്യമില്ല. സഞ്ജു സാർ ഐ ഡോണ്ട് നോ സാർ പോയെന്നറിയില്ല, കാരണം സാറിൻ്റെ വൈഫിൻ്റെ ഡെലിവറി ഡേറ്റ് ആണ്. ഇൻസ്പൈറ്റ് ഓഫ് ദാറ്റ് ഹിസ് പ്രസൻസ് വാസ് എ ഗ്രേസ്. താങ്ക് യു സഞ്ജു. പിന്നെ ഫിനാൻസിൻ്റെ കാര്യവും നമ്മുടെ ഡിപ്പാർട്ട്മെൻറ്റ് സെക്രട്ടറിയും എന്താ പറയുക എല്ലാത്തിലും ഒരു ക്രിട്ടിക്കൽ ഐഡിയ തരികയും എന്താ പറയുക എന്തിലുണ്ടെങ്കിലും അതിനൊരു ഇങ്ങനെ ചെയ്യണം അല്ലെങ്കിൽ ഇങ്ങനെ ചെയ്യണം എന്ന് ഷാർപ്പായിട്ട് പറയുകയും ഒരുപാട് സ്പോൺസേഴ്സിനെയും നമുക്ക് എബി സാറിനെയും സ്പോൺസേഴ്സിനെ സാർ ഒരുപാട് ഹെൽപ്പ് ചെയ്തിട്ടുണ്ട് കേട്ടോ. അപ്പോൾ അത് ചെയ്ത അവർ ഡോക്ടർ മിഥുൻ ഡൊമിനിക് CD. കാരണം സാർ ഒരുപാട് മെസ്സേജ് ഇങ്ങനെ അയക്കും, ഇത് അമ്മ ഇങ്ങനെ ചെയ്യണം, ഇത് ചെയ്തോ ഇന്നത് ചെയ്തോ. So really thankful to you, Dr. Mithun Dominic. Thank you. പിന്നെ ആസ് തോമസ് കുട്ടി സാർ രജിസ്ട്രേഷനിലുണ്ടായിരുന്നു. അപ്പം അതിൻ്റെയും ഒരു മോണോപ്പൊളി എന്ന് പറയുന്നത് നമ്മളുടെ IQAC കോർഡിനേറ്ററുമായ ഡോക്ടർ ഇഗ്നീഷ്യസ് അബ്രഹാം സാറിൻ്റെ കോൺട്രിബ്യൂഷൻ എന്ന് പറയുന്നതെന്ന് വെച്ചാൽ ഒരുപാട് ഇപ്പോൾ ഈ ഒരു പ്രോഗ്രാം ചെയ്യുമ്പോൾ ഒരുപാട് ഡോക്യുമെൻറ്റ്സ് ഉണ്ട്. ഇപ്പോൾ ക്ലിയറൻസിനായാലും എല്ലാ ഡോക്യുമെൻറ്റ്സും കഴിഞ്ഞ കോൺഫറൻസിന് ഇത്ര ഭംഗിയായി ചെയ്തത് സാറ് തന്നെയാണ്. അപ്പോൾ എനിക്കധികം ഒന്നും ചെയ്യേണ്ടി വന്നില്ല. അപ്പോൾ NTAC 2019 പകരം 2023 ഇട്ടാൽ മതി. അങ്ങനെ സാറ് ഡോക്യുമെൻ്റ് ചെയ്യും, അത് ജസ്റ്റ് പേര് മാത്രം മാറ്റുക, പിന്നെ താഴെ ഇഗ്നീഷ്യസിൻ്റെ അവിടെ ഫ്രാങ്ക്ലിൻ സാറിൻ്റെ പേരിടുക, അങ്ങനെ ചെയ്ത് പോവുക. അപ്പോൾ അതുകൊണ്ട് എനിക്ക് ഒരു എഫേർട്ട് ഒന്നും വേണ്ടി വന്നിട്ടില്ല. സ്റ്റിൽ ഐ റിമെമ്പർ പൊളിറ്റിക്കൽ ക്ലിയറൻസിന് വന്നപ്പോൾ ഫ്രാങ്ക്ലിൻ സാർ എനിക്കൊരു മെസ്സേജ് ഇട്ടു, താങ്ക് യു റാം ഫോർ യുവർ എഫേർട്ട്. ആക്ച്വലി അത് ഇഗ്നീഷ്യസിൻ്റെ എഫേർട്ടാണ് കേട്ടോ ഫ്രാങ്ക്ലിൻ സാർ, അങ്ങേരാണ് എല്ലാം ചെയ്തു തന്നത്. സോ താങ്ക് യു ഡോക്ടർ ഇഗ്നീഷ്യസ് ഫോർ ഓൾ യുവർ സപ്പോർട്ട്. പിന്നെ ഡോക്ടർ ഗ്രേസ് തോമസ്, അത് എന്തു ചെറിയൊരു കാര്യമായാൽ പോലും എനിക്കൊരു വോയിസ് മെസ്സേജ് ഉണ്ടാവും മിസ്സിൻ്റെ, രാമ അത് നോക്കണം, രാമ ഇത് ചെയ്യണം, രാമ അവരുടെ ലോണ്ടറിയുടെ കാര്യം നോക്കണം, രാമ ഇന്നത് ചെയ്യണം. അങ്ങനെ ഓരോ ചെറിയ മൈന്യൂട്ട് തിങ്സ് വരെ ഇത്ര ശ്രദ്ധയോടെ ചെയ്യുന്നതും, കാരണം അത്രയ്ക്ക് ഇൻവോൾവ് ആയിരുന്നു ഇൻ ദ പ്രീവിയസ് ടു NTAC-ൽ. അപ്പം അതുകൊണ്ട് ഇങ്ങനെ എല്ലാ കാര്യങ്ങളും നന്നായിട്ട് പിന്നെ എപ്പോഴുണ്ടായി രാമ ചോദിക്കണം, എപ്പോഴുണ്ട് രാമ എന്തായി, അങ്ങനെ ഒരുപാട് തവണ എൻക്വയറി ചെയ്യുക. അത്രയ്ക്കൊരു മോറൽ സപ്പോർട്ടും തന്ന ഡോക്ടർ ഗ്രേസ് തോമസ്. റിയലി താങ്ക്ഫുൾ ടു ഡോക്ടർ ഗ്രേസ് തോമസ്. താങ്ക് യു. പിന്നെ ഇന്നത്തെ വെൽക്കം സ്പീച്ച് ഇത്രയ്ക്ക് ഇംഗ്ലീഷിൻ്റെ ലാംഗ്വേജായ ഡോക്ടർ ജിനു ജോർജ്. ഇപ്പോൾ പ്രോഗ്രാം കമ്മിറ്റിയിൽ ജൂൺ മിസ്സിൻ്റെ കൂടെ ജിനു മിസ് ഉണ്ടായിരുന്നു. പിന്നെ അതുപോലെ തന്നെ ഒരു കൾച്ചറൽ പ്രോഗ്രാം ഞാൻ പറഞ്ഞില്ല, ഗ്രേസ് മിസ് കൾച്ചറൽ പ്രോഗ്രാമിന് ഒരുപാട് മിസ്സിൻ്റെ ഒരു കോൺട്രിബ്യൂഷൻ ഉണ്ടായിരുന്നു അലോങ് വിത്ത് ജിനു മാം. അപ്പോൾ അവരുടെ സീനിയേഴ്സ് എന്ന് വെച്ചാൽ അത്രയ്ക്ക് സപ്പോർട്ടായിരുന്നു. കാരണം എന്തുണ്ടെങ്കിലും അവരോട് നമ്മൾ ഡിസ്കസ് ചെയ്യുകയും എന്ത് ചെയ്താലും അവർ നമുക്ക് രാമ കുഴപ്പമില്ല എല്ലാം പോസിറ്റീവ് ആവും, ഞാൻ ഇന്ന് പ്രാർത്ഥിച്ചിട്ടുണ്ട്. ജിനു മിസ് എപ്പോൾ കണ്ട രാമ ഞാൻ ഇന്ന് പ്രാർത്ഥിച്ചിട്ടുണ്ട്. സോ ഫോർ ഓൾ യുവർ പ്രേയേഴ്സ് ആൻഡ് ഓൾ യുവർ പ്രസൻസ് റിയലി താങ്ക് യു ഡോക്ടർ ജിനു. പിന്നെ ഇപ്പോൾ ശരിക്കും പറഞ്ഞാൽ ഇത്രയൊരു സിമ്പോസിയം വരുമ്പോൾ എനിക്ക് ഭയങ്കര ഒരു റിലാക്സ് ഞാൻ ഫീൽ ചെയ്തിരുന്നു. കാരണം ആ റിലാക്സ് എനിക്ക് കിട്ടിയതുണ്ടെങ്കിൽ അത് ഓൺലി ബിക്കോസ് ഓഫ് എന്താ പറയുക അവർ HOD ഡോക്ടർ ഫ്രാങ്ക്ലിൻ ജോ. കാരണം സാറ് ഒരിക്കൽ പോലും അങ്ങോട്ട് ചിലപ്പോൾ സാറിന് ദേഷ്യം വന്നിട്ടുണ്ടാവും, ഫ്രാങ്ക്ലിൻ സാർ പ്ലീസ്. സാറ് ചില സമയത്തൊക്കെ വരുമ്പോൾ രാമൻ അത് ഇൻവിറ്റേഷൻ അയച്ചു, അയ്യോ ഞാൻ മറന്നുപോയി സാർ, കുഴപ്പമില്ല അയച്ചു. അപ്പം അങ്ങനെ ഓരോ കാര്യത്തിലും ഇടയ്ക്കൊക്കെ വീഴ്ച വരുമ്പോഴും സാറത് കൂളായിട്ട് ഹാൻഡിൽ ചെയ്യുകയും ഒരിക്കൽ പോലും എനിക്കങ്ങനെ ഒരു പ്രഷറും തന്നിട്ടില്ല. ശരി, നമ്മളൊരു കാര്യം ചെയ്യുമ്പോൾ നമുക്കൊരു ഫ്രീഡം വേണം, എന്നാലും നമുക്കതൊരു കംപ്ലീറ്റ് ആയിട്ട് ചെയ്യാൻ പറ്റുള്ളൂ. ആൻഡ് ദാറ്റ് ഫ്രീഡം അത് എനിക്ക് ഒരുപാട് ആസ് എൻ HOD ആൻഡ് ആസ് എ കൊളീഗ് ആസ് എ സീനിയർ ഫ്രാങ്ക്ലിൻ സാർ എനിക്ക് ഒരുപാട് തന്നിട്ടുണ്ട് സാർ. അത് എന്താ പറയുക, ഈവൻ ഓൾ ദ പ്രൊഫസർ ഇറ്റ്ഷോക് ടോർ, നോബൽ ലോറേറ്റ്, ഓൾ ദ പീപ്പിൾ ഹാസ് കം ത്രൂ ഫ്രാങ്ക്ലിൻ സാർസ് കോണ്ടാക്ട്. പിന്നെ അത്രയ്ക്കൊരു ഇന്ന് സപ്പോർട്ട് എല്ലാത്തിലും, അത് ഐ ഡോണ്ട് നോ വാട്ട് വേർഡ്സ് ടു സേ ടു യു മൈ HOD. And really you are such an inspiring HOD, and for your smooth word, thank you sir. അപ്പോൾ എനിക്ക് ഇത് ടീച്ചേഴ്സ് ഇത് ഇത്രയും എത്ര പറയണമെന്ന് എനിക്കറിയില്ല. ഓൾ ദ ടീച്ചിങ് സ്റ്റാഫ് അത്രയ്ക്ക് അവർ സപ്പോർട്ടാണ്. അപ്പോൾ എത്ര കുറഞ്ഞിട്ടുണ്ടെങ്കിലും ഐ എം എക്സ്ട്രീംലി സോറി, പക്ഷേ അത്രയ്ക്ക് അവരൊരു സപ്പോർട്ട് എനിക്ക് കിട്ടിയിട്ടുണ്ട് ഫ്രം ഫ്രാങ്ക്ലിൻ സർ ടു ഷാലുമോൻ സർ. So I sincerely thank from the bottom of my heart all my 13 colleagues for their support. Really thank you. അതില്ലെങ്കിൽ അത് കാരണം ഓരോ സ്റ്റേജ് കഴിയുമ്പോൾ അവർ എത്രത്തോളം ഇൻവോൾവ് ആണ്, എത്ര ക്ലാസ് അവർ ഇതിനു വേണ്ടി മാറ്റി വെച്ചിട്ടുണ്ട്, എന്തോരം എഫേർട്ട്, ഇവൻ എക്സാമിൻ്റെ കാര്യം എല്ലാം മാറ്റി വെച്ചിട്ട് ഇതിനു വേണ്ടി തന്നെ ദേ ഹാവ് ഡെഡിക്കേറ്റഡ് ദംസെൽസ്. സോ റിയലി ഐ ആം എക്സ്ട്രീംലി എന്താ പറയുക ഭയങ്കര ബ്ലെസ്ഡ് ആണ്. ആൻഡ് ഇത്രയും ചെയ്തപ്പോൾ ഇത്രയും ടീച്ചിങ് സ്റ്റാഫിൻ്റെ ആ ഒരു പൊട്ടൻഷ്യൽ എന്ന് പറയുന്നത് ഒരു ഭയങ്കരമാണ്. ഇത്രയ്ക്ക് ഏബിളുള്ളൊരു 13 സ്റ്റാഫിനെ, 13 ടീച്ചിങ്, 13 വ്യക്തിത്വങ്ങളെ ദൈവം എനിക്ക് തന്നല്ലോ. അതിന് ഐ എം ഹൈലി ബ്ലെസ്ഡ്. താങ്ക് യു ഓൾ മൈ കൊളീഗ്സ്. ദെൻ മൈ നോൺ ടീച്ചിങ് സ്റ്റാഫ് ജോൺസൺ, അന്ന ആൻഡ് ചിഞ്ചു, എന്താ പറയുക അവർ എല്ലാത്തിലും അവരൊരു സപ്പോർട്ടുണ്ട്, എവ്രി വൺ. സോ താങ്ക് യു ഓൾ ദ നോൺ ടീച്ചിങ് സ്റ്റാഫ് ഓഫ് അവർ ഡിപ്പാർട്ട്മെൻറ്റ് and or of the office. കാരണം ഓഫീസിലെ ഒരുപാട് ഇപ്പോൾ ജൂഡേട്ടൻ അവർ ഡോക്ടർ തമ്മോക്കിയുടെ ട്രാവലൊക്കെ അവരാണ് ചെയ്തത്. ആൻഡ് all the non-teaching staff, they have really helped us. Then രഞ്ജിത്ത് ഉണ്ടോ ഇവിടെ? രഞ്ജിത്ത് എന്ന് പറയുന്നത് വലിയൊരു പ്രസൻസ് ആണ് രഞ്ജിത്ത്. ഓക്കെ, പറയും. അപ്പോൾ രഞ്ജിത്തിൻ്റെ വലിയൊരു കോൺട്രിബ്യൂഷൻ, നിങ്ങൾ ഇത് കാണുന്ന സ്ക്രീൻ എല്ലാം രഞ്ജിത്തിൻ്റെ ഒരു വലിയൊരു ഹാൻഡ് ഉണ്ട് അതിൽ. സോ റിയലി താങ്ക്ഫുൾ ടു യു രഞ്ജിത്ത്, താങ്ക് യു. പിന്നെ സഞ്ജയ് ആൻഡ് ദെയർ കമ്പ്യൂട്ടർ ടീം, പ്രിജോ. അപ്പോൾ അവരുടെയൊക്കെ വലിയൊരു ദേ ആർ ആക്ച്വലി ബിഹൈൻഡ് ദ സീൻസ് ആണത്. ദേ ഹാവ് ഡൺ എ ലോട്ട് ഓഫ് തിങ്. താങ്ക് യു വെരി മച്ച്. ദെൻ ഇപ്പോൾ ഒരുപാട് കാര്യങ്ങൾ പ്രിൻ്റ് ഔട്ട് എടുക്കണം. അപ്പോൾ പ്രിൻ്റ് ഔട്ട് എന്ന് വെച്ചാൽ അത് നല്ല പ്രിൻ്റ് ഔട്ടുള്ളത് IQACയിലെ റൂമിലാണ്. അപ്പോൾ അത് ശ്രീജിത്തും അലൻ ശബദ് അവരൊക്കെ എപ്പോൾ ചോദിച്ചാലും ദേ ആർ റെഡി ടു ടേക്ക് ദ പ്രിൻ്റ് ഔട്ട് ആൻഡ് എവറിത്തിങ്. റിയലി താങ്ക്ഫുൾ ടു ഓൾ ദ IQAC ടീം ഹെഡഡ് ബൈ ഡോക്ടർ ഇഗ്നേഷ്യസ്. താങ്ക് യു. പിന്നെ കൾച്ചറൽ പ്രോഗ്രാം, ഐ തിങ്ക് ഓൾ ഓഫ് വെയർ ബെനിഫിറ്റഡ് വിത്ത് ദ കൾച്ചറൽ പ്രോഗ്രാം. Actually, they were done by a team of Lakshmi Priya Miss, Shobha Miss, then Boni sir, everything. So, from the bottom of my heart, I thank all the people for their excellent cultural program. Then, media പറഞ്ഞപ്പോൾ അതിൽ ഏറ്റവും നമ്മൾ സപ്പോർട്ട് ചെയ്ത കമ്മ്യൂണിക്കേഷനിൽ സുജിത് സാർ ആയിരുന്നു, അലോങ് വിത്ത് ബാബു ജോസഫ് സാർ. സോ റിയലി താങ്ക്ഫുൾ ടു യു സുജിത്ത്. പിന്നെ ഒരുപാട് കമ്മിറ്റീസില്ല, നമ്മുടെ സൈൻ, ലൈറ്റ് ആൻഡ് സൗണ്ട്, ഫുഡ്, ഡെക്കോറേഷൻ, എവറി പീപ്പിൾ. Really thankful to all the people. And finally, our own students. അത് എനിക്കറിയില്ല എന്താ പറയേണ്ടത്, അത്ര എന്തായാലും ഇപ്പോൾ എല്ലാ ഡിഗ്രി സ്റ്റുഡൻസ് ആൻഡ് MSc സ്റ്റുഡൻസ് റിയലി ത്രൂ ഔട്ട് ദ 2 days, നോട്ട് ഓൺലി ഓൺ 2 days, എല്ലാവരും. ഇപ്പോൾ ഇതാ കുറച്ച് പേര് ഇവിടെ നിൽക്കുന്നുണ്ട്, കുറച്ച് പേര് ഇവിടെ നിൽക്കുന്നുണ്ട്. എല്ലാ കമ്മിറ്റീസിലും ഒരുപാട് സ്റ്റുഡൻസ്, അവരുടെ സപ്പോർട്ട് എന്ന് പറഞ്ഞാൽ ഭയങ്കര ഇൻവാല്യുബിളാണ്. ഇപ്പോൾ കുറേ പേര് ട്രാവലിൽ അവിടെ പോയിട്ടുണ്ട്, അവരാക്കാൻ പോയി, ഡെലിഗേറ്റ്സിന് എയർപോർട്ടിലും റെയിൽവേ സ്റ്റേഷനിലും എല്ലായിടത്തും ആക്കാൻ പോയി. എല്ലാവരും എല്ലാ കമ്മിറ്റീസിലുള്ള എല്ലാ സ്റ്റുഡൻസും റിയലി താങ്ക്ഫുൾ ടു യു. നിങ്ങളാണ് ഇതിൻ്റെ ആ ഒരു റിസർച്ച് സ്കോളേഴ്സ്, എവറി സ്റ്റുഡൻസ്, റിയലി താങ്ക്ഫുൾ ടു ഓൾ ദ തിങ്സ്. എനിക്കറിയില്ല, ഞാൻ ഒരു സെക്കൻഡ് ഒന്ന് നോക്കിക്കോട്ടെ ആരെങ്കിലും വിട്ടിട്ടുണ്ടോ എന്ന്. ഇല്ല, കാരണം പിന്നെ എനിക്കൊരു അവസരം കിട്ടിയില്ല പറയാൻ, അതുകൊണ്ടാണ്. ട്രാവൽ ഫുഡ്, പിന്നെ യൂട്യൂബിൻ്റെ പറഞ്ഞു, ഇല്ല പിന്നെ എനിക്കൊരു അവസരം കിട്ടിയില്ല. കാരണം ഇത്രയും ആൾക്കാരില്ലെങ്കിൽ ഈ ഒരു പ്രോഗ്രാം നടക്കില്ല. അപ്പോൾ നന്ദിയുടെ ഒരു വാക്ക് വലിയൊരു വാക്കാണത്. ഓക്കെ, സോ ആരെങ്കിലും ഞാൻ മിസ് ചെയ്തിട്ടുണ്ടെങ്കിൽ ഐ എം എക്സ്ട്രീംലി സോറി, ബട്ട് റിയലി താങ്ക്ഫുൾ ഓൾ ഓഫ് യു. പാർട്ടിസിപ്പൻറ്റ്, സോറി. അപ്പോൾ നമ്മൾ ഒരുപാട് കോളേജസ്, ഡിഫറെൻറ്റ് പാർട്ടിസിപ്പൻറ്റ്സ് ഫ്രം നോർത്ത് ടു സൗത്ത് ഓഫ് കേരള, ഔട്ട്സൈഡ് കേരളയിൽ നിന്ന് കുറവായിരുന്നു ഓൺലൈൻ പാർട്ടിസിപ്പൻറ്റ്സ്. റിയലി വിത്തൗട്ട് പാർട്ടിസിപ്പൻറ്റ്സ് ഒരിക്കലും എന്താ പറയുക ഒരു പ്രോഗ്രാം സക്സസ് അല്ല. സോ റിയലി താങ്ക്ഫുൾ ടു ഓൾ ദി പാർട്ടിസിപ്പൻറ്റ്സ് ഫോർ ദെയർ 2 days stay here and for their presence, for their lectures, for their poster presentations. Really thankful to all the participants from bottom of my heart, from chemistry department and from Sacred Heart College, Thevara. ഇനി ആരെങ്കിലും വിട്ടിട്ടുണ്ടോ? So really thankful to all the people, and finally everything I humbly dedicated to the Almighty God. Thank you very much.
Thank you so much, Ramakrishnan sir. A gentle reminder to all the participants out here. The best color has been arranged and it's passing through South Railway Station. If any of the participants want to board at South Railway Station, you can avail the same. Now, I kindly request everyone to rise for the national anthem.
पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय
The end of the story is a new beginning for many others. On this note, we have come to an end of 21st Professor K.V. Thomas Endowment Seminar and the 4th International Symposium on New Trends in Applied Chemistry 2023. On behalf of the Sacred Heart College, Postgraduate and Research Department of Chemistry, we sincerely thank the dignitaries for being with us and enlightening us. Also, I extend my sincere gratitude to each and everyone who is involved in the program and making it a grand success. Once again, thank you so much for your valuable presence. Our refreshments are arranged in the Marian Hall. Kindly enjoy the refreshments.